Hello and welcome from Chicago. In this lesson, I'm going to contrast web services with something that may be a bit more familiar, websites. You can see on the screen that I've got my browser open to Amazon. The idea is to give us a feel for how web services are like websites. After all, they both include reference to the web, but also how they differ. And this in turn will help us get a better sense of what web services are good for. So I'm here at Amazon. Again, I'm using a browser quite obviously. And now I'm going to do typical browser type things. I'm going to do a search. So I'm going to type in the name of an author and a book. Let Amazon do a little bit of searching. And as you can see, I get some results. Now let me just point to the obvious. I'm in a browser. I send a request to the Amazon web server. The Amazon web server responds with HTML, which my browser then displays. I can continue this, of course. I can continue my searching. I can place an order. I can change my credit card. I can decide whether I want the book that I ordered to be gift wrapped, all of that good stuff. What I'd now like to do is approach this same process from a different angle. And of course, that angle is going to be web services. So to that end, let me close this down and bring up my Emacs editor. You're looking at one of the working files. It's called wishlist.txt. It's very simple. And the first entry is reminiscent of a database record. So you'll see the author's name in the first column, Hilary Mantel. Second column, name of novel. Third column, ISBN number. And then the fourth column is the maximum amount that I'm willing to pay for this book. The ellipses, of course, are the danger point for me because these are other books or items on my wish list. So here's the general idea. I have this little file. It's my wish list. I could now write a program basically in any language I like. And nowadays, almost every language has sufficient libraries to do what I want to do. So I write a program which basically is a web service client, and it goes against the Amazon e-commerce web service, not the web site that we just visited. And the reason for this is that Amazon has been particularly good at pairing websites with web services. In the case of the e-commerce site service pair, anything that I can do there interactively, I can do programmatically. Now again, you may be like I am. I actually enjoy the process of browsing for books, looking them over, mulling over whether I want to buy a given book and so forth. So I like the shopping process, but the point of interest here is that we could automate this. Now, I didn't pick Amazon by accident. Let me bring up another one of the working files. It's called amazon.txt, and this is just a very quick summary of what Amazon has pioneered over the years. So the e-commerce service is the one that we just talked about. Amazon also has the simple storage service, S3 for short. Some of you may be using that. It's got cloud computing services under the label EC2, and the general point that I'd like to make once again is that you can access all of these, in the case of Amazon, as either websites or as web services. Now there's going to be some obvious differences. So there you see a 3-bullet summary of websites and web services. And what I'd like to do, rather than read that summary, you can see it. It's not very long. I'd like to make some general points. One of the attractive things about web services is that they piggyback on existing infrastructure. In particular, they piggyback on web servers such as Nginx, Apache 2 Tomcat, which is a Java-based web server. We'll be seeing quite a bit of that. They piggyback on other technologies as well, HTTP, including HTTPS. The interaction from the client side with either a site or a service is fairly familiar. It's basically request response. The big difference, of course, comes in the software that is used on the client side. So if you visit a website, you're doing so interactively, usually using a browser. If you're visiting a web service, you're doing that programmatically. And except in development or perhaps test mode, you're certainly not going to use a browser. you're going to use what I'm going to call an arbitrary program. So you're going to write a web service client in some program of choice or some language of choice and use that to talk to the web service. So there are notable similarities and there are some minor differences. From either a programmer's or a business person's point of view, the real appeal of web services is that everything you need to do them is probably already at hand. And Java, as we're going to see, is particularly good both for writing web services and for writing clients against those web services. In this lesson, we're going to look at a full code example. What you're looking at in my Emacs editor is a working file called firstexample.txt, and it's just an inventory of what needs to be done to pull off a full example. I'm going to use it to talk about what we'll emphasize in this lesson and what we'll emphasize in later lessons. So on the service side, this is clearly where we have to start. We need to write the service and then publish it. Java is very good at this. It supports a clear separation of concerns. Writing the service is one thing, publishing it is a different concern, and how you write the service doesn't close off options about how you publish it. So I'm going to write the service using JSP, Java Server Pages. You may have used this, for example, in websites. I'm going to use it in a web service. And I'm also going to use some back-end so-called POJO code, plain old Java object. In other words, a straight Java bean. I'm actually going to use two of those. They're fairly straightforward. We'll look at those a bit later. For publication, I'm just going to tell you how I'm publishing it now. We'll go into some details later. So I'm using the Tomcat web server. The current version 8, Tomcat 5.5 or greater is probably going to be just fine. Now the client side is a bit tricky. We don't want to spend time today writing a full client in Java or in some other language. We could do that, but there's an excellent command line utility called curl, C-U-R-L. I've got the URL down there. Basically right here, curl will run on any platform you're likely to be using, and it's very convenient for the sort of thing that we're doing. It's more convenient, for example, than using a browser as a test client. So I've got a couple of curl commands that we'll look at in a bit, and I'm going to use those to make sure that the service is up and running and behaving as expected. So let me start on the service side, and I'm going to bring up another working file. This one is called predictions, all lowercase, .jsp. So this is the JSP script. Now at the top, you see some standard Java comments. And what I'm doing here is just summarizing the flow of control. So a client to my web service is going to come in and hit the JSP script. The JSP script is going to do a little bit by way of proof of concept, but then it's going to turn to the back-end Java Bean code to do the heavy lifting. And we'll look at that code in a bit. Right underneath, you see two curl commands. So I've given them there literally. In fact, I'm going to copy and paste these to the command line shortly. The first request is a so-called GET request. By the way, ---- request GET is actually the default, so we could drop that, but I've put it in for emphasis. This is going to hit the service, and we're going to get back some XML. The second curl command issues a POST request against the service, and a POST request is not acceptable for this particular service. We can craft the service any way we like. In this case, just as proof of concept, what I'm going to do is outlaw POST request. I'm going to honor only GET requests. The code starts right here. So to highlight it, basically from here to here is my JSP script. I think I'll leave that highlighted for the moment. And it's fairly straightforward. If you look at the very first line, you see JSP : use bean. What I'm doing here is referencing one of those back-end POJOs. In this case, the POJO called predictions. When we look at the data, you're going to see that the web service returns rather silly corporate type predictions. So we'll see some examples momentarily. This is the sort of thing that might come from a database. In my example, to keep life simple, I'm basically going to read these from a text file. In any case, right now, what I want to do is take a closer look at the code. And the code starts at this line. This area right here, let me highlight it again for emphasis. This is what, if you've not used JSP before, this is what people sometimes refer to as a scriptlet. So it's a little bit of Java code embedded right in the JSP script. I would say in general, this is not considered best practices, but I'm going to use it right now because I want to take a look at how web services look from the service side. So I've got lines numbered over on the right as comments, 5 of them, and we're going to take them in order. I'm going to give a very quick explanation of how they work, and then we're going to check to make sure that this service actually does work. So the very first line, you see request.getMethod. This is my way of retrieving the so-called HTTP verb. In other words, is the incoming request a GET request, a POST request, a PUT request, a delete request, or something else? So I retrieve this as a string, and then as you can see, as I move down to line 2, I check to make sure that this is a GET request, and if it isn't, we're basically done. I send back a response to the client saying, GET requests are the only sort of request that I honor. You've come in with something else, so I'm not going to honor that request. Down in the else clause, in particular at line 4, I need to do some setup, and I'm going to defer the explanation of that setup until we look at the back-end Java code. For now, line 5 is more important. What happens in line 5 is I basically get the prediction list that I mentioned before, and I send it back to the client. It's going to go back as rather straightforward XML. It's now the client's job to parse that XML, to extract the data, and so forth. But at the conclusion of line 5, in effect, my service has handled the client request. The client is welcome to make another request, but basically we're done. What I'd like to do now is illustrate the 2 curl requests. So to that end, let me make a copy of this and open up command line prompt. There's my curl request. It's going against the Tomcat web server, which is running on the same machine in this case. So when I hit this, as you can see, the screen is now filled with a bunch of XML. So let me just highlight 2 parts of it. So we'll sort of do a manual parse of the XML. So about a quarter of the page down, I've highlighted this in blue. You can see that Devin Blanda is the predictor in my jargon. So this is who is making the prediction. And then the prediction is this rather inflated claim that balanced, clear thinking utilization will expedite collaborative initiatives, whatever that might mean. In all, I've got 32 of these. As you might guess, under the hood, I'm storing them in a Java array. So let me now clear the screen, and let me retrieve that curl command and change the GET to a POST. A POST request conceptually is a create request. A GET request conceptually is a read request. So my web service, if you like, supports read operations, but not create operations. So this is going to be rejected. So I hit the return, and what I get back, as you can see, is an HTML document. The reason for that is that my JSP script assumes that you're hitting it from a browser. You're really not. In this case, we're using curl instead. I could change it so that the return document was plain text or something else, but in the interest of simplicity, I've just taken, you might say, default JSP behavior. The important part is this. If you look at this line, this is basically my error message, that the specified HTTP method is not allowed for the requested resource, and up above is actually the string that I provided, GET requests only are allowed. The important point that we've seen here is that the service is actually being published, and we're getting the behavior that, in this case, I expect. What I'd like to do now is go back to my code, So again, this is the JSP script, and what I'd like to do is look very briefly at the backend POJO code. Then I'll talk a little bit about deployment. All right, so let me bring up another one of the files in the working files directory. This is prediction.java, prediction singular, no S. And as you can see by inspection, I'm sure you've seen this kind of code quite a bit in Java. It's the modern approach. This is a so-called POJO class. It implements the serializable interface for reasons we'll get into a bit later. Let me just note that the serializable interface is empty. It doesn't require me to do anything. There's basically no harm. We could take that out, but for reasons we'll get to a bit later, I'd like to leave it in. So what you see is the usual. I have a no argument constructor. We could take that out, of course. And then you see two properties following the standard Java idiom. There's a who property. This is the person that makes the prediction. And there's a what property, and this is the prediction that is made. So this is about as straightforward as Java code gets. Each instance of a prediction represents one of those 32 predictions that we saw in XML. So the more interesting class is also in the working files folder, and this is predictions with an S. And as you can see, there's a bit more here. Now let me make a general point. This again, by the way, is a POJO class, and there's quite a bit of code in here. Some of it's a little bit complicated. Some of it we'll return to later. Let me just break it down into two broad categories. Some of this is straight data processing. In other words, I need to read the predictions from a file. They're in a text file. I need to bring them into my program, put them in an array, break them up appropriately. I'm not going to focus on that code because that's not web service specific. I want to focus on the stuff that is web service specific. And that begins right here at this line, line 2. Line 1 above is part of this setting up. And we'll get to that eventually, but not right now. So get predictions is the get part of a predictions property, pretty straightforward. So what I now do is this. Down in this if statement, I'm checking to make sure I have everything I need in order to read the text file. By the way, in a more realistic example, this might entail reading from a database. So the same sort of integrity check that you'd expect to find there. The second if statement makes sure that my predictions array is already populated. So the first thing I check is, could I populate this array if I had to? And the second is, have I already done it? If I've already done it, I'm not going to do it again. Finally, this is the web service specific code. You can see I call return to XML. And that code, let's move down a bit so we can take a look at it. You can see there's populate. It's a little bit tricky. Here's to XML. So I've got 4 through 9 over here on the comment section. So these are the lines of interest. Some of these lines, again, I'll go over pretty quickly. Where needed, we return to them later. So the important line is actually 5. I create an XML encoder. This has been around in Java for quite a long time, since Java 1.2, if memory serves. And the XML encoder is going to do just what the name suggests. It's going to take a Java object, in this case an array, and it's going to encode it as an XML document. That document we're going to send back to the client. So at line 6, I take the predictions array, which has been populated now with prediction instances, who says what, basically, and I write that out using the encoder. And then at line 7, I close the encoder to signal to the runtime, I'm done with it, don't need it anymore. And then line 8, I get a string representation of this thing. The string representation, in effect, is the XML document that goes back over to the client. And that happens in line 9, where I return this string. Let me summarize. And let me summarize by going back to predictions.jsp, which is where we started at the code level. So a remote client, in our case, this is really a Perl client on the same machine, but a remote client could hit this JSP script, and the processing then would start in this little scriptlet at line 1. We do an integrity check. If you like, it sounds a little highfalutin to call it a security check, but in effect, it is a sort of security check. We're trying to filter out anything but read requests. So we check to make sure that we got the right kind of request. That's done in this code, basically 1 through 3. And then lines 4 and 5 make contact with the backend POJO. In this case, it's the predictions object. And from the predictions object, we get this XML representation of the predictions, and we send this back to the client. Now, this first example is what web services people would call a RESTful or a REST-style web service. REST is an acronym, of course, R-E-S-T. And in the next lesson, we're going to take a look at what that means. So what I'd like to do is take a brief pause here, and when we return, we'll pick up this topic again by talking about REST. In this lesson, we're going to pursue the theme of what web services are good for. So I'm going to provide an example of task automation. I'm going to talk a little bit about Java-based data retrieval from a browser and software system integration. You see those 3 items listed in one of my working files. It's called y.txt, and you're seeing it in my Emacs editor. So let me start with the task automation, and let me bring up another working file that summarizes that. This file is called erp.txt, and what I'm going to describe is something that's probably familiar to you from your work. So suppose we have a company, we need inventory items, perhaps we do manufacturing. You could manage the inventory, of course, interactively. You could have a human look at it regularly and control it, but you can also get very strong programmatic control nowadays using so-called ERP systems, in particular, the inventory control subsystem of such a system. So I'm thinking of something pretty straightforward. I have a program that monitors my database. When inventory levels fall below a particular threshold, that program cranks up a web service client, which goes against the web services that vendors provide. So basically, the selection of the appropriate inventory items, the placing and tracking of orders, all of that good stuff can be done automatically. This is a wonderful use of web services because it just fits in so naturally. Once again, the web service is piggybacking off of existing infrastructure. There's no fancy programming required. It's fairly straightforward. Let me return to my little list and look quickly at the second item. I don't have a nice, concise phrase to describe this, so what I'd like to do instead is show you a couple of examples. So first, let me bring up another working file. I call this yahoo.txt. Let me explain how I got this. I simply visited the Yahoo website and then did view source to get the HTML page, and I extracted some arbitrary JavaScript. The JavaScript itself is of no particular interest to us. This does a little bit of cookie tracking. We don't care about that so much. The point of interest is that virtually every HTML page nowadays has embedded JavaScript. And that's the theme that I'd like to pursue. So what I want to show you now is a website. Let me come up here and enter meteor.com. Meteor is a bleeding edge web framework. It's gotten quite a bit of buzz over the past year or so. If you look at this web page, it looks fairly conventional. What I'm going to do now is go back and look at some of the code under the hood. So to that end, I'm going to bring up another working file, meteor.txt, and I'm going to move down here. As you can see, it's a HTML document. I'm going to move down here to the bottom and highlight this part. Notice that the body of the HTML document is completely empty. There's nothing in there. This is typical for any Meteor web page. The magic of Meteor occurs up here. So you see here a link to some JavaScript. When this page is loaded into the browser downloads this JavaScript. This JavaScript then builds the so-called DOM, the data structure that the browser displays in a window. It builds that DOM in place. And in the course of building the DOM, this JavaScript goes off to a web server, or perhaps web servers, to download data. In that capacity, the JavaScript is acting as a web service client. This is becoming increasingly popular in website design. The use of JavaScript embedded in the HTML page and acting as a web service client. We'll be spending quite a bit of time on this particular theme. Let me return one last time to y.txt, our overview, and I want to talk a little bit about software system integration. I'm going to bring up a PowerPoint slide in just a moment, but first let me make two general points about web services. An attractive feature of web services is that they're language neutral. You can write a web service in one language, you can consume the web service in a completely different language. Web services are also inherently platform independent. It doesn't matter whether you're working on a Windows platform. Web services effectively blur platform and language distinctions. So it's nice. I can write a web service in whatever language I'm most comfortable with. You can write a client against that service in whatever language you're most comfortable with. So what I've depicted here on the right is a legacy database system. The database system isn't so important. This might be a COBOL program, a Fortran program, a C++ program, whatever sort of program is of interest to us. And it's been front-ended as a web service. And then on the left, you see clients making calls against the web service in order to talk to the back-end system. Now, where does the need for this sort of thing arise? Well, it's very familiar in our business. You have a company with its information systems. It acquires another company with different information systems. As you can imagine, the management says, we need those systems to be integrated yesterday. We can't afford to rewrite those systems. What's a quick and relatively pain-free way to achieve systems integration? So what we've looked at is task automation. We did that in an earlier example with Amazon. Today we talked a little bit about inventory control, JavaScript and web services, a theme we'll pursue at some length at the code level, and software system integration. Three natural and fairly straightforward uses of web services. In this lesson, we're going to look at our first code example, which you see on the screen is one of my working files. This one is called firstexample.txt. We're looking at it in the Emacs editor, and it's just a quick inventory of what's required for the example. So on the service side, which is where we're going to focus to begin, we need to write the service and then publish it. The service itself is written basically in three pieces. There's a JSP script, Java Server Pages, and then there are two back-end Java beans, so-called POJOs, plain old Java objects. For publication, I'm going to use Tomcat, which is a Java-based web server. Some of you may have used that before. You see the URL on the screen where it can be downloaded and easily installed. We'll go into those details a bit later. Now, on the client side, it's a bit trickier. In real life, we'd want to write a client in some language, but for testing purposes, the curl utility, you see the URL for it, is really convenient. Curl is available on all platforms, and it's possible if you have a Unix-type system that it's installed already. So, without any further ado, let's take a look at the code, in particular at the JSP page. So I'm opening up now another one of the working files. This is called predictions.jsp, and I'm going to go over it in some detail. So in the comments at the top, I indicate basically how this is going to work. So if you look at this line, a client is going to hit the JSP script, which is in effect the front end of the web service. And the JSP script is going to communicate with the backend Java Bean code in order to get the data to send back to the client. The service itself is fairly straightforward. When a client hits the service, the client receives a list of what I'm going to call sage corporate predictions. We'll see these in the flesh shortly. In order to test the service, I have two curl commands. One of them is here. That issues a GET request, which I'm going to honor. And the second is going to issue a POST request, which the server is going to refuse. So let's jump into the details. This very first line uses a customized JSP tag called useBean, and it identifies the object reference that I'm going to use in the code. I call this preds, short of course for predictions. The supporting code is a class called predictions, as you can see on the next line, and the class is predictions as well. By the way, I could drop either type or class. I don't need both, but I've included both. A little further down at this line, we begin what JSP folks call a scriptlet, embedded Java code. So this will look familiar, even if you've not seen JSP before. It's standard Java, and it relies on a number of so-called implicit object references, which my code picks up by way of inheritance. So in this case, I have an object reference called request. That's the incoming HTTP request. Another called response. That basically is a channel back to the client so I can communicate. The application is a little bit tricky. I'm just going to give it a name and explain it later. It's the servlet context. It allows me, in effect, to talk to Tomcat. And finally, the last implicit object reference is called out. That's the output stream. That's where I'm going to write the XML document that I'm going to send back to the client. So the logic is pretty straightforward. The first thing the code does is to filter on the HTTP request. So you see request get method at line 2. This is going to return a string. At line 3, I then check to see that this string is get. Uppercase, lowercase, mixed case, doesn't matter, as long as the request is a GET request. If it isn't, I'm going to generate a so-called status code, in this case 405, and in HTTP speak, 405 stands for method not allowed. So basically, my code is saying a GET request is okay, anything else is not okay, you're going to get an error. And you can see at line 4 a customized error. So response send error sends back the appropriate status code and then a little customized string message. If everything is okay, the else clause kicks in, and at line 5, the code makes use of the preds object reference, that's the one all the way back from line 1, in order to set things up so that it can get the data required. The data, again, consists of a list of corporate predictions. We'll see what these are momentarily. And then finally, the real action is in line 6. The preds object reference is used to get the XML document, and out print line sends that document back to the client. At this point, business is over. We've completed the transaction with the client, and the script simply exits. Now, in order to show how this works, let me bring up a terminal window. So I'm going to close the editor, and you can see a curl command up there at the top. I'm simply going to execute this. It runs, and let me highlight what's important. Devin Blanda is a corporate officer who makes this prediction above. So basically, Devin is the who, and this prediction is the what. As you can see at the line slightly above, you see void index 30. Let me highlight that. This indicates that the underlying predictions might have been generated from an array, which is exactly the case. There are 32 of them in all, and Devin's is just one of these. So basically, what the service has sent back to me, the client, is this XML document that represents all of the predictions. Let me show you what happens if I try to change this curl example to something else. What I'd like to do instead, and I'll clear the screen to make it more visible, is issue some other type of request. In this case, let's go for a put request. Post or anything else would do. Put is basically an edit request. If I do that, I basically get back an error page. So in this case, you can see the status code is 405. That's the method not allowed. And then hidden in this little HTML error document is my customized string saying get requests only are required. As proof of concept, then, we see that the service accepts get requests and rejects non-get requests. Those are the key points. So let me summarize. The service has been published with Tomcat, and we've tested it with 2 curl commands. So those curl commands are acting in effect as client requests. What we've not looked at is the back-end Java code, and we're going to do that after taking a brief pause. In this lesson, we're going to wrap up the first code example. What you see in my Emacs editor is one of the working files. It's called parts.txt, and it's a simple list of the code modules. So, in the last lesson, we looked at predictions.jsp. That's the JSP script that a client first hits. Down below are 2 so-called POJO classes, prediction.java and predictions.java. The prediction in the singular represents a single prediction, and a prediction has a who property that represents the person making the prediction, and a what property that represents the prediction itself. Predictions.java does the heavy lifting. For example, it builds an array of prediction objects. It converts that array into an XML document and returns that to the JSP script, which in turn returns the XML document to the client. I didn't want to use a real database. That would complicate things too much. So instead, I have a text file called predictions.db that acts as my database. So let's go back and take a quick review look at predictions.jsp from last time. There it is. And the point of interest for us is this object reference in line 1 called preds. That's an instance of the predictions.java class. So what I'm going to do is work my way to that class. To begin, I'm going to look at a single prediction. So what you see is prediction.java, another of the working files. It's one of these very simple Java Bean classes. It implements the serializable interface. That's of no particular interest to us right now. That's an empty interface, doesn't require any special work on my part. The important parts here are line 1, which is the set part of the who property, the person that makes the prediction. And then down here at line 2, you see the set what, which is the what part of the prediction. So in effect, what the service is going to do is populate an array with instances of this class. So let's look at the class that does most of the work, predictions.java, plural, another one of the working files. And this has some complexity to it. Today I'm going to move quickly over part of the complexity, the stuff that has to do with pure data processing, and focus on the parts that are relevant to the generation of the XML. So to that end, let me draw your attention to line 1. So you see something called set servlet context. For now, it's enough to say that the servlet context is how my application talks to the underlying publisher. In this case, let's just call that Tomcat, because I'm using the Tomcat web server. The important method for me is this one called getPredictions. So let me go through this quickly, because the details aren't that important to us. The first thing I do is I make sure that I can talk, in effect, to Tomcat, because Tomcat is going to help me read the data file. So that's what I'm doing here. So if getServletContext is null, there's nothing I can do. I can't read the data. We're basically out of luck. If I can talk to Tomcat, but my predictions array is in effect empty, then I need to populate it, and I'm going to do it with data. Let me do a very short digression to show you the data file. So this is another working file called predictions.db. As you can see, it's a simple text file. So for example, the first line, Cornelius Tillman, is the who. Managed holistic contingency will grow killer action items is the what. So let me return to here. So what I'm checking is to make sure I've read that data file. If so, I'm going to take my list of predictions and turn those into an XML document. So that for us is where the action really starts. And this is the toXML method way down at the bottom of the source code. So what I'm using in this particular case at line 5 is an XML encoder. This is one of the standard Java classes. It's been around forever, and it will take a Java object and serialize it out as an XML document, which is precisely what I need. At the next line, 6, I take the predictions list, I write it out, I close the encoder, and then what I do is stringify, if you like, the document. In other words, I get a text representation of the predictions list, and that's what we're going to see on the screen. So if I can now go back and bring up a command line prompt, I can do my curl thing. I'm going to simplify it this time to curl localhost 8080 / predictions / predictions.jsp. Voila. What we now have is the XML representation of that underlying list of predictions made from data in a text file using 2 Java POJO classes. That's a wrap, then, of the overview of this first example. Some details we've not covered, but we will return to those. What I wanted to do here was to give you the feel for what a simple web service would look like from the code level. In this lesson, we're going to focus on publishing the predictions web service. In the last couple of lessons, we've looked at the JSP script, the backend Java beans that make up that web service, but now we're going to get to the practical matter of how do we put the service together in such a way that it can be published and made available to clients. Basically, we need 2 things. The first is a web server. Java has various options. Tomcat and Jetty are probably still the most popular. They're both lightweight but production ready. Each of them can handle either websites or web services. We're interested, of course, in the web service part. The second tool is technically optional, but publishing a website or a web service tends to be tedious, and it's nice to have a tool that automates that. In this case, I'm going to use Ant, although Maven is another perfectly fine tool that can be used. So in this lesson, the emphasis is going to be on Tomcat. In the next lesson, we'll look at Ant. So let me turn to the Tomcat overview. We're now looking at a second working file. This is called tomcat.txt. The first file, by the way, was just called tools.txt. So this is a very quick overview of Tomcat. Let me just say for the record, you see the URL on the screen in front of you. You can install Tomcat in various ways. I prefer downloading the zip file and unpacking it. You can install Tomcat wherever you like in your local system. It doesn't matter. For reference, I'm going to use the term Tomcat Home to designate that install directory. And I'll show you where I've installed it on my Mac momentarily. Now I have a little bit of background. You can look at that at your leisure. The really important part for us is here in the middle, this little depiction. So you see Tomcat Home, and then underneath I've drawn 2 subdirectories that are of particular interest to us. The first is the bin subdirectory. That contains startup and shutdown scripts for both Unix type and Windows systems. So basically you run startup to start Tomcat and shutdown to shut it down. Normally, when I have it on, for example, one of my desktop machines, I have it running indefinitely. The only time I ever restart it is when I reboot the machine. The second subdirectory of interest is web apps. It's got various subdirectories, and the short version is this. The way you publish a website or a web service to Tomcat is you drop a jar file into the web apps directory or one of its subdirectories. It's as simple as that. If you want to unpublish something, you remove that jar file. If you want to update the thing, you overlay the jar file with a new copy. It's really very nice. You certainly don't have to stop Tomcat in order to redeploy or do anything like that. So what I'm now going to do is move to the command line so I can flesh some of these ideas out. So I'm opening up a terminal window on a Mac. This is actually a bash shell. So on my system, immediately under my home directory, I've put Tomcat 8. You might want to put it someplace else, but again, for emphasis, it doesn't really matter. Wherever you would like to install Tomcat, whatever name you would like to give it is just fine. So let me show you the directory structure. So again, I can highlight it maybe to make it slightly more visible. There's the bin subdirectory. Here's the web apps subdirectory. Let's just look at web apps for the moment, and then I'll come back to bin momentarily. Right now in web apps, you don't see any jar files. You basically see subdirectories, including something called examples. Tomcat comes with a bunch of sample websites already. We're not going to bother to look at those right now. Instead, I want to start Tomcat, confirm that it started, and then give you a brief overview of the other subdirectories under Tomcat. So to that end, again, here's where I am. I'm in Tomcat Home, and I'm going to do bin startup.sh. If you were on Windows, it would be startup.bat. So the old bat file. You'll get a little echo confirming basically that you have started. On the screen, you see this Catalina this and Catalina that. So let me just clarify. This is also in the working file. Tomcat technically is the name of the web server. Catalina is the name of the so-called servlet container, which is the most important component of the web server. Now, in order to confirm that Tomcat is running, I could use curl, but it's a little nicer to open up a browser, point it to localhost 8080. I'll refresh just for confirmation. And as Tomcat tells you, if you can see this screen, then you have successfully installed and started Tomcat. So basically, right now, we are up and running. We could, at this point, deploy the predictions web service, and we'll do that shortly. Now let me come back to my terminal and clear the screen for readability and just give you a very brief tour of the other subdirectories. So bin we've just seen. Bin you use to start up Tomcat and if needed, shut it down. Web apps over here is where we're going to put our websites and web services. More of that later. Logs. Logs contains an enormous amount of logging information by date, by source. The file you see over here to the left, Catalina out, is basically the catch-all. It's got everything in there. The only thing you have to remember about the logs directory is that occasionally you need to clean that thing out. So there are many nice utilities that will back that up for you if you like. Let me clear again, just to give you the sense. There's a subdirectory called conf. Here's the very good news. In Tomcat, the main configuration file is called server.xml. Mostly you can leave that alone. Where you might touch that, for example, is that if you wanted to enable HTTPS. And we'll talk about that when we do security. Out of the box, Tomcat supports HTTP connections, but not HTTPS connections. So bin, conf, logs, web apps are the main ones. The lib subdirectory that you see right here contains libraries. Normally speaking, you're just going to take what's in there and not add to it, but that's a fine point that we can revisit a bit later. For now, our main interest is bin. We need to get Tomcat up and running. And web apps, that's going to be the target for our websites and for us, in particular, web services. In this lesson, we're going to use the Ant build tool in order to deploy the predictions web service. So you're looking at the working file called ant.txt. I've got the URL for the ant tool on the second line. If you open a browser and just search for Apache Ant, you'll get a hit. There are various ways to install it, pretty straightforward. For example, I'm on a Mac. I used Mac ports to install. There's a Windows installer. There are installers for Linux and so on. For the particular Ant script that I'm going to provide, version 1.6 or higher is what's needed. The current version is 1.9. Once you've installed Ant, the way to check that it is properly installed is to open up a command line prompt and type ant -version. Now let me give a very quick summary of how ant works, and then we'll use it. When you type ant at the command line, it looks for a file called build.xml, which basically is a list of tasks that you want ant to perform. So for example, you might want ant to compile some files. You might want ant to place certain files in certain directories. In our case, we're going to ask ant to do all of that and then to build a jar file with a .war extension, WAR, web archive. So the easy way to deploy to Tomcat, or to Jetty for that matter, is to put the web service or the website in a WAR file and drop it into the web apps directory under Tomcat. In my particular case, if you come down here, the relevant command is ant -d. That capital D basically means I'm providing a command line argument. That argument is the name of the WAR file. So to take a simple example, if I give the name as hi, it's going to build hi.war and then deploy that file. So what I'd like to do now is switch from the Emacs editor to the command line so I can show you how this works. So first, let me show you Tomcat web apps. And as you can see right now, there's no WAR file in that directory. So what I'm going to do is move up. I've built a directory called test. Let me show you it. In test at the top level is build.xml. And at the same level, there's a subdirectory called src. That name is very important to me. If you now look at src, you'll see that in there, you have a subdirectory called predictions. We'll look at that in just a second. You've got my so-called database file, predictions.db. That's just a text file with all the predictions in it. There's my JSP script, and there's what Tomcat calls the deployment descriptor, web.xml. That's a configuration document. We'll look at the details later. Right now, I want to show you the predictions subdirectory under source. And in there, you can see I've got my prediction.java and predictions.java. Those are the two Java beans that support the JSP script. Now, what I'm going to do, this is our context. I'm going to type ant -d war name equals predictions. Any name would do, space, deploy. Cross your fingers, hope for the best. This went pretty quickly, and it tells me what it did. It did a clean, a prepare. Those details we'll worry about later. A compile, a deploy. The important thing is basically for us this last message. So it's told me that it has copied the built WAR file to the web apps directory. So let me clear the screen to make it a little more visible. And what I'm now going to do is confirm that the thing is deployed. Home, Tomcat 8, web apps. And what you'll notice is way over here to the right, you see predictions.war. What Tomcat has done is unwarred the file. Some people describe this as unpacking the WAR file. Basically, it's built a subdirectory called predictions, and it has unpacked the contents of the WAR file into predictions. Now let me show you what's in that WAR file. So I'm going to use the jar utility, standard with Java, tvf, T for table of contents, predictions.war. And what you can see is that the ant has done quite a bit. For example, this line, it has compiled the prediction.class file. It has compiled the predictions file. It has put the configuration file web.xml in the appropriate place. It has put my so-called database file under a subdirectory called data. Some of these placements are optional, some are mandatory. For example, the rules are basically this in Tomcat. If you have a .class file, it must occur someplace under webinf classes. In our case, it's webinf classes predictions, that's the package name, prediction.class, and so on. Now, let me clear the screen for readability, and let me go back to this directory where I did the deployment command. Over to the left, there's a build subdirectory. So essentially, what my script does is the following. It copies everything out of source into build, so I don't touch anything in the original source directory. This is for safety purposes. It then does all of the compilation, all of the building, and so forth in that build subdirectory, and then it constructs the war file that I told it to construct, predictions.war. It copies that over to web apps in Tomcat. If Tomcat thinks that the file looks reasonable, it will unwar it. In other words, it will create the subdirectory, in this case called predictions. So we can actually go back and look at that once again. So this is the result of unwarring. If you see that, it's reasonably good news. It means that Tomcat hasn't found any obvious problems and we're probably good to go. If you don't see that file, you know we've got a problem, and now we're into the logs subdirectory because we're going to look at the logging information. In future lessons, I'll go into more detail about how this deployment file works, but I do want to show you one last thing. So what I want to do is show you build.xml and just give you a heads up on what you need to change on your system. So I've got a very long comment at the top, which is basically a tutorial. It repeats many of the points that I've just made. But this is the critical line here. The very first part of my build.xml file specifies where you've installed Tomcat on your machine. So in my case, on this machine, it's users, Martin Kalin, Tomcat 8. You would put in whatever directory you installed. And if you're using Windows, by the way, you can use the forward slashes. You don't need to use the backward slashes. Okay, in summary, this is our first look at the Ant utility, how it facilitates the building of web services that we then deploy, in this case, to Tomcat. By the way, the same Ant is easily adapted to work with Jetty and other Java-based web servers. In this lesson, I'm going to suggest 2 short exercises to help review and consolidate what we've seen so far. What you see on the screen in my Emacs editor is one of the working files. It's called amend.txt, and the cursor right now is pointing at my web.xml file. So this is the so-called deployment descriptor. It's a configuration file. Technically, it's optional, but in production-grade services, you'd always have it. So my Ant script requires it, but an empty one will do very nicely right now. Now you'll recall that in this prediction service, the first code example, I had a JSP script. It's called predictions.jsp, and I had 2 back-end Java beans, basically 2 fairly straightforward .java classes. My choice of names, predictions.jsp, puts a bit of burden on the programmer. So, for example, when a client calls my service, as you see in this sample curl command, immediately after the 8080, the port number, you see /predictions. For Tomcat, that's always the name of the war file. The same, by the way, for Jetty. So the war file is predictions.war, so we have /predictions. Following that, you have /predictions.jsp, the name of my JSP script. What we'd like to do in the first exercise is get rid of that predictions.jsp. So to that end, the first exercise is quite simple. Rename predictions.jsp to index.jsp, which is a default name. rebuild the war file using the and script. And once that's done, you see down here now with the new curl, all we need after the port number is /predictions, because Tomcat will now look for either index.html, we don't have that, index.htm, we don't have that, or index.jsp, we do have that. So naming predictions.jsp to something else, in this case index.jsp, greatly simplifies on the client side. So it's a good idea. Now I'm going to review very briefly how the and script works, but let me first make a general point. Because you're already a Java programmer, you know about implementing application logic. That's not going to change in web services, of course. You're still going to do most of your work in the application logic area. The new part is the building of a deployable service, and so that's what we're emphasizing in these two exercises. The application logic basically is irrelevant. So let me go to a second document, very simple. This is in the working files as well. It's called bean.txt. And what I've done is taken my predictions.jsp and amended it. So at the top, you see this JSP use bean. That's also present in the predictions.jsp. The ID I use is called now. Any name would do. The change, of course, is here. Java.util.date is one of the standard classes in the Java distribution. Before, I was using a user-defined class called predictions. So all of these Java classes are eligible to be used as beans. By convention, of course, a Java bean is a class that implements properties with get-set methods. Date has those. It has, for example, getTime, setTime, things like that. But Date also has other methods that are not properties. Basically, with the object reference now defined up here, down here in my Java code, I can call any date method that I like on this object, referred to by NOW. So my suggestion is that in the second exercise, you do something like now get time or now toString to get a human readable version of the current time. And then you use the implicit object reference out together with println to send back a response. If you like, of course, you could format this as XML. It also could go back as plain text. That's not the big deal. The big deal is putting it all together, doing the packaging and the deployment to Tomcat. So let me do a quick review of how to do this. Pick any directory you like on your system. Let's call that the current working directory. Put my build.xml in the current working directory. Create a subdirectory called src. So the name is important. It has to be lowercase. Put the dummy web.xml in that directory, and also put your new JSP script in that directory. We already know it's easiest if you name that index.jsp. And then from the current working directory, here for review is the ant invocation. So it's ant -d, war name equals anything you like, deploy. And then for testing, once you've done that, the deployment on Tomcat's side should be instantaneous. I'm assuming, of course, that Tomcat is up and running. Curl localhost 8080/time. This should hit your index.jsp, and you should get back whatever message you send with the out.println. In this lesson, we're going to take a step back from the code, the predictions web service we've been looking at recently, in order to get some perspective on web services. In particular, I'd like to look at the two dominant flavors of web service out there right now. They both go by names, REST in the one case, SOAP in the other. Later on, we'll worry about exactly how the two are related. So this is our first look at these terms. As you can see, I've got a working file up on the screen in Emacs. It's called rest-soap.txt. It summarizes some important points. I'm not going to follow it in order. Instead, I'm going to focus on the part in the middle. First, though, let me say a few words about the acronyms. REST was coined by Roy Fielding in a PhD dissertation in 2000. It stands for Representational State Transfer, but it's come to have a completely independent meaning, I would say, nowadays, and Fielding is not altogether happy about that. But you know how these things happen in our field. The Rails framework has been extremely influential in determining how the term REST is now understood, and I'll refer to that point any number of times. The predictions web service that we looked at the last couple of lessons would be considered to be REST style. SOAP is quite different. SOAP is actually two things. It's a messaging protocol. It's typically built atop HTTP, but in principle, it could be built atop anything else. It's also an XML dialect. So for example, a SOAP document is XML, but it has its own distinct grammar and it has its own vocabulary. SOAP originally stood for Simple Object Access Protocol, but nowadays officially it doesn't stand for anything. So when I use the terms, I typically say REST-style web services or RESTful web services in order to underscore the informality of REST. SOAP-based web services, by contrast, follow the SOAP protocol and use the SOAP dialect of XML. Now let's look at the difference from a programmer's point of view, since that's the thing that interests us the most. So you can see I've got the cursor placed just to the left of REST, and I want to look at the conversation between the client and the service. So REST is very close to the HTTP metal. A client makes a request against a RESTful web service by sending one of the standard HTTP requests, a GET request, a POST request, a PUT request, a DELETE request, perhaps some other type of request as well. But the four you see there on the screen would be the dominant ones. The service, in turn, responds with an XML or a JSON or perhaps a plain text or perhaps even some other type of document. In principle, the service might respond with a binary payload, but this would be unusual, and I'd argue that web services are not ideally suited for that sort of payload. They can be used that way, but that's not really what they're best at. Now let's contrast that with SOAP. In a SOAP conversation, the client is going to send an HTTP POST request. Let me just allude to the reason now and get into more detail later. A POST request has a body. A GET request, for example, does not have a body. And in a SOAP conversation, a request is always a SOAP document. The response is also a SOAP document. So SOAP requests are POST requests, and embedded in the body of that HTTP request is a SOAP document. So it basically says, this is what the client would like. The service responds in turn, typically with a SOAP document. There has been some movement in SOAP so that now JSON is also supported, mostly in the .NET world, but to some extent in the Java world. It's also supported for response documents. Between the two, SOAP predates REST, and at one time it looked as if SOAP was going to be the dominant player. Rails, in its initial release, for example, had some limited support for SOAP, but quickly moved off of that to REST. Right now, it's fair to say, I think, that REST is the dominant approach to web services. All of the social networking websites, Tumblr, Twitter, Facebook, basically anything you can think of, they all support REST-style services and typically only REST-style services. Among the big commercial players, Amazon is the one that consistently provides both REST-style and SOAP-based services. In this lesson, we're going to focus on RESTful web services, in particular on how REST can be considered as an API. In front of you, you see in my Emacs editor yet again, one of the working files. This one is called rest.txt, and it does some summary points. I'd like to use this mostly as reference. I'm not going to go through it top to bottom, but I am going to start up at the top because the central concept, the core idea in RESTful services is the resource. And a resource is any informational item that has an identifier. So for example, I'm going to use the Acme company's product list, a fictitious company in our case, as the resource. 3 quick points about a resource. Quite obviously, the resource has to be hosted on some network machine that's accessible to clients. Typically, for example, a product list would be stored in a database. Those details don't matter to us so much. The important thing is that the host machine can be reached. So for example, it has an IP address, in this case, www.acme.com. Finally, for the very quick summary, any resource has various representations. In web services, we're interested typically in text representations, that is, in documents. But for example, Acme's product list could be represented by a movie, by a slideshow of images, and so on. Now, I'd like to turn to HTTP support for resources, but I'd like to do that by drawing parallels between how HTTP supports REST-style web services and how programming languages, in particular Java, supports the kind of things that you and I do as programmers. So for example, HTTP has so-called URIs, Uniform Resource Identifiers. These are the counterparts, for example, of variable names, class names, package names, and so on, the things that we're so familiar with in a language such as Java. In Java, of course, there are rules. So for example, if you have a package name in Java such as java.util.concurrent, the period is used as a separator. In the case of URIs, the slash is typically used as a separator, but you could also use a colon. There are various rules, various possibilities. So for example, our resource could be identified as /acme/products. URLs and so-called URNs, N for name, are subtypes of URIs. You and I, in our everyday business, mostly use URLs, but as we'll see later, a typical URL, although it is a URI, also includes a URI as a part, but we'll come back to that later. In all of programming, we're familiar with operations. So for example, some operations, arithmetic, comparison, that sort of thing, are relatively low level. There are fancier operations, sorting a tree, for example, that kind of thing. The counterparts of those operations in HTTP, these are operations on, of course, resources, named, identified resources. These are the so-called HTTP methods, nowadays commonly called verbs, because URIs are thought of as nouns. Now, among these operations in HTTP, 4 are particularly important because they cover the so-called CRUD operations: create, read, update, and delete. And what I have roughly in the middle of the document are examples. So you see, for example, post/acme/products. The 4 examples you see there are, by the way, basically the start lines of HTTP requests. So these start with the verb, then comes, if you like, the noun, the URI. By the way, some of the information, for example, the information needed to create a new product would be in the body of the post request. Similarly, if you look at the delete request, the ID of the particular product to delete would be included elsewhere in that request. Of interest to us right now is that we have HTTP methods that cover the basic CRUD operations, the counterpart of operations in a programming language. Now, in a language such as Java, we have explicit data types: int, float, double, char, string, that sort of thing. In HTTP, the so-called MIME types, multiple internet mail extension types, are used to type payloads, HTTP response payloads in particular. And you're familiar with these types. You've seen them often, I'm sure. For example, text/XML is one such type. Technically, text would be the type, XML would be the subtype, application would be the type, JSON would be the subtype. If you take all possible combinations of type and subtype, ones that make sense, you have in the ballpark of 4,000 MIME types. That's huge. Finally, HTTP supports status codes, which are a way for the client to be notified about how a request fared. So for example, if I send a GET request over to some website or web service, I hope I'm going to get back a status code of 201, which means OK. We're all familiar with the status code 404, which basically means the server couldn't find what we were requesting. And if you're a programmer, you've occasionally run into that 505, which is server error. Let me summarize. One of the reasons you can look at REST as an API for web services is that REST derives underlying support from HTTP. HTTP has identifiers, URIs. It has operations, which are the so-called HTTP methods. It has data types for payloads, and it has status codes to record how a given request fared. In this lesson, we're going to wrap up our overview of REST-style services. In particular, I'd like to highlight what's good and not so good about such services. Like everything else in computing, there are pluses and minuses, so I'd like to touch on those two topics. To begin, let's review the conversational pattern in a REST service. So I've got the cursor set in the working file, rest2.txt, to this line, and this depicts a request that goes from a client written in whatever language to a RESTful service written in whatever language. So the request consists of an HTTP verb-noun combination and perhaps an HTTP body. So let me clarify. A GET request in HTTP does not have a body. So basically, all of the information has to come in the so-called start line, which we've seen before. So in this case, get Acme products. This is a read request. And in the HTTP header. So for example, the HTTP header would specify the network address of the machine that hosted the desired resource. We don't have to get into the detail right now. An understanding of the concept is sufficient. By contrast, a POST request, in this case, create a new Acme order. The details of the order are going to be in the body of the POST request. A POST request always has a body, although technically the body could be empty. Now, in the other direction, coming back from the service, what we get is a status code plus a body. So an HTTP response always has a body. The body could, however, be empty. So for example, if everything went okay, we might get back a status code of 201. We might get an XML payload, a JSON payload, a plain text payload, a binary payload, and once again, the MIME data types would be used to specify what it was that we were getting. Now let me turn to the pluses and minuses. As noted earlier, all of the social networking sites, so for example, Facebook, Tumblr, Twitter, and so on, these all support REST-style web services, and that's no accident. If you're supporting a REST-style service, you're obligated, in effect, to send back information, typically in document form. And XML is extremely attractive if you're on the server side, because any modern database system can dump its tables, its views, and so forth as XML. So for example, if I want the Acme product list, and that product list is in a standard database, they can simply dump the table as an XML document, and I, the web service, just return that to the client. I'm going to summarize this by saying there's very little pain in a RESTful service on the service side. The client side represents, in effect, the pain point, in particular with XML. If I'm a client and I get back an XML document, I need to parse that document to extract the informational content. The problem is that there is no uniformity across the industry for the kind of XML I'm going to get. So in particular, the XML I would get from Facebook would differ from the XML I get from Yahoo, from eBay, from Twitter, from Tumblr, and so on. REST, again, is a state of mind, if you like. It's a style. It's not a protocol. It's not a standard. So on the client side, I'm confronted with the difficulty of parsing XML. The big exception to this rule is if I'm a JavaScript client and I'm receiving a JSON document, because a JSON document is the text representation of a JavaScript object. So for example, the document from Acme in JSON might be a list of products. If I'm a JavaScript client, I can convert that list straightforwardly into a JavaScript array and then process the array in the usual way. So I'm going to summarize this point by saying the real challenge in REST-style web services tends to be on the client side. So one of the things we'll look at over time is how to minimize that challenge. So what I'm doing in this slide is summarizing the points that we've hit so far. I'm depicting, for example, the conversational flow from the client to the service and from the service back to the client. I'm summarizing the CRUD operations, as you can see over on the left-hand side. And on the right-hand side, I talk a little bit about what one can expect in an HTTP response in a REST-style web service. In this lesson, we're going to round out our overview of web services by focusing on the pluses and minuses of SOAP-based services. To begin, what I'd like to do is to contrast client-service interaction in SOAP as opposed to REST. So to that end, you see on the screen in my Emacs editor the working file soapoverview.txt. What I've depicted right at the very top is basically the client-service interaction. So for example, from the client side, a request goes out to a SOAP-based service as a posted SOAP document. In other words, the HTTP verb is post. That's because a post request has a body. A GET request, for example, does not. And the SOAP document becomes the payload of the HTTP body. The service on the server side then does whatever processing is appropriate, and what the client gets in return is another SOAP document. So that SOAP document, the response document, is the body of the HTTP response. And then the client does whatever processing is appropriate. Now let's turn to the pluses and minuses. I've listed only one minus. You could spell this out in more detail, but for now, one is enough because this is the major minus. SOAP-based services compared to REST-based or REST-style services represent an additional layer of software. So I've depicted that down here. Let's say a client is going to send off to a service a list of products. That's the argument, if you like, passed in the request. And what the client wants to get back is a list of prices for those products. So what you can see in the depiction is that there's a SOAP library in play on both the request and the response side. So for example, the SOAP library is going to take that Java list of products, convert it into XML, send it over the wire to the service. The service is going to respond in XML, perhaps in JSON, but more commonly in SOAP and XML. And a SOAP library is then going to convert that XML into a Java list of prices. So what we have is added complexity. And in programming, added complexity is always a bit worrisome. There are, however, some considerable pluses that offset these minuses. For me, personally, the most important one is the first that I've listed. So in what I'm going to call routine exchanges, which should be the vast majority of exchanges between the client and the service, there's no need on the client side to parse any XML. Indeed, on the client side, the XML remains mostly transparent. The client code never sees it. Similarly, the client API is high level in the sense that the client simply calls functions. So for example, to get a list of prices for some products, the client might call a function called getProductPrices or something like that. So the web service calls tend to look just like ordinary function calls in whatever language you happen to be using. Finally, and this is another significant benefit, it seems to me, there are utilities to generate basic client code for service. This is because SOAP-based services come with a so-called service contract. It's called a WSDL document. We'll study it in detail later. And that document can be used with utilities to generate most of the boilerplate client-side code. This concludes then our first comparison and contrast of REST-style services with SOAP-based services. For the moment, our attention is on the REST-style ones, and what we're going to look at next are Java frameworks for doing REST-style services. In this lesson, we're going to focus on Java frameworks for REST-style services. Now recall from the overview of REST-style services that these services tend to stay close to the metal. By that I mean they like to make use of what underlying infrastructure, underlying technologies already provide. So for example, they use HTTP, and as we'll see later, HTTPS as APIs. They use what XML and JSON as document interchange technologies already provide. They tend to piggyback on hardware infrastructure, such as web servers, that sort of thing. So REST has a very stick close to the metal mentality about it, and the frameworks that support it have that same mentality, as we're going to see. The first code example that we looked at, the predictions web service, used JSP and some back-end POJOs. Let me remind you that at the technical level, a JSP script and related scripts are translated automatically into servlets before they execute. So a JSP script, you might say, is simply a means of generating a servlet automatically. It's the servlet code that actually executes. That's important because the first framework we're going to look at is the HTTPServlet. This has been around now for almost 2 decades. It's tried and true. It still deserves very serious attention, and it's the framework that we're going to start with. We'll use it to build a full CRUD-enabled version of the predictions service. The original prediction service supports only GET operations. The amended version will support all of the CRUD verbs: create, read, update, delete. Another framework that's gained a lot of popularity recently is called JAX-RS. The JAX stands for Java API for XML. The RS, of course, for RESTful Web Services. There are various implementations and extensions of the JAX-RS framework. One of these includes Metro, which is the reference implementation. It goes under the code name Jersey. So all of these names can be a bit confusing, but JAX-RS is the basic framework. Another framework worthy of attention is called Restlet. It's third-party. It actually predates JAX-RS. It's interoperable with JAX-RS. So for example, you could do a Restlet service but include JAX-RS code in it, and it's very, very similar in style. Now, these frameworks don't exhaust the possibilities. There are many other options. Some of you, for example, may be using Spring to do enterprise Java applications other than web services. Well, Spring, as you would expect, has support for web services as well. The choice of these three is to underscore 2 points, I think. These are tried and true, very basic frameworks in their own right, but they're also representative of other options. So in surveying these frameworks, we'll get a general sense of the options that are available in Java. In this lesson, we're going to focus on the HTTPServlet framework for doing REST-style services. To that end, I'd like to talk about what's attractive in this framework. I have the cursor in my Emacs editor. The working file, by the way, is servletframework.txt. I have my cursor pointing at the fully qualified name, so you can see it's javax.servlet.http.httpservlet. So let's get to the technical details that make this an attractive thing to use to write REST-style services. To begin, the HTTP servlet covers all of the CRUD verbs with the appropriate do methods. So you can see the list there. I have do get, do post, do put, do delete. And the idea is if the service receives a get request, then do get is called. If it receives a post request, do post is called. So the filtering of requests by verbs is done already. Furthermore, the HTTPServlet class follows the so-called adapter pattern or adapter idiom. By that I mean this class defines all of the do methods, but it gives them empty bodies. So effectively, in the HTTPServlet class, the do methods are no ops. So I've given two examples of do get and do post, and you can see the empty body. What's nice about this for me as a programmer, I can subclass HTTPServlet. Let's call that my HTTPServlet. And then I can override the do methods that I care about and ignore the others. So for example, if I care about do get, I can do my own override of that. If I don't care about do post, I just take the empty version that I inherit from my parent. Very straightforward, a familiar programming idiom in Java. There are some other points of interest, technical ones. Each of the do methods takes two arguments. The first is the HTTP servlet request. It's a map, as you might guess. It encapsulates everything that comes in the HTTP request. So whatever the client sends me, basically I get as a Java map that I can manipulate in the usual way. The second argument is the HTTP servlet response, and it contains an output stream that allows the servlet to write back to the client. So for example, if I'm going to send back some XML or JSON, plain text, whatever, I would use that output stream with the appropriate print or write method to send information back to the client. Furthermore, the HTTP servlet response class has very nice symbolic constants that cover the HTTP status codes. So I've listed three of them. You see SC underscore OK, that's 200. SC method not allowed, that's 403. SC not found, that's 404. A final point worth mentioning is this. Sometimes in RESTful services, you need access to the HTTP headers. So for example, cookies are stored in the HTTP header. There might be authentication information stored there, digital certificates, digital signatures, that sort of thing. In the HTTPServlet framework, I have full access to the HTTP headers, both on the incoming request and in the outgoing response. Now, what I'd like to do in the next lesson is start a revision of the original predictions service. That original service supported only get operations, in other words, read operations. I'd like to use the HTTP servlet to illustrate how we can expand that prediction service to cover all of the CRUD verbs. So for example, a client now can read all of the existing predictions all at once or one at a time. We'll add that feature. Can get back, for example, XML or JSON. We'll add that feature. Create a new prediction, add it to the list. We'll add that. Edit an existing prediction, delete an existing prediction. You're looking in my Emacs editor at the working file servlet.ws.txt. This summarizes the new version of the prediction service. For reference, I'll call this Predictions 2. It's a REST-style service, as was the original version, but this one uses an HTTP servlet and two back-end POJO classes. The two back-end classes are similar to the originals, but there have been some revisions. We'll get a look at that source code pretty quickly. The major changes are these. First, the revision supports all of the CRUD operations. So we can create new predictions, edit existing predictions, get a list of all of the predictions, or get a list that includes just a single prediction for inspection. Further, the response payloads can be in XML or JSON as proof of concept. Now the working files include predictions2.war, which is ready to deploy, but I'm going to redeploy it just by way of review. Finally, I've got some curl commands, a suite of 10 of them. I've put those in a Perl script to make it easy to run them. In the very worst case, you could run these curl commands independently to verify that the revised prediction service is doing what it's supposed to do. If you're on a Unix type machine, a Mac, a Linux machine, you have Perl. I've included here, as you can see, the URL for ActiveState, which has a very nice and free implementation of Perl for Windows. Here, in any case, is that Perl script I was talking about. The syntax is unimportant. The important thing is you can see in this little list, I've got some GET requests, POST requests, PUT requests, DELETE requests. I'm going to run this script after deploying the predictions2 service in order to confirm that the service does what we think it should do. And in this case, that means supporting the CRUD operations. To that end, let me open up a terminal window. And just by way of review, let me confirm that I've got my build script there. So I'm going to go ahead and deploy this service. So ant-d warname equals predictions2, and I'm going to ask that this be deployed to Tomcat. So the build takes just a second. You get confirmation that this is done. Now what I'm going to do is run these Perl tests. So Perl, and I've called the test curl test.pl. Oops, I thought I'd call it that. Curls test. Perl curls test.pl. Okay. So the very first test is going to do a get against the service, and we should see a list of all of the predictions in XML. I hit return, and you see basically the end of that list. So for example, Hiram down here is the last predictor, and this silliness up above is what Hiram predicts for e-business. I hit return. The next command is going to confirm that I can do a get on a given request. So instead of reading all of them, I can read one at a time if I so choose. And here you can see you've got a prediction from Devin. We've seen him before. And up above, balance, clear thinking, blah, 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 is Devin's prediction. So I'm highlighting it just for emphasis. I'm going to do the same thing now, but get JSON payloads instead of XML. So just to confirm that the service does that, you can see simply by eyeballing that this is JavaScript object notation, not XML. I can do it for all predictions or for a single prediction. So here's the prediction with ID 11. This is from Lenny Fink, and up here in JSON format is yet another of these predictions. This is now a big one. So this is a post request. This is a request in effect to add a new prediction to the list. So I've taken a line from a T.S. Eliot poem. We're going to run this one. I get back a very simple XML document confirming that the prediction has been added. But just to make sure, we're going to do a read all request once more. And you can see down here at the bottom, the predictor is T.S. Eliot, and the prediction is the one we just added to the list. So the post command works. I'm now going to do a put. So I'm going to edit the prediction that I've just added. And I got a confirmation that prediction 33 has been edited. Again, we're going to get a list of all of them to confirm. And you can see down here that the editing has indeed taken place. The final CRUD operation, of course, is the delete. So we're going to delete the prediction that was just created. I hit return. I get a confirmation that the prediction has been removed. Just to make sure, we'll do yet another get all. And you can see we're back to the original list with the prediction from Hiram being the very last one. And that basically concludes the script. So what we've done in this lesson is a very brief overview of what predictions2 is going to look like. I've run some tests against it to confirm that the service really does support the CRUD operations. You're looking in my Emacs editor at another working file. This is called servletoverview.txt. It summarizes the code modules that are at work in this revision of the predictions web service. So again, this is a REST-style web service. It differs from the original in that it supports all of the CRUD operations, and it also can return either XML or optionally JSON responses. So we'll get into those details when we look at the appropriate code. What I'd like to do now is just quickly go through the three main source modules and then focus a little bit on one of them. So the first is prediction.java. This is a standard Java bean. It's got three properties: who, what, and ID. We'll look at that code momentarily. I'm going to jump over the middle one for now and jump down to predictions-servlet.java. This is the servlet that implements the CRUD operations by defining do post, create, do get, read, do put, update, and do delete, which is delete. As noted, this version of the prediction service can return XML, that's the default, or JSON upon request. Now let me focus a little bit on the middle module, which is basically a utility class. So it contains some properties, but the main thing we care about are two fields. It has a concurrent map, so it has a map of all of the predictions. The key for a lookup is the prediction ID, and the value is the full prediction, who said what. There's also an atomic integer, which provides the keys. So the keys are unique numeric values, very much akin to what you would see in a database. Both of these classes, very important, come from java.util.concurrent and its subpackages. Technically, concurrent map, by the way, is an interface. The implementation I'm using is the concurrent hash map. So the question basically is why. So consider this situation. Suppose we have two clients that hit the service at the same time. One of them wants to update prediction 32. The other one wants to delete that same prediction. Clearly, we can't let this happen. We have to have some coordination. So these two requests have to be serialized in some appropriate way. One has to come before the other. And for example, if the updater is at work, we can't let the deleter get at the prediction at all. Now let me put this in more technical terms. Java-based web servers, such as Tomcat and Jetty, implement what is sometimes called the one thread per request model. That is, as a request comes into the web server turns that request over to a thread taken out of a pre-built pool. The pool of threads is pre-built for efficiency reasons. That thread is then responsible for handling the request from start to finish. So what we have here then in this application is the classic thread synchronization problem in Java. There are many different ways it could be handled. I'm going to handle it in a fairly high-level way. The concurrent hash map and the atomic integer are both thread safe. So the thread synchronization is baked into those data types. So that's why I've picked them. There's one and only one concurrent map. It contains all the predictions. And basically, I'm letting the concurrent map implementation make sure that one client can't edit the same prediction that another client is deleting at the same time. Now, what I'd like to do is take a very brief look at prediction.java, the first of these Java beans, since it's the simplest piece of code, and then we'll go on to the other two modules. So let me bring up another working file. This is called servlet wscode1.txt. And as you can see up here, it's the prediction class slightly changed from the original implementation, and the change is here at the end. The class now implements the comparable interface, and the implementation is down here. There's a method called compareTo. This basically supports ascending sorts. So let me give you the bottom line. It'll be convenient to have the predictions always in sorted order, so that, for example, if you add a new prediction, it'll be shown at the end of the list. If you delete a prediction, it'll be easy to spot where it should have been and no longer is. So I'm going to use sorting mostly to help with the testing. When we looked at the curl commands last time, if you run those again, you'll see that everything is always presented in sorted order by prediction ID. Beyond that, this version is pretty much the same as the previous one. That is, there are three properties. There's a who, that's who makes the prediction. You see that at line 2. There's a what at line 3. That's the prediction itself. And then there's the ID, which is the unique identifier, and also the lookup key basically for a given prediction. In this lesson, we're going to look at the second backend Java bean for the rewrite of the prediction service. You see the code. It's in a working file called servlet wscode2.txt. You can see it's a standard POJO class, public class predictions. That's it. The really important parts are the three fields that you see at the top, lines 1, 2, and 3. The concurrent map, as mentioned yesterday, holds all of the predictions. In effect, this is our in-memory data store. We need it to be thread safe because, for example, two clients against the service might try at the same time to edit the same prediction. And of course, we can't let that happen. The concurrent map imposes the required synchronization, so it would prevent that from happening. The concurrent map is attractive because it's efficient. For example, it would allow one client to edit prediction 27 and another client to edit prediction 11. They could do that concurrently because they wouldn't be stepping on the same prediction. The atomic integer right below provides the lookup keys for the map. And again, we need to ensure that this is thread safe. So for example, two clients might try simultaneously to create new predictions. We have to ensure that those predictions get different IDs. And the atomic integer provides that required thread synchronization. The servlet context is a behind-the-scenes thing. It's needed, very important. It's basically the way the application talks to Tomcat. In this particular case, recall that the data for the predictions comes from a text file that's encapsulated inside the WAR file. It's the servlet context that allows the application to read from that file. So the code is a little bit grimy. It can stay behind the scenes. It doesn't really tell us anything essential about the web service. The constructor does pretty much what you'd expect. As you can see, it creates an empty concurrent hash map, and then it creates an atomic integer, which is going to generate the lookup keys. I want to jump now to the bottom of this file and review 2XML. This is unchanged from the earlier example of predictions, and it uses the tried and true XML encoder. Eventually, we'll generate more sophisticated XML, but for now, this is good enough. Finally, down here at line 5, there's a utility method called addPrediction. So the servlet that we're going to look at next would create a new prediction in a doPost call, and that prediction now needs to be added to the collection, and it's done in this little utility method. The rest of the predictions code we don't have to examine because, as I noted, it doesn't really add any essential knowledge to how the service works. The really important code for understanding the service we'll look at next. So this is yet another working file. It's called servlet wscode3.txt. And as you can see, I'm moving the cursor. This is our servlet. So I'm calling this the predictions servlet. It extends the HTTPServlet. There's a bunch of overrides. Some of them are more important than others. Let me just say a very quick word about line 1, the override of a init. A init is called by the servlet container once the servlet has been loaded into the container. So this is where in a servlet you would do constructor-like code. In this case, we create a new predictions instance. We just saw that utility class. And we also set the servlet context so that that predictions instance can then read the data file. Now, I'm going to pass over the rest of this code pretty quickly just so we can eyeball it this first time. We'll study it next time. So you can see there's the do get. The logic is a little complicated. More on that later. There's the do post. I've removed for this session the do delete and the do put, but they're there. The one that I want to focus on now is at line 14. You see do trace. In addition to the CRUD verbs, HTTP supports various other verbs. Trace is one of them. Options is another one. Headers is another one. And our web service isn't going to support any of these verbs, so we need a way to handle requests that might come in with those verbs. So the strategy is straightforward. Basically, what the code does is it throws an HTTP exception. That's a special type of runtime exception. And it uses one of these symbolic constants. In this case, this is method not allowed, 403 at the HTTP level. There's also a utility function down here called send response. And what I'd like to show you is how easy it is to generate JSON if requested. So the idea is this. Send response is called by do get, do post, do delete, do put, in order to send something back to the requesting client. And the client, in a do get request, can get either an XML payload, that would be the default, or a JSON payload if the client so desires. So to handle the JSON case, which is a special case, there is a Boolean argument in send response. If set to true, we're going to return JSON, otherwise XML. So I'm using a very lightweight JSON library. It's a simple jar file that's encapsulated in my WAR file, very small. And you can see the line here, XML to JSON object. The payload is just the XML string. So this just takes an XML string, converts it to a JSON string. Once that's done, we reduce that string to a byte stream. We're dealing with networking. What's going over the wires are going to be bytes. So we get the output stream, we take the payload, we write it out as a bunch of bytes, we flush the stream, we have now sent our response back to the client. In this lesson, we're going to look at the CRUD operations and the servlet implementation of the predictions web service. So you're looking at the working file servlet wscode3.txt. We looked at this briefly in the last lesson. This time the focus is going to be on two of the do methods. The first is do get and the second is do post. We can look at only two because this will give us a good feel for how the other two, the put and the delete, work. So for example, do post is used to create a brand new prediction from scratch. Do put is used to edit an already existing prediction. The underlying logic is quite close. Do get, as you can see here on the screen at lines 2 and 3 in the documentation, do get can be hit by a client in two ways. The first is with the URI /predictions2. That's interpreted to mean get all. In other words, send me back a complete list of the predictions. And the second form, get predictions2 query string ID equals 1, specifies a single prediction by its ID, and that will be sent back to the client. If you look at this second line, line 3 in the documentation, if you change that get to a delete, effectively you have the same logic. So all a delete does is to remove a given prediction from the hash map. Now, let's look at the details of do get. So in terms of the service logic, we have to distinguish between get all, read all if you like, and get one, and that's done at line 5. Request is the first argument to the do get method. Again, it's a map that encapsulates all of the information sent in the HTTP request. So we call get parameter with ID to see if there is such a parameter. The basic idea is this. If there is an ID parameter, we're dealing with get one. If not, we're dealing with get all. Furthermore, down here at line 6, we go into the HTTP header and look for an accept key value pair. So for example, if the client wants a JSON payload, then what the client puts into the HTTP request header is accept : application/JSON or the equivalent. If you go back and review the Perl script that runs those curls command, you can see how this is done at the curl level. In any case, on this side, the server side, we just want to see if there is an accept key value pair in the HTTP header. We then want to check to see if it contains JSON, literally. If it does, we assume that the client wants JSON, otherwise the client will get the default, which is XML. Now the logic continues in a fairly straightforward way. If there is no lookup key, which is basically the ID, then we assume that what the user wants is all. So we go into the predictions object, we get a reference to the concurrent map, we grab the values, change those into an array, and for readability, we sort that array. Finally, we generate an XML document, that's the default, and then we call send response, which we looked at last time. All send response is going to do is to take that document, it's called XML here, if needed, convert it to JSON, and send either the XML or the JSON as a byte stream back to the client. Now, the more complicated do-get is actually the second one. We had to extract the ID. We now basically do a lookup in the map to get the prediction with that ID. It's possible, of course, that we got a bad ID. For example, there is no prediction 4257. If a client requests that, we're going to send back, in effect, an error document. Otherwise, we're going to send back the requested document representing that prediction. Now let's take a look at do-post, which is actually simpler than do-get. So the way you hit do-post is up here at line 9. There's a post request, that's the verb, and the URI is /predictions2. The information for the new prediction is going to be in the body of the HTTP request, and it should consist of two parts: a who, the maker of the prediction, and a what, the prediction itself. So the first thing that do-post does is it tries to extract those two. So you see at line 10, get parameter who, at line 11, get parameter what. Very straightforward. If either one of those is null, we have a bad request. So we throw an HTTP exception with bad request as the status code. Otherwise, it's smooth sailing. Create a new prediction. That's that very simple Java bean with who, what, and ID properties. So that's easy to do. We set the who, we set the what, and then we call add prediction. It's add prediction that adds the ID to the newly created prediction. We get a copy of that ID so that we can send a confirmation back to the client saying that a new prediction with ID 47, whatever the number happens to be, has been created. And then we send this response back to the client. This confirmation response, by the way, is always sent back as XML. We never send back JSON for this particular case, although this would be relatively easy to change. In this lesson, we're going to review the servlet-based implementation of the prediction service. It's a REST-style service, of course. And to that end, you're looking at one of the working files. It's called servletreview.txt, and you're seeing it in my Emacs editor. So let me begin with a very quick code review. The servlet implementation has three classes, the simplest of which is prediction.java. That's just a straightforward Java bean with three properties. An instance of a prediction.java represents a single prediction, of course. A bit more complicated is predictions.java. This basically is where the sausage is being made. So this is a utility class it does the sort of low-level, grimy work that has to be done. So, for example, it reads the data out of a text file that's embedded in the WAR file, predictions.db. It reads those predictions into the Java data structure. So most of that code is utility code. The centerpiece, and this is also high level, is PredictionsServlet. This, in web service jargon, is the HTTP endpoint, which emphasizes that every incoming request hits this servlet instance. So, the features of the servlet that deserve review are the following. First, the servlet supports the 4 CRUD operations. So, post to create, get to read, put to edit, delete to delete. And as a further measure, the servlet explicitly rejects any other type of HTTP request. So, for example, trace and options are 2 other HTTP verbs. Should a client send a request with one of those verbs, the client is going to get a method not allowed error. Finally, this is a foretaste of what we'll see in the JAX-RS and Restlet implementations. The GET requests in the servlet allow 2 different types of response document. By default, the requester gets an XML response, but if the requester so desires, the requester can get a JSON document instead. And we'll be spending more and more time on JSON documents. Now, one feature of the servlet is a bit tricky, and that's the thread synchronization. So let me review that very quickly. Tomcat and Jetty follow the so-called one thread per request model. So an incoming client request is handed off to a separate thread for execution. So far, so good. The problem is that there is a single instance of the central data structure, the lookup table, that holds all of the predictions. So we can't allow a condition such as this. We can't allow 2 incoming clients, for example, to edit the very same prediction at the very same time. So we need to coordinate or synchronize those threads. Java has some wonderful data types for doing that. One of those, I'll highlight it here, deserves a little emphasis, is the concurrent hash map, which bakes the synchronization into its access methods. The concurrent hash map is also highly efficient. It's really a very well-designed type. The other synchronization construct is the atomic integer. Let me highlight that as well. The atomic integer ensures that every prediction is going to have its own unique ID value. Those values are generated from the atomic integer. Now, the predictions2 WAR file is available among the working files. For convenience, it also contains all of the source code. So if you'd like to tinker with that source code and then redeploy, you have the source code in the predictions2.war file. And of course, you can use the ant script to automate the redeployment. You're looking in my Emacs editor at one of the working files called servletexercise.txt. So it's a short programming exercise. The intent is to give you a chance to play a little bit with the predictions2 web service. So let me get right to the main part. If you look at the servlet code, there are, of course, the do post, the do put, the do delete, but of particular interest to us, the do get method. And this is the request handler. The do get implementation is a little bit tricky because there are 2 decision points. The first is this. The code needs to determine whether the incoming get request is a request to read all predictions or to read a single prediction. And in the case of a single prediction, the prediction ID is provided as part of the query string. This is because a GET request doesn't have a body. Our interest is in the second decision point. That decision point is about whether to send the requester the default document type, that's XML, or to send a JSON document instead. So here's a quick review of the relevant logic. There's a local variable called JSON, initialized to false. So as you can see, the type is Boolean. We then use the very convenient request data structure. It's a map to get the header to see if there is an accept key in the HTTP header. So again, the Servlet API gives us access basically to all parts of the incoming HTTP request. If there is such a header, in other words, the client has put it in, and in one of the test curl scripts, and in fact in 2 of them, I do that. If there is an accept header, then we check to see if it contains the keyword JSON. If it does, we assume that the client wants a JSON document, and we respond accordingly. Now, the exercise basically is to enhance this flexibility by first doing this in a slightly different way, and second, by giving the client the option of getting back plain text. So a GET request could now send back 3 different types of payload: XML, that could remain the default, JSON, or plain text. So here's the idea. If you come down to these sample GET requests, you see get/predictions2. That would be understood as read all, and the return document would be XML. The second example, get predictions, and here comes the query string, $ID equals 12. This would send back a single prediction. Again, the default document type XML would be used. Third example would send back all of the requests in JSON. So this would be an alternative to the current implementation. We wouldn't check the header. Instead, we would check the query string. And the code above shows how you would extract this. The fourth example does the same thing, but for a single prediction, sticking with 12. The suggested change to the code would now be to support plain text as one of the MIME types. So you would do that with something like query string type equals plain. That would be, again, read all, or type equals plain and ID equals 12. That would pick up a specified prediction and send it back as plain text. It's a fairly straightforward exercise. It will come into play in the next lesson when we start to look at JAX-RS. In this lesson, we're going to take our first look at the JAX-RS framework. JAX-RS, again, stands for Java API for XML, RESTful Services. It's become very popular in the past few years, and there are various implementations. I'll talk about those in a bit. To begin, we're going to look at one of the working files. This is called JAX-RS overview.txt, and it shows how JAX-RS differs from the straight servlet implementation we considered earlier. The basic difference you can see in this little depiction. So a client request comes in, and it hits a specially provided JAX-RS servlet. This servlet is designed precisely for a web server such as Tomcat or Jetty. The JAX-RS servlet then takes the incoming request and dispatches it to the application. And this application I'm going to call predictions 3. The same point could be made more technically. What you're looking at here, and I'm going to highlight something in roughly the middle of the screen, you're looking at the web.xml configuration file that is used for the predictions 3 service. And the line you see, servlet class is the XML tag, specifies com.sun.jersey, blah, 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 .servlet container as the servlet to hit. In other words, this is the official name for this JAX-RS servlet up above. This pattern is sometimes described as the interceptor pattern. So a request goes to a servlet. The servlet then passes off the request to the appropriate application. And we'll look at this in some detail a bit later. I'd like to highlight now another feature. The predictions 3 WAR file, which is available in the working files, has a lot of embedded jar files. Those jar files represent software libraries, and they bring up an interesting issue in doing web services. So as I've depicted the issue here, I call it to freeze or not to freeze the WAR file. So let me explain the difference. Freezing the WAR file means taking all of those jar files and embedding them inside the deployed WAR file. The main point for doing this is to avoid any sort of dependency issues, in particular, any sort of version control issues. The downside of this approach is that it makes the WAR file a little bit bigger because you've got these nested jar files. The alternative is to take those jar files and to copy them, for example, in the case of Tomcat, into Tomcat home/lib. That's where Tomcat libraries are stored. They're all jar files. If you take that approach, you have to restart Tomcat. The good news here is that those jar files would be shared across applications. I must say that my own preference is for the freezing. This makes production level deployment much easier. I can, for example, develop on one machine, take the WAR file, move it to a staging machine, move it from the staging machine to the production machine, and all of the dependencies are inside the WAR file. So I must say I like this approach quite a bit. Now, there are various JAX-RS implementations. We're going to use one called Jersey. It's the reference implementation. You can see I've provided the URL at the end. It's a good implementation, but there are other good implementations as well. Before wrapping up, what I'd like to do now is to run a little test. Again, I'm going to use a Perl script, and this Perl script is quite similar to the previous one. Let me bring up a terminal window here on my Mac. This is called curls test rs.pl, and it's going to illustrate some of the functionality in the Predictions 3 service. So let's give it a run and hope all goes well. The first sample curl request I'm showing is a request for XML. This is at the end of the URL. So basically what I'm asking for here is an XML document that represents prediction 12. I hit return, and you can see I've not formatted the XML in any particular way. It is basically the way it's delivered, no indentation and so forth, but you can recognize one of the predictions. The next one is I'm going to ask for XML/foo. This should not work because I expect a number at the end, and foo is quite definitely not that. And what I get back is a long error message. Basically, the gist of it is right here, HTTP status 404 not found. So my application rejects this. In a bit, we'll see how it does that. Now I'm going to ask for all of the predictions, but in JSON. This is quite a screen full. We don't want to try to read this. No indentation, but just by eyeballing it, you can see that we're getting back all of the predictions. Then finally, we're going to do the same thing, but we're going to request plain text. So you can see that in the curl URL. And here we get them nicely numbered. I'm going to use the plain text quite a bit because it's easy to confirm that creations of new predictions, editing of existing predictions, and so forth have worked. So to that end, we're going to do a post request, add a new prediction. We get a confirmation that that's been done. Just to be sure, we basically ask to see them all yet again. And as you can see down at the bottom, prediction 33, this is the one that was just added. Now we're going to delete that. This is the curl URL up at that first line, and we get a confirmation that it's been done. Just to be sure, we're going to look at all of them yet again. And as you can confirm down here at the bottom, the last prediction is number 32. It's that familiar prediction by now from Hiram. So the Predictions 3 service, like the Predictions 2 service, supports all of the CRUD verbs, but it's a little richer in its data typing. The response document can be JSON, XML, or plain text, and we have a slightly different form of requesting URLs. In this lesson, we're going to start out by looking at RESTful Routing, which is widely used across frameworks for REST-style web services. We're interested in particular in the JAX-RS and Restlet frameworks, which we're going to be looking at shortly. So RESTful routing is a good place to start. Let me begin with a shout out to the Rails community. The Rails framework really pioneered and popularized a lot of the work in this area, and now everybody is pretty much on board. So you find so-called RESTful routing used in Java, in Python, and C++, and so on. The core idea is pretty straightforward. So what you see in this working file called restful.txt are 4 examples. And these examples essentially are the start line from HTTP requests. So you see the first one, get/predictions, verb, noun. The noun, of course, is the URI. The verb is the standard HTTP method. That combination maps to do/get. Changing the verb from get to post, but keeping the URI, takes us to a different function, in this case, do/post instead of do/get. And then there are 2 further examples. These, in effect, are parameterized. The 27 represents the ID of a particular prediction. So with the get request, it's a request to read prediction 27. With the delete verb, it's a request to delete that prediction. So the verb and the noun together are, if you like, equal partners. It's not just the URI, it's the combination of verb and URI. Now, what does differ across frameworks is exactly how the RESTful routing is implemented. And in JAX-RS in particular, annotations are widely used. So for example, there are annotations such as @get, @post, @put, @delete. Pretty much what you'd expect. There also are further annotations. An example is down here. So you see @produces. This allows you to specify the document type that will be returned in response to the request. So in this particular example, you can see that it's going to be a JSON document. By the way, the name of the method down here, I call this getJSON. That's arbitrary. You could call it getABC or anything you like. Let me touch on one last point in this working file. You see down at the end, this is a pseudocode representation of what these RESTful frameworks are able to do. So you see get predictions / and then instead of a number such as 27, there's a placeholder, in this case ID, and then there's a regular expression, in this case an expression that requires 1 or more decimal digits. The important point here is that frameworks such as Restlet and JAX-RS make it possible to hand over basic data validation to the framework. And this is one of the features that's most attractive, I think, about these frameworks. Now let me move on to a second working file. This is called JAX-RS-style.txt. And I'd like to illustrate very quickly how you get RESTful routing in this framework. So as you can see here in the first example, there are 3 annotations, @get, @produces, @path. By the way, these could come in any order, but I've started with the verb. I've put produces in the middle and path at the end, but whatever style you prefer, it's easily done. The @get, of course, specifies the verb. The @path specifies the noun, the URI, and the produces is, as we'll see later, more a promise than a guarantee. So basically, I'm promising that JSON will be returned, but I have to do something to make sure that that happens. The second example of interest is the @path annotation. This illustrates the actual syntax for regular expression data verification. So in this case, you see that //d+. The /d+ is actually the regex expression, and it means 1 or more decimal integers. And then you see the @path param down here. I've put the cursor over the @. That indicates that the name of the placeholder is ID. So the name of the placeholder is arbitrary. It doesn't have to be ID. And there's a little review of basically what I've just covered. Now let me make one final point in this brief overview. JAX-RS allows us to automate the return of both XML documents and, where appropriate, JSON documents. What I've done in my example is to take the automatic generation of XML, but not the automatic generation of JSON. I'll get into the reasons later, but I'd like to indicate at this point that you can turn over a lot of the tasks: data validation, routing, XML and JSON payload generation. You can turn these over to frameworks such as JAX-RS and Restlet. In this lesson, we're going to do an overview, a quick survey of the source files that make up the JAX-RS prediction service. For reference, again, I'm going to call this the predictions 3 service. To that end, you're looking at one of the working files, JAX-RS code overview.txt. So let me start with the overview. Some of the classes are by now quite familiar. The first, prediction.java, is the Java bean with 3 properties: ID, who, and what. There are 2 differences worth noting. The first is that the get methods in this class are annotated with @XML-element. This is a standard Java annotation. We'll look at it in some detail later. The important point right now is that this annotation prompts JAX-RS to automatically generate an XML representation of a given prediction. So that's very useful. I don't have to use XML encoder or the like to generate the XML. JAX-RS is going to take that task over for me. There's also an override of the toString method, because the predictions 3 service is going to support plain text representations of predictions, and toString is a natural way to provide such a representation in Java. The second Java bean class I've renamed to predictions list in order to underscore that this is indeed a list. This class too contains the @XML-element annotation, and for the same purpose, to enable JAX-RS to do the XML generation automatically. The list part refers to this thread-safe data type in Java, copy on write array list. I could have used a thread-safe map as before, but I wanted to highlight the options that Java provides for thread safety. The atomic integer, by the way, once again ensures that each prediction gets a unique ID. In this class too, the toString method is overridden to provide a text representation of the entire list. The class that we'll spend the most time on is predictions rs.java. The RS, of course, is for RESTful Service. And this is the class that contains the very many, very readable, very nice JAX-RS annotation: @get, @path, @produces, and so on. This class supports all of the CRUD verbs. It provides 2 versions of get per representation type. By that I mean there are 2 versions of get to return XML, 2 to return JSON, 2 to return plain text. The 2 versions in each case are get all, in effect, the whole list, and get one, where one is specified by a particular ID. The last class is special purpose. In this case, it's called RESTful Prediction.java. Any class will do, and we're going to take a quick look at it because that's the best way, I think, to explain why it's needed. So we're now looking at another one of the working files. This is also one of the implementation files, RESTful Prediction.java. So let me start at line 1 with this first annotation, @application path /resources p. So the idea is this: in a JAX-RS WAR file, you can have many different applications. In our case, there's only one, but we could have 2, 3, 4, as many as we like, and each of those applications would be distinguished within JAX-RS by its own URI. So the URI that I'm using here is /resources p. We could simplify this simply to / because we have only one. This particular class, whatever it's named, so I call it RESTful Prediction, extends application, and application is up here. It's basically part of the JAX-RS core. Now here's the idea. We need to override something called get classes, and in this particular case, The heart of the override is this line, set add. Set is this hash set. Predictions rs.class, that's basically our RESTful service. If we had multiple applications, we would have multiple set.adds. Basically what we're doing is this. We're providing a list of applications for that JAX-RS servlet that is going to take all of the incoming requests for a WAR file and then pass those requests on to the appropriate application. So if you like, this resource prediction class is part of the glue that connects the JAX-RS service to the special purpose servlet that's used in Tomcat. It's not something that needs to be studied in much depth. We won't look at it again. It's just important to understand how the whole thing is glued together. A request comes in, hits the JAX-RS servlet. The JAX-RS servlet then knows about the various services that it's supposed to manage. In this lesson, we're going to look at the centerpiece of a JAX-RS service. And that centerpiece is a POJO class. You can see it here. So I'm in the working file, predictionsrs.java. That's the name of the class. And immediately above it, at line 1, is a path annotation. So let me explain that right to begin. When this application is deployed, it's deployed, of course, in a WAR file, as usual. And in this case, the WAR file is called predictions3.war. That's also included among the working files. The path annotation at line 1 basically means that the URL that ends /predictions3/, so the second slash is that slash right there, will get you to this class, predictions RS, the POJO class. So it's intuitive. What you're going to see, for example, if you just look ahead to line 4, you'll see for the method called getXML, there's an additional path annotation that is /XML. The meaning, again, is intuitive. /predictions3/XML gets you into this class, predictions RS, and to this method, getXML. So basically, the path annotations are an intuitive way to show what the navigation is going to be. Let me return briefly to line 2. In previous versions of this service, I've had to set the servlet context. Let me just remind you that setting that context was necessary so that the application could read the data from predictions.db, the text file that's encapsulated in the WAR file. JAX-RS adds a nice touch. They support so-called dependency injection with the annotation called @context. So by annotating this identifier, SCTX, of course for servlet context, I turn the task of initializing that identifier, that field, to the JAX-RS runtime. I don't have to do it myself. It's a small touch, but it's a nice touch. Okay, let me return now to the various CRUD operations. All of them are annotated, for example, @get at line 3, and then @path. So basically this is the verb, and then the noun, if you like. @produces is used to specify what the response document type will be. In this case, it's XML. Another nice feature of JAX-RS is that it automatically handles the generation of XML. I don't have to do anything except make sure that there's an appropriate library. In this case, the appropriate library is JSON. Down here, at this particular line, the return line, you can see that there is a response type. That's a JAX-RS type. There's an OK method that will set, as you would guess, the status code to 200. I feed that the predictions list, specify the type that I'd like, XML in this case, and basically ask JAX-RS to build that for me. Very straightforward, and as you're going to see, all of the CRUD handlers work essentially the same way. Down at line 7, there's an additional feature I'd like to review. This time in the path annotation, we have /XML, that part we've seen before, followed by, in braces, ID:,
And the important part here is this is a regular expression for data validation. So the idea is straightforward. Suppose a client hits this service with /XML/27. The regular expression here, which basically says one or more decimal integers, this regular expression will ensure that there's at least one decimal integer, in this case 27. So this is going to go through. If, by contrast, a client were to say /XML/foo, that would fail the regular expression validation, and the client would receive a 404 error. All of this, again, is done automatically. So the data validation is a particularly attractive feature of JAX-RS. At line 8, I show basically the same thing for JSON instead of XML. So you see here the same regular expression as above. Now let's look at the post verb. This one is particularly important because it allows a user to create a new prediction. So it's at post, as you'd expect, produces text plain. Basically, that's the confirmation. And down here for the path /create. Now this next part is particularly nice. You see there are two annotations called @form_param, one for who and one for what. Basically, this tells the JAX-RS runtime to go into the body of the post request, to look for the keys named who and what, and to extract those values and to assign them to the parameters who and what. Very convenient, very high level. The rest of this then is pretty straightforward. For example, down here, should the user send a post request in which either who or what is missing, we can return on the fly basically a bad request. Otherwise, we create a new prediction, we create a message, that's the confirmation message basically, and then send back that response. At line 10, you can see there is the @delete verb and the usual sort of logic you would expect. Let me wind up with one last note. We're looking here at line 11 at a method called toJSON. If we wanted, we could let JAX-RS automatically generate JSON as well as XML. The problem is that this would impose a little bit of a burden on the client. The client would have to tinker with the HTTP request headers by injecting into those headers the desired data type. So in this case, application/JSON. The code to generate the JSON is straightforward. It's basically this line, which uses the Jackson libraries, object mapper, write value as string. So this takes a given prediction, turns it into a JSON document, which is then sent back to the client. So in my design, I decided not to automate the generation of the JSON, but rather to do it myself because it's so straightforward. So let me summarize. The centerpiece of a JAX-RS service is a heavily annotated class of the type that you've just seen. JAX-RS undertakes the automatic generation of XML and, if you desire, of JSON as well. It supports dependency injection in a very nice way. And even nicer, as far as I'm concerned, it supports data validation with regular expressions. In this lesson, we're going to look at the Restlet framework. We're doing REST-style web services. The service changes. We're not going to do predictions this time. The new service is a bit simpler. It's called adages, and an adage is just a saying such as, "The limits of my language are the limits of my world." And the application comes with about a half a dozen adages already built in. The application supports the full CRUD verbs, so you can create new adages, edit existing ones, and so forth. The working file is adages.war. It's ready to deploy. It also contains all of the source code. The working file you're looking at right now, this overview, is called restlet.txt. If you deploy a Restlet service to Tomcat or Jetty, there's an interceptor servlet that comes into play, just as with JAX-RS. In effect, this servlet acts as the container for the services that you and I write. So in the case of the adages service, a request comes in from a client. hits the Restlet server servlet. You can see that here. I'll bring the cursor over for reference. And the server servlet then dispatches that request to the appropriate code. The Restlet service is going to look familiar with respect to the annotations. So there's @get, @post. The difference is that they are capitalized, but they're not all uppercase. One point worthy of mention is that Restlet comes with its own libraries for XML and JSON, although you could use others. And a feature that I like is that a Restlet service has an explicit routing table, which shows which URIs map to which code segments. So let me give an example right now. I've switched to the working file restletcode1.txt, and the code of interest is on line 1. So you see a public class. The name is arbitrary. Here it's called Adages Application. It extends the Restlet application class, and the important thing is the override you see. So there's a method called create inbound route, and the body of that method is in effect the routing table. So you see at line 3, a router is created, and then in the subsequent lines, there are pairs. There's a URI given as a string, and then there is a target given as a Java class. The preferred style in Restlet is to map a URI to a class. You could map different URIs to the same class. This would work perfectly fine, but it's not the preferred style in Restlet. So to take just 2 examples, here at line 4, you see that the URI /XML/ and then in curly braces ID, so that's a placeholder as you would suspect, for an ID such as 18, something like that. That URI maps to the XML1 resource class. That class has a method that's going to return a single adage. The next one down at line 5, /JSON, maps to the JSON all resource class, and you see that below at line 6. So that class, again, the name is arbitrary, extends the Restlet server resource, and down here at line 7, you see the familiar @get annotation, and then the body of the method, in this case toJSON, manages the details, generates the appropriate representation, in this case JSON of course, and then sends that representation back to the client. Let me show you a further example. So I'm switching working files to restletcode2.txt, and here we see an example of the post handler. This public class called createResource again extends the Restlet server resource class. Down at line 1, you see the familiar annotation for a post request. And the point that I wanted to emphasize is down here at line 3, very similar to JAX-RS in style. There's a nice utility class called form. This is a Restlet class. It basically structures the data that come in the HTTP request so that it's easy to extract what we want. So in this case, we're going to extract the value of the words. In other words, we're going to pick out the adage itself. And then after doing the appropriate logic on that, we're going to return a string representation basically confirming that a new adage has been added to the list of current adages. The point of this lesson has been to underscore that JAX-RS and Restlet are very, very similar in style. Sometimes people ask, well, which is better, which is to be preferred? A lot of that depends, I think, on taste. I think the important point is both JAX-RS and Restlet represent a level above the basic HTTPServlet approach. So these 2 frameworks are quite good, and in Java, it's always wonderful that one has choices. So we've seen so far 3 frameworks. In this lesson, we're going to look at options for publishing REST-style services written in Java. You're looking at the working file publishoptions.txt. Let me begin with a brief review. So far, we've used Tomcat and Jetty, both of which are written in Java and which are themselves relatively lightweight web servers. We've used those for development, and these are also, of course, suitable for production. These are real-world web servers. They support HTTP and HTTPS. They make an excellent choice for the publication of Java-based websites and web services. Scripts written in Ant or Maven, we've seen an example of an Ant script, can automate the process of deployment and take away a lot of the pain points. If you're using an IDE such as Eclipse, NetBeans, IntelliJ, and the like, these also automate the deployment of web services. So Tomcat and Jetty, although they are production grade, do not pose any serious challenge. The point of this lesson, however, is to look at options. So you might want something even lighter weight for development. And to that end, I'm going to show you an option that's available in Restlet. There are similar options available in JAX-RS. This next working file is called main.java. It's encapsulated in an executable jar file called Restlet publish.jar. And in this case, it's used to publish the adages service that we looked at last time. What I'd like to underscore is how straightforward the approach is. So you can see here, I have the cursor on my main method, and then starting at line 1, the setup is quite straightforward. First, we instantiate a component. Component is one of the Restlet built-in classes. Next, we call getServers on that component, and we basically add a toy HTTP server. So it's a toy server in the sense that it doesn't support real concurrent access. It handles each process in sequence to completion, but otherwise it's fully knowledgeable about the HTTP protocol. The second argument to add, by the way, is the port number, and I'm picking 8182. Any port number would do if it's open. Finally, we attach a URI, in this case /adages, any URI would do, to a given application, in this case the adages application that we looked at last time. And the final step in this little dance is to start the component. This basically runs the program indefinitely. You then could use basic curl requests covering the CRUD verbs in order to test that this is actually working. So this is a nice lightweight alternative to something like Tomcat or Jetty, but my 2 cents is that with scripts written in Ant or Maven, Tomcat and Jetty are almost as straightforward to use as something like this command line server. In this lesson, I'm going to suggest a programming exercise, a full programming exercise, that should help to put all of these details together and make the REST-style web service a bit more comprehensible, especially for programmers. What programmers understand is code, and we learn by writing code. So that's the spirit of this exercise. To that end, I have a working file. It's called exerciserest.txt. It summarizes some points. I don't want to read through it. I will refer to it from time to time. Let me instead take a more informal approach and talk about the spirit of this exercise. The first thing you have to decide, of course, is what framework you're going to use. So the 3 that we've covered, the HTTPServlet, JAX-RS, and Restlet, of those 3, the servlet, of course, is the simplest, and the other 2 represent a layer of software above the servlet. So I'd pick one of these 3, and I wouldn't worry too much about which one. For example, if you pick the simplest, HTTPServlet, in the course of doing the exercise, you may wind up finding that there are features you would very much like to have, but don't have. For example, the servlet is not especially good at RESTful routing. It gives you the do get, the do post, and so on. But if you have variations, for example, on get requests, get plain, get XML, and so on, you would have to handle those, in effect, internally within the do-get method. You'd have to farm those requests out to other methods that you would have written. If you were using JAX-RS or Restlet, by contrast, you'd have more direct control over the routing. But this is something that would really come to the fore in using the HTTPServlet framework. If you pick one of the other 2, JAX-RS or Restlet, you're going to find that there's a level of complexity, and we've seen that complexity. There's a level of complexity that you don't run into with the servlet example. For instance, the web.xml configuration file becomes more complicated because you've got the so-called interceptor pattern. So whichever framework you pick, I think you'll get an appreciation of what the other frameworks have to offer by way of contrast. So let me now summarize what I think are the main points. I'm simply going to do a very quick run-through. So in the exercise, you should implement the 4 CRUD operations. You want to do as much with RESTful routing as you can. In particular, the spirit of REST-style services nowadays is to give equal emphasis to the verb and the noun in a route. So for example, we've seen that a URI verb combination such as get predictions would lead you one place, whereas the combination post predictions would lead you someplace else. So this is the equal weighting of verb and noun. You should take advantage of what HTTP offers. Again, this is in the spirit of REST. You have status codes that let the requester know how the request went. 200, of course, is always good news. Something in the 400 range is always bad news. The MIME types can be used to determine whether the requester gets an XML response, a JSON response, a plain text response, or something else. In terms of data, I would not worry about that very much. So for example, in this first full exercise, I wouldn't bother going to a real database, although that's always an option. The different variants of the prediction service that we've seen hardwire the data in a text file, predictions.db, which in turn is packed into the deployed WAR file. Again, that code you can take a look at, and I'd suggest even borrow straightforwardly to avoid sort of the data processing side of things. The Adages service takes an even simpler approach. It has the data as an array of strings. That array of strings is then transformed into a thread-safe list of adages. I'd minimize the complexity of data and focus instead on the REST style. Let me hit this bullet point. It is important to support thread safety. So to that end, the central data structure should be a thread-safe data structure, and the 2 attractive ones are the ones that we've seen so far. There's the concurrent hash map and the copy on write array list. These are really powerful data structures. Both are part of java.util.concurrent, and I think getting used to using them is a very nice thing as well. If you get the chance, I would make this probably optional. I would do something with data validation. The way all data validation is done nowadays, if it's done seriously, is through regular expressions. So I'd get my feet wet playing with that as well. So good luck with the exercise. Just getting something done is more important than the particulars. So I'd approach this exercise in that spirit. In this lesson, we're going to take a step back from the code details and look at the architecture of REST-style web services. In particular, we're going to look at the 2 different approaches that we've taken so far in these lessons to writing such services. You're looking at one of my working files. This is called restarchitecture.txt, and at the top, I summarize in words the 2 different approaches that we've taken. I also have some very simple depictions of those 2 approaches, and the cursor is in front of the first. So let me cut to the quick. In this first approach, which uses HTTPServlets directly as web services, the service is simply a servlet instance that sits inside a servlet container. In the case of Tomcat, the container is called Catalina. In the case of Jetty, there's less confusion. The container and the web server are both called Jetty. In any case, the initial prediction service, done with JSP, and the later predictions to service, done with the HTTPServlet subclass, both of those exemplify this first approach. There's lots of appeal to this approach. If you've done websites in Java, your websites basically are instantiated as servlet instances. In other words, in exactly the same way. So that experience with websites can be carried over directly to web services. There's also very little complexity. The web service instance sits inside the servlet container. There's no intermediate layer of software. The second approach we've seen in JAX-RS and Restlet has a quite different architecture. In this case, you have, when you deploy with Tomcat or Jetty, you have the so-called interceptor servlet. We've seen that. And in the case of the Jersey implementation of JAX-RS, that interceptor servlet is very nicely named. It's called Servlet Container. You can see the cursor in front of the fully qualified name. What happens in this architecture is that a web service becomes, in effect, an application instance that sits inside the interceptor. The interceptor, in other words, acts as a container in its own right. What you now get is some complexity. So you have instances of the JAX-RS servlet container sitting inside the Tomcat servlet container. Now, with this additional complexity, of course, comes additional functionality. So in both JAX-RS and Restlet, for example, we've seen that you get nice support for RESTful routing. You get, if you like, automatic generation of XML and even JSON documents. You get some easy data validation using regular expressions. So there's features that come with that extra software layer, but there's also complexity. Now, an obvious question, of course, in going over these architectures is to pick a favorite. And you may think that I'm chickening out here, but I'm not going to do that. It seems to me that one of the really attractive things about Java is that it gives us choices. That can be irritating when you're forced to make a pick. It can be a little bit annoying. It causes some head scratching, but it's better, I think, to be given those choices than to be forced to take a particular option. So if simplicity is what you want, then of course the HTTPServlet is the way to go. There's no intermediate layer of software. It's as close to the metal being the underlying web server's container. It's as close to the metal as you're going to get in doing REST-style web services. If the additional functionality is attractive to you, the RESTful routing, the use of annotations, the automatic generation of payloads and so forth, then JAX-RS, Restlet, and even other frameworks become quite attractive. The most important thing, obviously, is to have a sense of the trade-offs. If I go this way, there are pluses and minuses. If I go that way, there are different pluses and minuses. As in everything in our business, it's always a question of trade-offs. In this lesson, we're going to review options for generating JSON responses and RESTful services. I'm going to use the Predictions3 service, which is written in JAX-RS, for illustration. You're looking at the working file json.txt. So if you look at line 1, where the cursor is placed, you see the standard Java XML annotation at XML root element, and then lower at line 2, you see another annotation at XML element. That's on the getter for the who property. There are similar annotations on the getWhat and the getID properties. The result of these annotations is the following. If you come up and look at this comment, I'll highlight it. You see that the outermost element in the XML document is prediction, and then inside, nested inside, are ID, what, and who elements. That's basically the result of those annotations. There's nothing in the code itself that explicitly generates this XML. The JAX-RS does that automatically because of the annotations. Now, it's fair to say, I think, that Java's support for XML has been solid right from the start, and you could make the case nowadays that it's best in breed. So it's quite good. It's certainly adequate to any task that we might have in XML. With JSON, it's a different story. The JSON support is quite good, but it's mostly third-party. So, for example, down here at this bullet point, I single out Jackson, and you see the URL there. Jackson is widely used for JSON generation and consumption. We'll see the other side a bit later.
It's the JAX-RS package that's used in the Predictions-3 service. There are other lighter weight packages. For example, JSON Simple is something that I like if I just have to do routine generation of JSON documents. In any case, the important thing is that the support is there and it comes from third-party packages. Now, the Predictions-3 service could rely upon the JAX-RS runtime to generate both XML and JSON automatically, but the Predictions-3 service doesn't do that. Instead, the JSON is generated manually. So I'd like to explain why, and the last point down here covers the three basic reasons. The first reason was mentioned earlier. That is, JAX-RS will generate JSON payloads automatically, but the requester has to inject an HTTP header into the request. Basically, that header puts in the MIME type application/JSON. In the earlier curl tests, this is done. So for illustration, if you like, you could go back and take a look at the curls test for the Predictions-2 service. The second reason is that the Predictions-3 service already has a uniform style of RESTful routing. So for example, if the client wants an XML response for all of the predictions, the URI would be /predictions/XML. If the client would prefer JSON, then it would be /predictions/JSON. And if the client would prefer plain text, it would be /predictions/plain. So the routing already covers the desired type. I didn't want to impose a further burden on the client by requiring the client to inject an HTTP header. Finally, it's really no big deal. It's quite easy to generate a JSON payload given either Jackson or one of the other libraries. So for example, in the very last line, you see the code at the end, new object mapper, and so on, that's used to generate a single prediction. The same command would be used to generate a list of predictions in JSON. So there's really very little burden to what I just described as the manual generation of JSON documents. In this lesson, we're going to switch from the service side of REST-style services to the client side. In particular, we're going to focus on one of the challenges that faces any client of a REST-style service. The working file that you're looking at in the Emacs editor is called client-challenge.txt. In general terms, the challenge on the client is to extract information from whatever document is returned by the service. For now, there are two broad cases to consider. The first case is this. The response document is in JSON. If the client is in JavaScript, this is really good news, as we've talked about before, because a JSON document is, in effect, just the text representation of a JavaScript object. So all the client needs to do is to convert that document into a JavaScript object and then proceed as normal. If the client, by the way, is not in JavaScript and gets a JSON document, then the client needs to do something like parse the document to extract its informational content. The other case, and this is the case we're going to be focusing on at the beginning, is that the response document is in XML. This is still very, very common. And there are two general approaches that might be taken. In particular, of course, we're concerned about Java approaches. So let me address those directly. The first approach is to parse the XML document to extract the information. Now, Java has very good support for the two standard ways of parsing. One is called DOM parsing, DOM, as in Document Object Model Parsing. A DOM parse basically is tree-based. That is, the DOM parser builds a tree structure, and then the tree structure allows information to be extracted pretty easily from it. This works for relatively small documents. For large documents, a stream-based parse, a SAX parser, simple API for XML is the standard used there. We'll get into some of these details a bit later. In any case, if a parse is done, this can be a little bit tedious because the parse has to be done, it has to be checked for success and so on, and then the information has to be extracted. The second approach is an attempt to avoid the parse altogether. So Java has very strong tools and libraries that allow XML documents to be converted into Java objects and vice versa. These technologies are grouped under the label binding. This is standard, by the way, across the industry. It's not particular to Java. So the so-called JAX-B, Java API for XML binding packages, are ideally suited for this task. Suppose that a Java service returns an array list of products. What we would like to happen on the service side, of course, is to have that array list of products automatically converted into an XML payload. This can be done with JAX-B technologies straightforwardly. But on the client side, we'd like to take that XML document and have it converted automatically into an array list of products. In fact, we'd want that behavior on the client side regardless of the language in which the service might be written. This is a typical example of what's known as XML-Java binding. This second approach, this automatic conversion of XML into Java and Java into XML, requires a bit of setup, and it depends very much on what is known as the XML schema, which is an XML document. In effect, it's a grammar that describes the layout of a particular response. So in summary, what we're going to be working our way towards are JAX-B tools in Java that allow us on the client side to avoid explicit parsing of response documents in XML. In this lesson, we're going to look at a full client against the REST-style predictions2 service. Before I explain the working file that you see on the screen, that's perl.out.txt, let me clarify what I mean by a full client. All of the clients so far have been very short Perl scripts, some of them packaged together to do a series of tests, and curl is excellent for preliminary testing of RESTful web services, but curl is also limited. Curl is able to send out any of the CRUD requests, but when it gets back a response, curl by itself does not have the power, for example, to parse an XML or a JSON response. For that, we need a more powerful tool, a client written in a standard programming language. I'm picking Perl just for convenience, but Ruby, Python, C, and even Java would be just fine. I'm picking non-Java quite deliberately because web services are supposed to be language neutral. So this is a chance to illustrate that point. We have the predictions2 service written in Java and a client against that service written in a non-Java language. Let me now turn to the working file. The Perl client runs a series of tests. It does all of the CRUD tests that we've seen before. It requests XML payloads, JSON payloads. It does get all. It does get one. We're interested in the XML responses from the service. And in particular, one of those responses is a single XML document that contains all of the predictions. We've seen that document earlier. We don't care so much about the details right now. The point of interest is this. The Perl client parses that document and extracts the information of interest. And in this case, the information of interest for each of the 32 predictions is, first, the ID. So those are the integer values you see on the left. And then the who, so Cornelius Tillman is the first who, then an arrow followed by the what. The document you see is plain text, but it's not downloaded that way from the service. Instead, it's extracted via an XML parse. Let's turn now to the code that does the parsing. So this working file is called predictionsclient.txt. It's a fragment of the full client. The full client is called predictionsclient.pl, and it's ready to go if you have Perl and the required libraries. Let me get to the details. At line 1, you see a function. In Perl, it's a subroutine, but it's a function called getTest, and this is basically a getAll request. The predictions2 service is going to return an XML document that contains all of the predictions. When the response is received, getTest calls handle response. You see this at line 2. And the second argument to handle response is a pointer to another function called parse XML. Parse XML is what does the heavy lifting. So let's move down to that guy right away. At line 3, I'm using the XML XPath library that comes with Perl. Virtually every modern programming language has this library, or the equivalent. XPath is a standard part of XML. Basically, what it does under the hood is a tree-based parse. The outcome of that parse is a tree structure. XPath is then able to search that tree and extract elements that are desired. That extraction, in this case, occurs in lines 4, 5, and 6. And the basic idea in each of these is each of these searches returns a list. So, for example, at line 4, this extraction returned a list of IDs. Line 5 returns a list of the who's, the authors of the predictions, and line 6 returns a list of the predictions themselves. Line 7 is just a standard Perl loop that iterates across each of those lists and prints out per prediction, ID, who, what. So let me go back, refresh our view of what the output is from that while loop. Now let me go back to the Perl code for one last point. The idea here is that once the response is received from a successful request, the work has just started. And the first part of that work is typically a parse or the equivalent. So we see that in Perl. We'll see that again later in Java and even later in JSON. But this is now a more realistic client, more realistic than the curl clients we've seen so far, because it's got to do some down and dirty work, in this case, XML parsing. In this lesson, we're going to look at our first Java client against a REST-style service. And in fact, the REST-style service is going to be the Ecommerce service from Amazon. We've talked about that service before. This is the web service counterpart to the e-commerce website that is so familiar. Indeed, we're going to look at two clients against the e-commerce service. These clients are packaged in executable jar files. The first is called Amazon1.jar. The second is called Amazon2.jar. These are included in the working files. The working file you're looking at right now is called AmazonSetup.txt. You'd execute these jar files in the standard Java fashion. So from the command line, you would do java-jar amazon1.jar, and then you need two command line arguments. The first is called an access ID. The second is called a secret key. So let me explain those very quickly. In order to run these programs, you're going to need to be registered with Amazon. You may have registered already and have these credentials. If not, you see the URL, aws.amazon.com. So registration is free, but you need the access ID and secret key. The short version of the two is this. The access ID is your numeric identifier. The secret key itself is not sent over the wire in a request. Instead, the secret key is used on the client side to generate a hash value that is sent as part of the request. Amazon, of course, has a copy of your secret key, and it tries to generate exactly the same hash value. If so, it respects the request. If not, it rejects the request. We'll talk about that a bit more later. The first client, Amazon1.jar, does a so-called item lookup operation against a Harry Potter book. The application has hardwired in it the numeric identifier for this book, and basically asks Amazon, do you have this book? If so, please send me the information about it. If the request is successful, the client gets back an XML document. Here's a part of it. So we're now looking at another working file. This is called AmazonResponse.txt. If you run the client, you'll see the full XML document. This has been edited for readability. What you see at line 1 is the so-called item ID for the book in question. So you see the value there, 0545, and so on. And then down here at line 2, you see so-called item attributes. This is the information that the first client is interested in. In particular, the first client is going to extract the author's name from this XML document.
And as you can see, starting at line 4, there's other information as well. Product group, title, and so forth. The first client extracts the information by doing an old-fashioned XML parse. We'll see the details in the next lesson. The second Amazon client takes a more sophisticated approach. It uses the JAX-P libraries in order to avoid an XML parse. But we'll get to those topics shortly. In this lesson, we're going to take our first look at the RESTful client against the Amazon e-commerce service. You're looking at the working file Amazon code structure.txt because it will be useful before jumping into the code to have a sense of how it's structured. The executable jar file, amazon1.jar, has 2 source files therein. Those files are, of course, also compiled. The first of those is called request-helper.java. It's basically a utility class. I'll clarify a bit more in a bit. And the second is called RESTful Amazon.java, and that's the class that contains main. So, with respect to overview, there's basically 3 things that this client has to do. The first is actually the trickiest. Amazon is very fussy about the URL that is sent in a GET request to do an item lookup. The item lookup is the operation that we're going to perform. In particular, the information that's contained in the query string attached to the GET request has to be formatted in a very precise order. If there's any mistake in the formatting, Amazon basically rejects the request. So the key value pairs have to be sorted, they have to be base 64 encoded, there has to be an appropriate timestamp, all of that sort of thing. I've delegated all of that low-level work to the request helper class, so that class is basically a black box for us. There's no really important lesson to be learned from looking at the details. It just does what it has to do to make the request work. The second chunk of code uses the java.net.url connection class. That's a standard library class. And it's well suited to set up a network connection to Amazon in order to send the request and get the response. So it's really straightforward, as we'll see momentarily, and it's ideally suited for what we want to do. Finally, when the response comes back from Amazon, it comes back as a relatively large and complicated XML document that needs to be parsed. In this particular example, I'm using a so-called DOM, or tree-based parse, and again, I'm relying upon one of the standard Java classes to do that. Let's look at the code. This second working file is called amazon1code1.txt. The full source code is available as noted in the jar. Let me just remind you about the invocation here. The way you run this client from the command line is as java -jar amazon1.jar. And then as command line arguments, you provide your access ID and your secret key. Those are picked up, of course, in main. Let me jump now here to the end, to line 1. They're picked up in main, and my program then passes them off to the function called lookupStuff, which is at line 2. So as you can see, the lookupStuff method receives the access key and the secret key. It immediately calls below the constructor for the request helper, which is going to do the dirty work. And we'll see that again in a second. Starting at line 3, we create a map. So just a collection of key value pairs which contains the information that Amazon wants. So for example, the particular service that we want is officially called AWS e-commerce service, AWS for Amazon Web Services. The current version you can see there. The operation we're going to perform is called an item lookup. We're looking up a book. And the ID is the numerical value that identifies that item. Once all of the relevant data are put into the map, the request helper is used to put everything in proper order, timestamp it. Then we're ready to connect to Amazon. And that's done in a method called requestAmazon. That's called at line 5. The argument is the string representation of the URL to get to Amazon. So down at line 6, requestAmazon receives that string URL. At line 7, we use the standard Java class URL in order to parse that string. So if the parse is successful, in other words, the URL is properly formatted, we get back a URL instance, and that can be used then to open up a connection to Amazon. So that occurs in just one line of code, as you can see at line 8. Very convenient. The line below it, which sets the input to true, does that because we're going to be receiving input back from Amazon. In effect, the XML document that Amazon's going to send us in response. The next task then is to read that response. So to that end, I create a buffered reader, so that's going to read text in effect. And then in a while loop, I iterate until I get the full response back from Amazon. This is basic networking, of course. I have no idea if Amazon is going to send the whole thing in one chunk, the whole thing in 3 or 4 chunks. So we go through a while loop until we've gotten all of the chunks. At this point, the response returned all the way down at the bottom is the string representation of the XML document. The next job is going to be to parse that document to extract the information that we want.
In this lesson, we're going to complete our look at the first Amazon client against the e-commerce service. You're looking at the working file called Amazon 1 Code 2. Let me review quickly how we got here. We sent a GET request to the Amazon e-commerce service, and in particular, this request was for what Amazon calls an item lookup operation. So Amazon maintains numeric codes for all of the items at its e-commerce site. We sent the code for a particular item. It happens to be a Harry Potter book. That was a successful GET request. What we got back in response was an XML document, and you're looking at a fragment here next to the cursor. What we need to extract from this document as proof of concept is the author, who is Rowling. Now, to the right, what you see is a depiction of the subtree in the DOM representation of this document. So we're going to parse the document to generate a tree. In that subtree, there's going to be an author node, and under that author node, there's going to be a text node that contains Rowling's name. So the idea is the code needs to find that text node and extract the name. So here's the relevant code. It's in the RESTful Amazon class, and the method name is getAuthor. The string argument, the XML document, is the entire XML document, the fragment of which you see above. Let me move down here to the numbered lines for ease of reference. What happens in line 1 is that XML document is reduced to a bunch of bytes, and those bytes are then used to populate a byte array input stream. You'll see why in just a moment. Basically, the Java parser wants a byte array. Down here at line 2, we build the parser. So I'm calling it builder because, in effect, this is the object that's going to build the DOM representation, the tree. The actual parse occurs at line 3. It returns a pointer to the root of that tree. In effect, a pointer to the item lookup response. The work now begins in earnest. So at line 4, we use the parser to get a list of all of the author elements in that tree. In this particular case, there's only one author, but of course there could be arbitrarily many. So we get back a list, in this case, a list with just a single item in it. At line 5, we're going to iterate across that list. Again, this is going to be fast since there's only one item in it. And in the nested loop, the for_int_j loop, we're basically iterating over the children nodes of the author. And what we're looking for is a text node. There might actually be several of these because the author's name might be so long that it can't fit into a single text node. But in this case, the fix is in. There's going to be one text node because Rowling's name is relatively short and the whole name fits into that node. We grab that text node and then we extract the author's name from it, and the author's name is then returned. Now you can see this code is not terribly long, but it is a little bit grimy. It's a little bit technical, and in order to write it and to get it to work, you'd have to have a fairly good sense of how the XML document is structured, of how the Java parse of the document works, and so forth. So it's technical code, if not particularly long code. It does manage, of course, to extract the author's name in the end, and that's the proof of concept that we wanted to establish. If you were going to do this once in a great while, going through the challenge of a parse like this might not be such a big deal, but suppose you needed to do this on a regular basis. The question then becomes, isn't there an easier way to do this? And the short answer is yes, there certainly is. And what we're going to do in the next lesson is use the JAX-B packages in order to avoid the explicit parse of the XML document. In this lesson, we're going to look at a second client against Amazon's e-commerce service, and the working document you're looking at is called Amazon2code1.txt. It's included in the working files, and it summarizes the similarities and differences between the two clients. So let me start with the similarities. The second client, like the first, can be invoked from the command line. So in this case, it's java-jar, amazon2.jar, and as command line arguments, your access ID and your secret key. Amazon2.jar contains all of the relevant files, including, for convenience, the source code. The second client, like the first, does a so-called item lookup. It provides the numeric key, in this case for a book, a Harry Potter book, that Amazon has in stock, and Amazon responds with an XML document that summarizes all of the relevant details about that book. And the first client, we used a so-called DOM parse, tree-based parse, to extract relevant information from the XML document. In this case, we're going to avoid the parse altogether and rely instead on JAX-B technology. So let me go over the details before we look at the actual code. The B in JAX-B stands for binding, and basically what this does is it provides a correspondence between XML data types and Java data types. Here are the details. Amazon publishes an XML schema for its e-commerce service. It's quite a beast, as you can see there, 1,300 lines of XML, and I have the cursor positioned on the URL. For convenience, I've downloaded that document and put it on my local disk, and you'll see why in just a minute. Now, this XML schema fully describes the layout of the response documents that we get back from the Amazon e-commerce service. In programmers' terms, the XML schema provides data types, so this is extremely important. Core Java comes with an XJC utility. It's a conversion utility. It converts XML, in particular an XML schema, into Java data types. That utility, by the way, is in your install directory in the bin subdirectory, so the same place as the compiler and the runtime. The way it works diagrammatically is this. You feed an XML schema document to XJC, and then XJC generates the corresponding Java classes, which of course are Java data types. At this point, what you have is XML on the one side, the XML schema, and Java on the other side, class files. So it's quite powerful and convenient. By the way, in this particular case, you wind up with a lot of classes, about 85. So let me show you with the command line how this works. To begin, I'm in a bash shell, by the way. You can see amazon.xsd. That's the XML schema that I downloaded locally. And now what I'm going to do is run the XJC utility. The -p stands for package. XJC is going to create a subdirectory called pack-A. Any name would be just fine. And it's going to populate that with the Java classes that correspond to Amazon's XML schema. So here we go. Now let me just show you what this subdirectory looks like. As you can see, we have all sorts of Java source files. And let me highlight one of them just for emphasis. So you see, for example, there is a source file called item.java, and that represents a particular item such as a book or a CD and so on. We're not actually going to look at these files. They're heavily annotated. We don't care about the details so much. We care about how they're going to be used. In this lesson, we're going to continue looking at what I'm going to call the JAX-B client against Amazon's RESTful e-commerce service. The working file you're looking at is amazon2code2.txt. So let me review quickly what we did last time. We used the XJC utility that ships with core Java to generate roughly 85 Java classes from the XML schema that Amazon provides for its e-commerce service. So we have a bunch of Java source files. We'll need to compile those. Those files, by the way, are included in Amazon2.jar for convenience, and Amazon2.jar is among the working files as well. Let's look at the link in the JAX-B sense between what's on the XML side and what's on the Java side. So to begin, on the XML side, we have the schema from Amazon, and that includes, among its many elements, this one. And you see that this is an element that describes an item lookup response. And if you come down here to where the cursor is, you can see that such a response includes an operation request. This basically says what we want to do, an item lookup in this case. What's the thing we're looking for? We give its numeric value and so forth. And then what we get back is a list of items. Now in this case, the lookup is very simple. We get back a single book, but we could get back a list of many books, a list of books and CDs, a list of basically anything. The actual document that we get back from the Amazon e-commerce service looks like this: item lookup response, and then inside, following the outline described in the schema, you see operation request. I've deleted the details for now, we don't care. And then you see items, and this goes on and on and on, and it lists all of the items that we got back. In this case, as noted, we got back only one, but there's still a wealth of information in there. Now let's look at the Java side of things. From XJC, we get this item lookup response class. It had to be compiled. We got the source code. And when we get back a particular XML document from the e-commerce service, we can use JAX-B to create an instance of an item lookup response. In other words, an object in the Java sense. And that instance is going to contain all of the relevant information, all of the information that is in the XML document. And then we use standard Java code to extract that information from a Java object. In other words, we bypass any XML parsing. So the XML is kept down in the sub-basement, which is convenient. There's a fair amount of complexity in doing this JAX-B business. It requires an understanding of how JAX-B works. You need to download the XML schema. So there's a fair amount of preparation that has to go into using JAX-B technology. My point is that you wouldn't do this for a one-off application. If we just wanted to go to Amazon one time, get some information, extract the information, and then move on, then an XML parse might be the way to go. This second approach, the JAX-B approach, really makes sense if we're going to be doing this a lot. It's much more convenient for us as Java programmers to be working directly in Java rather than in XML. In this lesson, we're going to finish up the Amazon 2 client against the RESTful e-commerce service. You're looking at the working file, Amazon 2 code.3, and it sums up some of what we've done so far. So let me begin with the so-called binding. The binding connects an XML data type. In this particular case, an item lookup response document is described in the Amazon XML schema, and a Java data type. In this case, the item lookup response class that we got from the Java XJC utility. Given that binding, we can now do what is called marshalling and unmarshalling. Marshall is the name of a researcher who did a lot of work, and so in his honor, these processes are described using his name. So let me begin with marshalling. The way marshalling works is as follows. On the Java side, you have an in-memory object. In this case, let's say, an instance of an item lookup response. Marshalling then generates the corresponding XML document. In our case, marshalling is not what we're interested in. We're interested in the inverse process, going from the XML document that we get from Amazon to an instance of an item lookup response class. So the unmarshalling then, to put it in context, works as follows. We send a request to Amazon. We get back the item lookup response document. We unmarshal that to get a Java object. That Java object encapsulates all of the information in the original XML response document. And then we use standard Java code to extract the desired information. So let's take a look at that. The working file is now Amazon2 code 4, and this is the actual code in the Amazon2 jar file. As before, the name of the method is getAuthor. The parameter, string XML, is the XML document that we got from Amazon. So let me begin with the analysis. At line 1, there's a reference to Amazon.xsd. That's the XML schema that was downloaded from Amazon. It's included for convenience in the Amazon2.jar file. We use that to create a schema instance. So Java has a class called schema, as you'd expect. And that's all preparatory for line 3, which is the critical one. The JAX-B context in Java terms is all of the information that Java needs in order to convert between Java on the one side and XML documents on the other side. In particular, the JAX-B context uses reflection in order to gain the needed information about a given class. In this case, of course, it's the item lookup response class, and you see that at line 3. From the context at line 4, we get an unmarshaler. Then down at line 5, this is where the real work occurs. We use the unmarshaler to take the XML document and convert it into a Java object. Nice and clean, one line of code basically after the preparation. Now the code from line 6 on down looks a little complicated, but there's reason for that. When you do a lookup request against Amazon, for example, we did it on a Harry Potter novel, you might actually do it on everything about Harry Potter. Books, movies, records, toys, everything. So the response document, in principle, could be very complicated. In particular, from a programmer's point of view, that response can be a list of various other lists. So what we get back, you can see at line 6, in the Java correspondence, is a list of so-called items. Each of those items is itself a list, as the plural suggests. So at line 7, there's a for loop to iterate over that outer list. And on each iteration, we grab one of the inner lists. And then at line 9, we iterate across that inner list. Again, if you were going to do this only once, it would probably not be worth the effort. But think of yourself as doing this day in and day out in web services. Now, for each item, we grab the attributes, because that's the information that's of interest to us in this case. Down at line 11, we get a list of authors. In this case, of course, it's simple. There's only one author. At line 12, we extract the one and only author. In this case, of course, it's Rowling. So let me summarize by emphasizing again the big picture. The nice thing about JAX-B is that it allows us to work exclusively in Java and to avoid explicit XML parsing. The downside of JAX-B is that we need some preparatory work. We need to learn an API. We have to know about the JAX-B context, marshalling, unmarshalling, and all of that. My 2 cents is that this is certainly worth the effort if you're going to do this on a regular basis. If you were writing a one-off application, parsing the XML directly might be the way to go. But for repeated applications, such as applications against Amazon, JAX-B offers some wonderful functionality. In this lesson, we're going to look at a series of web services hosted by the Chicago Transit Authority, the CTA for short. And these web services provide, as web services, in a REST style, the same information that's available at the CTA website. I should mention that these services are near and dear to my heart. I take the bus to and from work, and so I have a little client that informs me when the next bus is going to arrive at a given station. Let me start out by contrasting the CTA services with Amazon's. The Amazon e-commerce service is traditional in the following sense. There's one service with a whole bunch of operations. So for example, we've looked at the item lookup operation, but there are search operations, order operations, filling the shopping cart operations, and so on. The CTA services are designed a little bit differently. It's one operation per service. So each service consists of a single operation, which makes everything very simple and very modular. The CTA, like Amazon, provides an XML schema, but again, given the modularity of the CTA services, the schema is very small, 30 lines or so per service. By contrast, that Amazon e-commerce service has a schema of about 1,300 lines. The CTA service is free to use. You do need what they call an API ID. I've provided the URL there if you're interested in trying this. I'm going to refer to that ID as the API key because that's what the CTA calls it. So let me give you a quick example. You're looking, by the way, at the working file CTA Bus Tracker 1.txt. My program, and we'll look at the code in a bit, would issue a GET request against a URL such as this. Let me highlight the URL for emphasis. And it would provide the relevant information, including my API key. In this particular case, we're asking the CTA when the next bus is going to arrive at a particular station. The CTA has numeric values that identify each of the stations. This happens to be a station on a north-south street, and the station is known informally as Southport. Once this request is issued, the CTA responds with the expected XML document. You see it here. It's about 26 lines in length, and I've marked some of these. There's a request timestamp. This is the informal name of the station location, the direction in which the bus is moving. By the way, this can be a little complicated. This particular bus moves south, but then makes a left turn to go east. This is the expected arrival time. In my experience, the CTA is within 5 minutes or so it's a fairly reliable service. And if you want the GPS coordinates, you can get those as well. Let's take a very quick look at the schema, just so you get a sense of how simple these services are. To that end, I'm switching working files to CTA Bus Tracker 2.txt, and this is most of the XML schema. I've excised 8 lines or so, and as you can see, for example, at this marked element, you have ETA, so expected time of arrival, and notice that max occurs is set as unbounded. You can either get a single time, or if you like, you could get, for example, all of the expected arrival times over a day, or if these change by day, over a week or even longer. Very nice. And down here, we referenced this a bit earlier. This is a numeric value that indicates which direction the bus is moving. In this lesson, we're going to wrap up our look at the client against the RESTful Bus Tracker service from the Chicago Transit Authority. You're looking at the working file CTA Bus Tracker 3.txt. The full source code, bustracker.java, is also included among the working files. Let me get to it very quickly. There's a base URL, you see this next to the cursor, against which all of the requests are going to be made. I'm going to make 3 of them for demo purposes, and they occur down in this private method called demo, and each of the requests is marked with a comment to the right. So the first request, you see the full URL, so it's the base URL plus get time, that's the particular service, plus key, and that's my CTA API key that's entered as a command line argument. Make request is then called. Make request also receives the response. We'll see that in a second. The second demo involves the get vehicle service. This provides the richest information. It basically gives a list of all of the CTA buses, tells you where they are, if they're under repair, if they're out on their routes, and so forth. So it provides a wealth of information. This is perfect for data analysis, where you're doing a study, for example, of this sort of thing. And then the final demo, down at line 3, checks out a particular route. All of the information is passed into the CTA service as query string key value pairs. Now, the make request method down here uses one of my favorite utility classes in Java, the URL connection. You see that at line 4. This is ideally suited for RESTful clients. It opens up a connection, you can send a request, receive the response, the API is straightforward, and we've seen this class used a couple of times before. Way down here at line 5, there's a while loop which reads the response from the CTA service. It comes in as chunks of XML, and the while loop simply puts this together to wind up with one big XML document. In this particular demo, I do nothing but print that document, but in a client that I use for going to and coming back from work, I just use a very simple XML parse to extract the information that I need. What I'm going to do is switch working files. This is now rest summary.txt, because now is a good time to wrap up what we've seen. We've seen a couple of clients against a fairly complicated RESTful service. That, of course, is the Amazon e-commerce service. And we've seen a client against a relatively simple, straightforward service, and that's the CTA Bus Tracking service. Let me use that as a springboard to provide an overview. One of the real challenges of REST is that there are no standards. There are accepted practices, and folks that provide RESTful services provide those practices to some degree or other. For a programmer on the client side, this can be frustrating. There is good news. Virtually all services nowadays provide at least an XML schema, or the equivalent. XML schema is not the only game in town. There's RelaxNG, there's Schematron. There are other ways to provide a grammar for an XML payload, but XML schema remains the default. So with an XML schema, as we saw in the Amazon case, we can use Java's XJC utility to create Java classes that then allow us to use JAX-B so that we can avoid explicit XML parsing. Very nice. On the downside, the XML schemas that you get from different services vary widely. So, for example, Amazon has its own, eBay, Facebook, Tumblr, Twitter, and so on. So there's no standardization across these XML schemas for RESTful services. The big question for all of us as programmers, I think, is this. When you're writing RESTful clients, how are you going to handle the payload that comes back, assuming that it's XML? This is the question of whether to parse explicitly using a DOM parse or an XPath-based parse, which is a variant of a DOM parse, or to go to JAX-B in order to avoid dealing with XML at all. My view is that for very simple services, for me the CTA service is a perfect example of that, a straightforward parse is not a bad way to go. It's not that complicated. There's not that much information that you normally need to extract from the response payload. For something bigger, and I'm thinking here, of course, of Amazon, it seems to me that the JAX-B technologies really do pay off. Much easier, I think, to work in Java to extract information than to work in XML. In any case, this wraps up our look at clients against RESTful services, that is, RESTful services that respond with XML. What we're going to do in the next lesson is start to look at JavaScript clients against RESTful services. In this lesson, we're going to look at the first of two examples that involve JavaScript clients and JSON documents. This example also illustrates what people call orchestrating web services. So let me begin with the orchestration idea. Web services are meant to be highly modular. REST-style services in particular have a very simple API, and these two facts encourage what folks call orchestration. That is, getting distinct web services to work together in order to create bigger, richer, more complicated services. In this particular example, we're going to orchestrate two distinct web services. We've seen already, or at least we've talked about in general, why JavaScript clients should prefer JSON to XML, plain text, or some other format as a response document from a RESTful service. And the reason can be depicted down here. If a JavaScript client gets a JSON document, that document can be unmarshaled into a native JavaScript object, which then can be processed in the usual way. Let me illustrate this with an image. And this will clarify what this first service looks like. Why don't we start on the right-hand side? You see something here called the W3C service. Technically, this service doesn't come from the World Wide Web Consortium, but rather from the World Wide Web Consortium Schools, which is an independent group that specializes in education and consulting for all things web. In any case, one of these W3C services delivers up a list of CDs from the 1980s, artist, name of album, price, that sort of information. But the response is in XML, as you can see in the image. So in this example, I've written an intermediate web service. Let's call that the CD service. It's very, very simple, JSP based with a backend Java bean, just like the first example we saw. And the main job of that CDs service is to take the XML payload and convert it to JSON. And that JSON is then sent back to a jQuery script. So jQuery, I'm sure you're familiar with it, at least by reputation, is a particular dialect of JavaScript, a very friendly one for what we want to do. That jQuery script is running in an HTML page that we're looking at in a browser. So going the other way, the jQuery script issues a GET request against the CDs service, which then issues a GET request against the W3C schools service. The CD service in the middle gets back an XML document, converts it into a JSON document, sends it back to the jQuery script, which then does some processing. So let me illustrate that by bringing up a browser and showing you the whole thing. Let me refresh this URL. By the way, I've published this service using Tomcat. So what's happened is the request has gone from the browser to the CDs service, which has gone to the W3C school service. The CD service got back XML and converted it to the JSON that you see displayed in this alert window. Now the font is a little bit small, but if you look at that very first line, you can see a left square bracket. That's a JavaScript array. Inside, you can see a left brace. That's a particular CD object. So what you have is an array of these. What the JavaScript, in this case the jQuery, does is it takes that JSON document, it's converted into an array. This is actually done automatically, as we'll see when we look at the code. And then the jQuery creates an unordered list of, in this case, the name of the album and the artist. So the first entry you can see is Empire Burlesque, Bob Dylan, all the way down to the bottom, Unchain My Heart, Joe Cocker. This is an overall view. This will give us some context. What we'll do in the next lesson is get into the details and start looking at the code. The JSP code is very simple. The backend bean is very simple. And we'll also have a chance to look at the jQuery. In this lesson, we're going to focus on the code in the orchestrated CDs service. All of the code is contained in a single WAR file called cds.war. That's deployed with either Tomcat or Jetty or a comparable web server. Basically, it contains three important pieces. There's an HTML document. It's called fetch.html. We'll look at that in the next lesson. That document contains embedded JavaScript, in this case jQuery. That's basically the client. On the server side, you've got a JSP script and a backend Java bean, very much like the first example that we did. Here's a very quick summary of the image we looked at last time that showed the architecture. The jQuery client in the HTML document issues a GET request against the CD service, which issues a GET request against the W3 schools service. That service returns XML, which is converted to JSON, which is sent back to the jQuery. As noted, we'll look in the next lesson at what jQuery does. Now let's focus a bit on the service side. The CD service code is two pieces, the JSP script, and that's very, very simple. As you can see down here, it's 2 lines. The second line is the important one for us. This line invokes the method getJSON in the backend Java bean, and that backend Java bean is an instance of the fetch.xml.java class. All of these source files are in cds.war, and the working file you're looking at is called cdscode1.txt. So we're now going to take a look at that backend Java bean. The working file now is cdscode2.txt. This consists of the heart of the intermediate service, in other words, the converter, the XML to JSON converter. The method of interest is called getJSON at line 0, and as you can see, it returns a string. That string is the JSON document. If you come down to line 1, that's the URL for the W3 Schools service. Notice, by the way, you can see from the URL at the end, cd_catalog.xml. This RESTful service is ridiculously simple. It consists of a static XML document, which is just returned upon any GET request. Once again, I'm using the URL connection class in Java because it's so convenient at line 2. So that's used to set up a connection. These details we can skim over fairly quickly. At line 3, a while loop is used yet again to retrieve the XML response line by line. Down here at line 4, there's some minor cleanup. The XML document received has a lot of single quotes in there. This line replaces those. Finally, at line 5, I'm using the JSON simple library. The jar file is included in the cds.war file. So I'm using that simple library to convert an XML document, which is lowercase first, to a JavaScript object. So the JSON object reference refers to a JSON object. Down here at line 6, however, that JSON object is stringified. In other words, it's turned into a text document, and it's that text document that is then sent back to the jQuery client. This code is fairly straightforward. It's about as minimal as you could hope for. The conversion of XML to JSON is straightforward. It's basically a one-liner in Java. In this lesson, we're going to wrap up our look at the CDs service. In particular, we're going to focus on the JavaScript, in this case, the jQuery client against the service. So as a quick review, I've brought up the browser. Let me do a refresh here. I've hit the service. What you see displayed in the modal dialog is the JSON that is returned from that service. And after the JSON is displayed, the code creates an unordered list, and it lists the CDs and the artists, as you can see on the screen. Now, if we look at the page source, you can see a very simple HTML document, and I'll highlight just a little chunk of that down here. Here's the jQuery code that is acting as the client against the service. I'd now like to move into the Emacs editor where we can get a better look at that code, and I've got some lines numbered. The working file you're looking at is fetch.html. That's the HTML document that we just looked at in the browser. And the lines of interest are these. You can see at lines 1 and 2, what this HTML document does is it downloads jQuery. I'm picking the minimalist version of jQuery, very lightweight, very small, and I'm getting the latest version because I have nothing in here that is version dependent, really. And here's the actual client. The jQuery syntax really isn't of interest to us. Most of it, I think, is straightforward, even if you're not familiar with this JavaScript dialect. So, for example, at line 3, getJSON issues a GET request against this URL. We're hitting my JSP script in the cds.war file. What is returned at line 4, this variable reference, whose name is CDs, is a JavaScript object. It's an array. In order to display it, I stringify it using a standard built-in JavaScript library function, stringify, and then I display it here. So let me backtrack for a second. What the CD service returns is a JSON document, in other words, text. But what the jQuery library does is automatically converts that JSON document into a JavaScript object. Ironically, in order to display that object in the alert window, I need to turn it back into a string. And that's what's done here at lines 4 and 5. Line 7 is where the action starts. The jQuery each function is an iterator, basically. So it's going to walk across the array, CDs, and each time it hits one of the elements, it's going to invoke this function of 2 arguments. The first argument is the index, and the second is the value at that index. And then at line 8, this is where elements are added one by one to what you see all the way down here at line 10, and that of course is the familiar unordered list at the HTML level. Lines 7 and 8 iterate over the array, and per array element, what they do is they add a new item to that unordered list down at line 10. Now the thing that's of interest to us is this. If you look at this part of the code, cds int.title, cds int.artist, this is just straightforward JavaScript. In this case, the jQuery dialect, but it wouldn't differ really in standard JavaScript either. So the point of interest for us is that even though the original data came in XML form, and that form was then converted to JSON, and the JSON then was converted into a JavaScript object, there's no explicit parsing, and in fact, there's really no way to tell, except for my intermediate code at lines 5 and 6, that we ever had JSON at play at all. In other words, the array that is processed down at lines 7 and 8 just looks like a regular old JavaScript array, which of course is the whole point. So that completes our look at the first JavaScript client. When we resume, we'll take a look at a second one. In this lesson, we're going to look at a second JavaScript client against a REST-style service. In this case, the REST-style service is the predictions3 service, which we studied earlier, and that service is implemented in JAX-RS. You can see that I've got a browser open, and what you see displayed as items in an unordered list are the 32 predictions. The HTML source is mostly JavaScript. So all of this is the JavaScript. The body of the HTML document that's downloaded to the browser is empty except for the placeholder for the unordered list. The JavaScript makes a call against the predictions3 service, gets the data in JSON form, and then generates what we see here. Now, there's a challenge here. The predictions3 service supports all of the CRUD operations. In particular, it supports post, the creation of new predictions, put, the editing of existing predictions, and delete, of course, the removal of existing predictions. So what we're seeing here in the browser might already be out of date. In other words, some other client may have issued a post request, a put request, a delete request that changes the predictions so that we're not seeing the current version. The challenge is to use JavaScript to ensure that what we see displayed here in the browser reflects the actual data. You can imagine the same scenario in a real-world application. For example, we might be looking at a product list, and the product list might be subject to change continually over the course of a day, and so we want to make sure that the client who is looking at the product list is looking at the most current version. So let me now do an overview of the various approaches to ensuring that the data are up to date. There are two general approaches, and they go by the quaint names push and pull. Let me quickly characterize each. In the push approach, on the service side, there's a list of connected clients, and if there's an important change to the data, the server on the service side might then push those changes down to clients. So for example, this might work well in a multiplayer online game where you have a central server that maintains the state of the game, records new moves, and so forth. A second approach, and it's the one that is used here, is the so-called pull approach. Each client regularly pulls the service to pick up any changes. In this particular case, the JavaScript client, it's written again in jQuery, embedded in the HTML page, does this every 5 seconds or so. Before we look at the JavaScript code, let me do a quick survey of the pieces of this example. First, the predictions3 WAR file, which is included among the working files, needs to be deployed. Once again, I'm using Tomcat for that. This version of the prediction service supports all of the CRUD operations, so we're going to be able to test whether this polling does in fact work. Poll.html is the displayed page we were just looking at. It resides in a WAR file called ajax.war. I'll get to the name when we look at the actual code, and it uses jQuery to poll the predictions3 service. In this case, it does so every 5 seconds. We're in a position now to test whether the polling actually works. So what we can do is display the page in the browser. in a separate prompt, issue a curl command, and here's the sample that I'm going to use that will delete one of the predictions, and that change in the predictions should be picked up in about 5 seconds or so, and the new revised list should then be displayed in the browser. We can also do more extensive testing. Earlier on, we looked at the file curls-test-rs.pl, which runs a series of tests against the predictions3 service. But for our purposes, this preliminary test should be good enough. In this lesson, we're going to finish the poll example in which a JavaScript client goes against the predictions3 service. The important thing about that predictions3 service, from our point of view, is that it supports all of the CRUD operations so that the predictions can be changed by any client. Furthermore, the predictions3 service is JavaScript friendly because it will return JSON documents rather than XML or plain text ones. So it's the most flexible of the prediction services. You're looking at the file poll.html. It's included in the working files, and it's the file that's embedded in ajax.war. Let me cut to the quick to why that name is used. Down here at line 4, there's a call in jQuery to the so-called Ajax function. Any function could be used. The term Ajax is not used so much anymore, but at one time it was used to characterize partial page updates. jQuery, that particular JavaScript dialect, has a function with that name, so for emphasis I thought I would use it. Now let me return back up to line 0. As you can see, the displayed URL here goes against the predictions3 service. It's deployed using Tomcat once again, and the important thing is way at the end you can see JSON, so this is a GET request for all of the predictions in JSON format because the JavaScript is going to find that very friendly. Now I'm going to jump around in the code a bit in order to explain the flow of control and the logic. So I'm going to go all the way down to line 9. And you can see down here at line 9, there's a call to $document.ready fetch. Once the browser has created the so-called DOM, in other words, the tree representation of the HTML page, in this case it's relatively straightforward, this function is going to be called by the browser, the ready function. The ready function, in turn, is going to call fetch, which is back up at line 4. In effect, then, that line 9 tells the browser, when you're ready, please invoke my fetch. The fetch, in turn, makes a call to the Ajax function. So let me just talk a little bit about the syntax in case you don't use JavaScript regularly. At line 4, the Ajax function takes a single argument. You see the parens, and immediately inside the parens, you see a left brace. Down here is the matching right brace and the matching parens. The important thing is that brace, key value, key value, key value, where the key values are separated by colons, constitute an object in JavaScript. In effect, an object in JavaScript is just an instance of a map. The key value pairs can come in any order. In this particular case, you see the URL, the method, which is get, the desired data type, which is JSON, that's at line 5. At line 6, we specify JSON using the MIME type subtype syntax. The char set is UTF-8, so Unicode transmission format 8. 16-bit Unicodes will be sent as 2 consecutive 8-bit bytes. We're telling the browser, don't cache the page, because we're going to be doing continual updates in any case. If this GET request is successful, this line 7 basically says call display preds, which is way back up at line 1. We'll look at that in just a moment. In case of error, all I'm going to do is log a message to the JavaScript console. Down here, this is really important. The set timeout function pauses for 5,000 milliseconds, so in other words, 5 seconds in between calls to fetch. So the polling occurs right here. Every 5 seconds, there's going to be a new call to fetch, and we're going to go back to the service and pick up any changes that happen to occur in the meantime. Now to line 1, the display preds function. What it does is, first, it cleans out the existing list. So if there's already a list of displayed predictions, it cleans that out. at line 2. And then at line 3, we've seen code very much like this in the earlier JavaScript example. There's the iterator, which iterates over the JSON array, and for each element prints out as the next item in the unordered list who said the prediction, followed by a colon, followed by what the prediction is. Notice that there is absolutely no parsing here of anything. The jQuery is working directly with the JSON, which jQuery has nicely converted under the hood to a native JavaScript object, an array of predictions. And it's the kind of thing that one sees a lot of nowadays in websites. That is, HTML pages that have embedded JavaScript, and that JavaScript makes calls against services to pick up data. In this lesson, we're going to do a wrap-up of REST-style clients against web services, and the example I'm going to use is JAX-RS. Both JAX-RS and Restlet have a client-side API in addition to the server-side API. The JAX-RS client we're going to look at is going to go against the predictions2 service, which is HTTPServlet based. So you could use a JAX-RS client against any REST-style service, just as you can use the standard Java URL connection against any RESTful service. All of the code for the client is included in a zip in the working files, and that zip is called JAX-RS client.zip. It contains a README and an Ant script to compile and run the client. Let's get into the client code. At line 0, I'm showing the first of 4 imports. There is a class called client that represents a RESTful client. There's another class called web resource that represents the resource against which the client is going to perform CRUD operations. There's the media type. We've seen that on the service side as well. That represents a MIME type. And there's a very nice form class that makes it easy to inject key value pairs into a request form on a post request. Down at line 1, you can see the URL for the predictions2 service. Once again, I'm publishing this service using Tomcat, and out of main, which I've not shown here, it doesn't do much, I call demo, and demo runs a series of tests, requests against the predictions service. So to begin, we instantiate a client, so client.create, very straightforward, easy to do. The follow redirects is in there just in case the service does a redirect. So basically, the client would follow redirects indefinitely. At line 3, you see the web resource. In this case, it's the predictions service. You create that, of course, with a URL. What follows are a series of short tests. So, for example, the first one called getAllDemo does a getAll request against the prediction service for both XML and JSON responses. There's a post demo, a put demo, a delete demo, and so forth. We're going to look at just 2 of these. So let me jump down here to the getAllDemo, which takes the web resource as a parameter. This is the first of the 2. So you can see the resource has an accept method, which specifies the desired MIME type of the response, XML, and then there's a get at the end. There's also, of course, a post, a put, and a delete. And the data type here basically says, return that document as a string. In other words, as text. If we did some JAX-B work, we could return a predictions or an individual prediction. But that would have to be set up using JAX-B so that the unmarshalling could occur. Once the response is in hand, I print it out to the screen for confirmation. The second getAll is very similar, except the data type changes, of course, from XML to JSON. So really, nothing new there. The post demo makes use of a very nice utility class called form. So you can see at line 6, we instantiate a form, and then what you can do with the form is just add key value pairs. And those are then properly formatted into the HTTP post request. That request occurs down here. You can see the post verb at the very end, and the response once again is a string. In this case, the string is plain text because all we're going to get back from the service is a plain text confirmation that a new prediction has been added to the existing group. So having taken this quick look at the JAX-RS client-side API, let's now make some general points, and I'm going to switch from this working file, which is client wrapUp.txt, to its companion file, which is client wrap2.txt. Let's begin with the JavaScript clients, because those are the ones we've looked at most recently. For JavaScript clients, JSON, of course, is the ideal response type because there's no need to do explicit parsing. The obvious point, but it's a point worth making again, I think, is that for Java and other clients, JSON is really no better than XML because the JSON would have to be parsed in order to extract the relevant information. Or, if not parsed, then JAX-B unmarshalling would have to be brought into play. On the client side, everything from the URL connection up through the client APIs available in JAX-RS and Restlet are very, very friendly. They're easy to use. For example, connecting to the service and sending requests is relatively straightforward. The big issue on the client side is always this, and this is the one we've talked about repeatedly because it deserves emphasis. What is a RESTful client going to do with the return payload? Is this payload going to be parsed? Or is something like JAX-B unmarshalling going to be used to construct Java objects that then can be manipulated in the usual way? In my view, this is probably the toughest decision that you have to make in writing RESTful clients. In this lesson, we're going to transition from REST-style web services to SOAP-based services. So let me start with a quick overview. SOAP is an XML dialect under W3C control. W3C, of course, is the World Wide Web Consortium. There are two official versions. 1.1 is the default, and 1.2 is the current version. For a programmer, there's very little difference between the two versions, and the examples that we'll be looking at could be done really in either version. At one time, SOAP stood for Simple Object Access Protocol. Nowadays, officially, it's no longer an acronym. SOAP also can be looked at a slightly higher level as a messaging protocol, and the messages consist of XML documents. They're commonly called SOAP envelopes because, as you can see in this little sketch, the document or outermost element is tagged with envelope, spelled exactly as you see there. The SOAP message can have an optional header that would contain metadata. We'll get into some details. And the required body, which contains the informational content. SOAP-based conversations look like HTTP conversations for the most part. The conversational pattern is typically request-response. So, a client begins the conversation by posting a request to the service. The body of that request is a SOAP envelope. And then the service responds to the client with another envelope, the response envelope. One of the most attractive features about SOAP is that mostly the XML remains transparent. That is, we don't see it any place in the code on the client side or on the server side, and that's because the underlying SOAP libraries handle the marshalling and unmarshalling. We'll see that in examples. As the saying goes, a picture is worth 1,000 words, so let me bring up 3 pictures to help with this introduction. So here's the first of those. This depicts a SOAP message semi-officially. Here's what I mean by that. The SOAP message contains 3 parts. So if you look at the top, you see the optional SOAP header, more about that later, the required SOAP body. These 2 parts together are sometimes referred to as the SOAP part. SOAP also can have optional attachments, and those attachments could be of any data type. So, for example, a SOAP message might contain as attachments a movie in some format. There are better ways to send binary payloads than by using SOAP, but the important point is you could actually use SOAP in that way to deliver multimedia content. As noted in the very quick overview, for the most part, SOAP remains transparent on both the service and the client side, and that's because XML played such a huge role, and the SOAP libraries do conversions. So in this example, you see conversions from Java into XML types on one end, and from Ruby types to XML on the other end. In this particular depiction, Java might be the client language and Ruby the service language, or vice versa. The really important thing is that XML data types, in particular XML schema types, act as the intermediate layer. XML, you might say, is what makes the services interoperable. So the clients can be written in one language and the service can be written in a different language. The reliance on XML, and the XML schema in particular, has other benefits. This is the most complicated picture, so let me try to describe what it's showing. Suppose that we're on the server side and we get an incoming SOAP request. We have an XML schema that can validate that request. So I'm going to jump ahead a bit. In SOAP, it's typically the messages themselves, those XML envelopes, that are data typed. So the XML schema describes in full detail what the request should look like. So on the receiving end, the first thing any production-grade SOAP server is going to do is to parse the incoming request to see if it's properly formatted. If not, an error message is going to go back. In SOAP, this is referred to as a SOAP fault. Only if the message is properly formatted, that is, validated, is it going to be forwarded to the application. And the service operation is then going to perform whatever logic is appropriate, generate a response, SOAP message, and send that back to the client. This overview provides a general picture of how SOAP works. In the next lesson, we'll get down into concrete details by looking at code for a SOAP-based service. In this lesson, we're going to look at a sample SOAP-based service and also an easy way to publish that service. You're looking at the working file ranservice.java. This contains the source code for the SOAP-based service. As you can see, it's fairly short. Let me go over the key parts of the code, and then we'll look at how to publish this service. So the import at line 1 for web service is the critical one here. For best practices, the code also has the annotation at line 2, web method. We could actually dispense with the second one. So let me explain how these annotations are used. If you annotate a public POJO class, in this case, ran service, as a web service, it's thereby a SOAP-based service, and all of the public methods encapsulated in that class become service operations. Now, it's best practice to annotate those public methods with web method. A better annotation actually would be web operation. Operation is the more generic language neutral term, but in Java, and for that matter in C#, web method is the annotation used. So there are two of these, one at line 5, another at line 6. A couple of points about these two methods. Notice that they are mutually independent. So for example, next1 does not call nextn or vice versa. Next1, as the name suggests, returns a single randomly generated integer, and nextn returns a list, a Java array of integers. So the two methods are independent of one another, and they also don't depend on any fields. So in programming language terms, these two web service operations are so-called pure functions. They depend only on any arguments passed in. Next1, of course, has no arguments. Nextn has a single argument, which is the number of integers to be generated. In order to keep the cap on that number, the implementation uses a constant called max_rans, currently set to 16, so the greatest number that a client could receive would be 16. So this code is POJO code with a few annotations. It will compile as usual using core Java 6 or greater. Now let's look at the publication options. This working file is called ranpublisher.java. By the way, both the publication code and the service code are packaged up in a jar file for ease of execution, and that's also included among the working files. So to execute, it would just be java-jar ranpublish.jar. We'll worry about a client in the next session. The import at line 1 is for the endpoint class. This is a wonderful utility class that makes it easy in development to publish a SOAP-based service. In production, we'd use Tomcat, Jetty, or the equivalent. Once again, we have a POJO class, in this case ran publisher. Any name, of course, will do. And the critical lines really are two. Line 3 sets a URL. So in this case, localhost, I'm going to run the client on the same machine as the publisher. I pick a port number, easy to remember, but also probably free. 8888 is a good choice. And then a URI, in this case, /rs for RAN service. But any URI would do. A little confirmation message printed to the screen, and the important line then is for endpoint publish. The first argument is the URL. The second argument is an instance of the service. So this is straightforward. This will publish the service indefinitely, so you'd have to kill the publisher at the command line using Control-C or the equivalent. Now, an important point should be made. The very same service, RAN service, can be published with endpoint, but also with Tomcat or Jetty without a single change to the service itself. So there's a very nice separation of concerns here. Writing the service is one concern. Publishing the service is then a different concern, and the Java API makes it very, very easy to separate those two concerns. In this lesson, we're going to focus on the SOAP envelopes that are exchanged between the RAN service, the SOAP-based service we looked at last time, and a client. We'll look at the client shortly. So here is the SOAP-based service. It's packaged in a jar file for convenience. So the jar file contains, again, the RAN service, which is the SOAP-based service, and the RAN publisher, which publishes the service. So let me execute that. Java -jar rand publish.jar. And again, that jar file is in the working files. There's a little printout just to confirm that the service is started. It's listening on the local machine at port 8888. And the URI is RS. Here's another prompt. What I have here is a Perl client. I want to make sure that the first client is not a Java client because I want to underscore that SOAP-based services, like their REST-style counterparts, are language neutral. So let's execute this client, rand client.pl. And the screen is now filled with the SOAP envelopes. They're not formatted very well. We'll look at these in the editor shortly. But all the way down near the end, you can see response is 5777 and so forth. That's the randomly generated value that is returned from the service to the Perl client. I'm now in my Emacs editor, and we're looking at the working file soapenvelopes.txt. This file is a capture of the wire-level activity between the Perl client, which initiates the conversation, and the RAN service, which completes the conversation with a response. I've got some comments started by two sharp signs on the right. From this point all the way down to here is the Perl side, the client side, and from here all the way down to the end is the service side, the Java side. So let's go back up to the top and start. This is a post request. It's the HTTP request start line. The except at the next line, so you see multipart /star, that MIME type covers, in effect, all multimedia types. What the Perl client is saying is, I'm ready to accept attachments. This accept, of course, is for application SOAP, and the Perl client is acknowledging that it understands SOAP. The rest of this we can pretty much ignore. This maybe deserves quick mention. SOAP action. This indicates the operation that's being invoked is next one instead of next n. So there are only two operations provided in that service. At this line begins the SOAP envelope. So this is the body of the post request. So the body of the post request encapsulates a SOAP envelope. And this SOAP envelope is very simple. It has no header. It does have a body, which is required. And down here, this element in effect specifies the operation. Next one as opposed to next n. And you see XSI nil, that's an XML schema data type equals true. What this says in effect is next one takes no arguments. If this were next n, the argument would be a single integer. This line is the HTTP response start line for the response. So this is coming back from the Java service. Most of this, again, we can ignore. The real action is down here with the SOAP envelope. It's formatted slightly differently than the Perl version, and that's because two different libraries are at play, but both libraries are producing standard compliant SOAP envelopes. That's the important part. So the Java envelope, like the Perl envelope, does not have a header. This is such a simple example, one is not required. Here's the SOAP body. This is the next one response, and the return value is 142, so on and so forth. Let me make a point about this value. Notice that it's coming over the wire, of course, as text. And what I want to do now is look at the Perl client to make a point about that text. So here's the Perl client, very straightforward. This line, use SOAPLite, is basically the import of the SOAP library for Perl. Among the dynamic languages, Python, Ruby, Perl, I think it's fair to say, has the best SOAP library. The code is very straightforward. At this line, my $SOAP, so the object reference is $SOAP. We can ignore the Perl syntax pretty much. This is an attempt to connect to the published web service. There's the URL that we've seen before. This next line gets the result, in other words, the response from that web service, and stores the value in a variable called num. That variable is printed out, and as proof of concept, this very last line of the code resets num to whatever that value is plus 100. Perl, under the hood, has converted that text value into an integer value because the Perl SOAP library understands that that value is an integer. We'll get into more details about that a bit later. What we have in this first example is a quick look at the wire-level traffic between the Perl client and the Java SOAP-based web service. And what we'll do now is focus a bit more on how the high-level APIs on both the Java side and on the Perl side are able to disguise this underlying SOAP traffic. Notice no place in the code have we seen any XML or SOAP at all. In this lesson, we're going to look at porting the RAND SOAP-based web service over to Tomcat. So let me begin with a very brief review. The JAX-WS framework, Java API for XML web services, that comes with core Java 6 or greater is very good at separating two concerns. The first concern is to write a web service. In our case, the implementation is webservice.java, to separate that concern from the publication. So in the first example of publication, I use the endpoint class, which also comes with core Java 6 or greater. What we now want to do is move all of that over to Tomcat. So what you see in my bash shell on my Mac are 3 files and a directory. So there's a README, we'll look at that shortly. Build.xml you've seen before. That's the Ant script for deploying to Tomcat or Jetty. Ran tomcat.zip, which is included in the working files, has everything that we're going to see, but it also contains a deployable WAR file. So if you want to follow along through the steps, I think that's advisable at least one time, but the WAR file is already included. And then the source directory contains the artifacts that we need. There are 2 XML files. We'll look at those in a bit. And there's also a jar file called webservices-rt for runtime.jar. That contains the classes that we need to do the deployment. In the RAND subdirectory of the source subdirectory, there's only one source file, randservice.java. We don't need the publisher because Tomcat now becomes our publisher. Let me walk through the steps. I'll clear the screen first. So I'm going to do the deployment, ant-d or name equals, let's just call this rand, any name would do, deploy. The deployment was successful. The question now is, how do we know that it really worked? To do a full-blown test, we would need to send a SOAP request over to the service. We don't want to do that. We want a quick and dirty test. We can use curl. So I'm going to do curl localhost 8080/rand. That's the name of the WAR file. Now I'm going to add a query string, $XSD XML schema document equals 1. What I'm requesting is the machine generated So Tomcat generated XML schema for this web service. I hit return. You can see that the screen is filled with what looks like XML schema elements, and that's exactly what they are. You can see the jar file. Jar, we'll look at its table of contents, rand.war. What you can see in there, if you walk through, are a couple of XML files. We'll look at those in a bit. The jar file that I mentioned before. For convenience, the source code ranservice.java, but also the compiled ranservice.class. Let me now move into my Emacs editor to show you what's included in that zip. So this is the README file. It goes over what I just showed you, so I'm not going to repeat that. Instead, I'm going to go to the all-important deployment file web.xml. So this again is included in both the WAR file and in the zip. Let me emphasize right at the start that this web.xml is generic. It can be used for the RAN service or any other SOAP-based service that we want to deploy with Tomcat or Jetty. There's basically 3 parts to it. Let me go over those very quickly. They're all commented. The first part is this class, WSServlet Context Listener. Tomcat is going to load an instance of this class, and that instance has one job. And that job is to load an instance of the WSServlet that you see here. The WSServlet and the WSServlet Context Listener, those classes are included in the jar file. That's why we need the jar. The WSServlet is the so-called interceptor. In other words, any request that comes for ran.war is going to be forwarded to the WSServlet, which is going to handle it. And that piece of information is provided down here at the URL pattern. The URL pattern /* means rand/*. Now, a request comes in for the RAN service. It hits the WSServlet up here. How does it get to our code? In other words, in this case, the SOAP-based web service implemented in ranservice.class. That's the job of the second configuration file. So let me show you that one, sun JAX-WS.XML. It's a very simple file, and this is the file you would edit per SOAP-based web service that you wanted to deploy. As you can see, the root element is called endpoints, and down here you see endpoint, and it's got 3 pieces of information that are critical. The implementation attribute is the fully qualified name of the service implementation. So in this case, ran.ranService. The name is the name of the class, in other words, without the package. And the URL pattern that we saw in web.xml is repeated here. You can use one and the same web.xml in any deployment to Tomcat, and then you would have a separate sun JAX-WS XML for the particular details, the implementation service, and so forth. Also, because endpoints is in the plural, as it turns out, you could have more than one web-based service in a given WAR file. That would complicate the routing a little bit, so my recommendation is just keep it simple, have a single endpoint in a single WAR file. So, all of the details are included in the zip file, all of the required code, and the deployable WAR file is in there for convenience as well. But if you have the time, you might want to step through the process that I've just gone through, and that's summarized again in the README. In this lesson, we're going to look back at the first SOAP-based example, the RAN service, and use that to draw some conclusions about what's good and what's challenging about SOAP-based services. I have 2 summary documents among the working files. The one you're looking at now is called SOAPReview1.txt, and the companion is SOAPReview2.txt, and we'll look at that momentarily. I'm not going to read through these. I'm going to use these really as a summary of the main points that I would like to make. Let's begin with the upside. If you look at the RAN service, on the implementation side, it's almost trivial. There's a POJO class, RAN service, any name of course would do, and it's annotated as a web service. It contains operations. Those operations are any public method by default but it's best to annotate those methods as web methods. It's good documentation, very easy to do. The really important thing is that those operations should be so-called pure functions. In other words, they should map their arguments to the return value. They should not depend upon fields shared with other operations. So for example, the RAN service has only two operations, next1 and nextn. Next1 can be called independently of nextn and vice versa. In a production-grade SOAP-based service, you would, of course, have more operations, and they might be more complicated. For example, an operation might go against a database, access other web services. All of that is perfectly fine so long as there is no interdependence among the operations. So, for example, next1 shouldn't have to assume that nextn has already been called, or vice versa. Another nice feature of pure functions is that they're thread safe because they don't work on shared storage. A good sign that you have pure functions is that your web service doesn't have any fields that might be shared among the methods. With Core Java 6 or greater, you have everything you need to do SOAP-based services. If you're using Core Java 5, I've left a URL here for you to check out. It's down here. That's the home page to get the required jar file. In the first example, on the service side we have Java, and on the client side we have Perl, and there's not a single piece of XML to be seen anyplace. The serialization to and from XML, in other words, the conversion from Java to XML on one end and from Perl to XML on the other end, is all done automatically. It's under the hood. It's not visible to the programmer. If we need to make it visible, we could. Java has utility classes to do that, but in general, we don't want to see the XML. It's just infrastructure. Now, one question that comes up that needs addressing is, what sort of Java types are serializable? That is, what types go automatically to and from XML? And the answer is very reassuring. All of the primitive types and their wrappers, so for example, both int, the primitive, and integer, the wrapper, string, calendar, that includes date, and even object as a catch-all. You can have arrays or collections of any of these. For example, either straight arrays or array lists, and any programmer type that is reducible to the above. And that covers most of the classes that you and I might write. If there's an example of a Java type that is not covered, and the most famous example of that is the map, so for example, a hash map, it's relatively straightforward to write the serialization code yourself. And in fact, starting with Core Java 6, they have a nice little tutorial in the Java doc about how to do that. In SOAP-based services, the programmer gets to focus on the application logic, not on the serialization to and from XML, which is a tremendous boon. Now, let me look at some of the challenges for SOAP. SOAP is now under W3C control, and it's designed to be transport neutral. This is really an important point, and the reason is this. If you deliver SOAP over HTTP or HTTPS, you get automatically everything that those transport protocols offer. So for example, reliability. If you send a SOAP message over HTTP and it fails to reach the destination, you get a notification. The system automatically will retry, typically up to about 10 times or so before failing. If you're working with HTTPS, you get data confidentiality, encryption and decryption, and so on. But if SOAP is to be transport neutral, that is, if it's to work on any protocol at all, and not necessarily HTTP or HTTPS, for example, something as basic as a named pipe in a Unix or a Windows environment, then things such as reliability and data confidentiality have to be baked into SOAP because SOAP can't rely on the underlying transport. This makes SOAP significantly more complicated. And the example I would use is WCF, the Windows Communication Foundation, which is a framework for server-oriented systems. WCF is essentially a layering on top of SOAP, and it aspires to be, and for the most part is, transport independent. For example, WCF works over UDP, it works over TCP, if you're familiar with those protocols. It also works, of course, over HTTP, but it doesn't require any specific protocol. Java, by the way, interoperates very well with WCF. Both sides have done a nice job in making sure that that happens. SOAP over HTTP, including HTTPS, is straightforward, friendly, and it brings a lot of advantages. When we turn to the client side of SOAP, we'll see even more advantages. If you move to transport neutral SOAP, you're moving into a far more complicated environment. So the examples that I'm going to use will stick with SOAP over HTTP and HTTPS. In this lesson, we're going to move to the client side of SOAP-based services. To that end, I'm going to review a command that you saw earlier, a curl command that was used to verify that the RAN service was up and running. So I'm going to run that command again. You see it in my bash shell. And when I run it, as you can see, the screen fills with XML. That's the XML schema for the RAN service. We'll look at some details later. Let me clear the screen and run a slightly different request against the web service. This time, I'm going to ask for the WSDL, Web Services Definition Language Document. That's the service contract. It includes the XML schema as a part. So let me run that. As you can see, the screen again is filled with XML. We'll look at this in some detail a bit later. First, however, I'd like to put that WSDL to good use. So I'm going to use the WSImport utility. If you have Core Java 6 or greater, this ships with Core Java 6. It's in the bin directory along with the compiler and so forth. -P for package. So I give a package name. I'm just going to use client. Any name would do. This is going to create a subdirectory that's going to be populated with a bunch of Java files. -keep. This makes sure that I get the source code. Otherwise, I'd get only the compiled code, the .class files. And now the URL for the WSDL. Localhost 8080. I'm using the Tomcat publication of the service. rand $WSDL. There's some confirmation messages. Let me now show you that client subdirectory. There's a mix of .class and .java files. We'll talk about the details of those in a bit, but the two important files for us right now are the rand service.java file, that's in the middle of the second column at the bottom, and the rand service.java class. I'll explain why that name came about a bit later. Let me now move to some client code that's going to use what I'm going to call the WSImport artifacts. In other words, the Java code generated using WSImport. I have a client already built called the RAN client. I'm going to compile it. It uses the code that we just looked at, and now, of course, I'm going to run it as proof of concept. So the client has made a call against the RAN service. In the output, you can see the first value returned, -720, and so forth. That's returned from a call to next one. And then the 6 values below that are returned from a call to next n, the two operations in that RAN service. Now let's look at that RAN client code. So this is the working file ranclient.java. And as you can see at line 1, there's an import for client.ranService. That's one of those artifacts created by WSImport. The second line, client.ranService, this is actually an interface, and it too was generated by WSImport. So here's how we put those to use. Down here at line 3, we create an object reference, in this case called port. You'll see later why this name is significant, but any name again would do. And that's created by invoking a constructor to get an object and then invoking the getRanServicePort method on that object. And I'll come back and explain this idiom in more detail a bit later. Once we have the object reference, it's all smooth sailing. So for example, at line 4, here's a call to the next one operation. And down here at line 5 is a call to the next n operation, and then a little for loop to print out the values. The thing to notice again is the obvious. There's no XML, let alone SOAP XML, visible anyplace here. All of the serialization is done under the hood. Most of the code has been generated for us by the WSImport utility. So what we're going to do in forthcoming lessons is take a closer look at the WSDL and use that to get a better sense of exactly how this client code is organized. In this lesson, we're going to focus on the excellent support that Java provides on the client side for SOAP-based services. In the last lesson, we had a quick look at the WS import utility, shown here in this first bulleted point, and this utility goes against the WSDL provided with the SOAP-based service. The WS import generates a bunch of classes that the client can use to contact the service. In the case of the RAN service and the WS import utility, the generated classes of interest are shown below in three groups. So you see next1.java, that represents a request to the next1 operation. Next1 response, of course, is the corresponding response that comes back. Next_n is the request. Next_n response is the response back from the service. Now, in effect, these four classes could have been produced with the XJC utility that we saw much earlier. In other words, these four classes are produced from the XML schema that comes with the WSDL document. With WS import, you might say XJC, the utility we used earlier, is under the hood. There are two additional classes of interest. RAN service is an interface that describes the invocation syntax for the next1 and next_n operations, and RAN service, we'll talk about the peculiar name a bit later, is an implementation of that interface, and it provides some additional details. Now, there's a very close connection between the classes generated, in this case these six, and the WSDL. But before we jump headlong into the details of the WSDL, it's XML, it's not very pretty, it will be useful to have an overview. So this working file is WSDLuse.txt, and the companion file I'm going to move to right now, and that's WSDLoverview.txt, and both are included, of course, in the working files. So here's how the WSDL is structured. For the RAN service, it's going to be, just to give you a sense of the size, about a page total, and the XML schema, which is a bit extra, is going to be another 1/2 to 3/4 of a page. So let's say ballpark, the whole thing is about 2 pages of text. So the WSDL begins with a definitions element, that's the so-called root or document element, and then there are 5 sections that occur in this order. So the first section is called types. This is basically the XML schema. The thing that's really of interest to us is that the XML schema provides data typing for the messages themselves, and we'll see that in some detail a bit later. The messages section is simply a listing of all of the messages that occur in the type section. So it's just an inventory, if you like, of the messages. The port type is very close to what a programmer would call an interface, so it provides lots of general information about the service. Of most interest to programmers is it explains what I'm going to call the conversational pattern. That is, it explains which side, service or client, generates which messages and in which order. So for example, let's take the RAN service. The RAN service follows the request-response conversational pattern. The client initiates the conversation with a request. The service processes that request and responds with another SOAP envelope. In the WSDL, you're going to see, for example, in the case of the next1 operation, the next1 operation or the next1 message is going to come first, and the next1 response message is going to come second. So the order is clear. The binding section is, in theory, the most complicated. It provides, in effect, implementation details that are absent in the port type section. In a modern WSDL, there's really only one item of interest in the binding section, and that's the transport layer. So for example, for the RAN service, as we're going to see, the transport is abbreviated as SOAP over HTTP. In other words, the transport is HTTP, but it might be something else, SOAP over TCP, or SOAP over some proprietary protocol. In theory, you also might have one binding for SOAP 1.1 and a different binding for SOAP 1.2, but this is unusual. In theory, then, you could have a number of binding sections, but typically there's only one. Finally, the service section puts everything together. it combines, you might say, all of the above to define the service, and that's done with so-called port elements. And a port is simply a port type, if you like, an interface, plus a binding, if you like, an implementation. As many bindings as there are, there will be exactly that many ports. For the RAN service, there is one binding, hence one port. There is always only one port type. So the only multiplicity you'd ever have would be in the bindings. This general view of the WSDL will help, I think, when we get into the details, and we're going to do that in the next lesson. In this lesson, we're going to focus on the WSDL, the service contract that's provided typically for every SOAP-based service. In general, there are two ways that you might get a WSDL. One is somebody might write it from scratch. That's unlikely anymore. There are utilities that generate the WSDL dynamically. So, for example, if you publish a SOAP-based service with either Endpoint or Tomcat or Jetty, those publishers will generate the WSDL automatically. That WSDL might be hand-tweaked to get some features that aren't in the machine-generated version, but mostly programmers allow the WSDL to be generated automatically. This is sometimes called the code-first approach to WSDL generation. The alternative would be called contract-first. So we're going to use the machine-generated WSDL, and the way you can get it, quite simply, is for any SOAP-based service, you can provide in Java the name of the WAR file, and then as a query string, $WSDL. We've seen this before, but let me show it again for review. And you can see the screen is now filled with XML, and this XML is part of the WSDL. Recall that the WSDL includes as a part an XML schema, so I'm going to move into my Emacs editor to look at the first of two working files. The first working file is rand-schema.xml, and it's basically the schema for the RAN services WSDL. It's very similar to schemas that we've looked at before. I've deleted some parts and left basically the parts that define the next N operation. This operation is the most interesting because the next N operation takes an argument and returns a list. There are two messages associated with this operation. You see the cursor in front of the first one. It's called next N. That's the request message that goes from the client to the RAN service. And the other SOAP message is next N response, and that, of course, comes back from the service to the client. So let's look at these in order. For the next N operation, there's a single argument. You can see it's called arg0, and the type is xs:\int. The xs: underscores that this is an XML type. It happens to have the same name as the Java primitive type, but this xs:\int is an XML schema data type. It's going to be mapped, of course, to the Java primitive int. The response message is a bit more interesting. So its name is called return. In the SOAP envelope, the element will be named return. Once again, the type is int, nillable equals true. This is a rather indirect way of saying that null in Java terms might be returned. In other words, what you're going to get back from the RAN service in a next N response is an array or the equivalent. For example, an array list, and either one of those in Java could, of course, be null. The minimum occurrences is 0. This would be the case if the response were null, and the maximum occurrences is unbounded because we don't know how long the list might be. Might be 2, might be 200. So the schema data types the messages. In this case, next N and next N response. The parts I've omitted up here are the similar definitions for the next one message. That's the request for a single randomly generated integer, and the next one response, which sends back a single integer. Now let's look at the full WSDL. So I've eliminated some parts but left others just to give you the feel. So as we saw earlier, the outermost element, the document element, is definitions. Then comes the types section. In Java, there's a link to the schema. We just looked at that. Then there's the message section. It's not so interesting. It's just an inventory of all of the messages. So what I've shown here are next N and next N response, and I've deleted next one and next one response. The port type is the section that we want to focus on a bit. In programmer terms, this is close to what we would call an interface. What it defines are the operations exposed in the service, and it defines those operations in terms of the messages listed above. Here's the next N operation. That's the request. It consists of two messages, an input and an output. Input is always from the perspective of the service. So this is a request message, the input message, and this is the response message, the message that goes back to the client. Because of the order, the pattern here is request response. Where the output message first and the input message second, you would have a pattern called solicit response. Request response is the dominant pattern in SOAP-based web services. The binding section contains implementation detail. In a modern WSDL, the most important part of the binding is shown right here. It's the transport. So you can see here the transport attribute ends with SOAP/HTTP. So this is SOAP over HTTP. It might instead end with /SOAP TCP/SOAP SMTP. That would be email, and so on. By default, this is a SOAP 1.1 binding. In Java, you typically have only one binding, but you could have more than one binding. The service section puts it all together, and as noted earlier, in the service element are port sub-elements. And the basic idea is this: you'll have as many port elements as you have bindings. So in this example, there's a single binding section right up here, hence there's a single port. The port is conceptually the port type plus the binding. The most important element of the port you can see right here, SOAP address location. So this is the so-called service endpoint. It's the URL at which the service can be reached. XML is not something that we like to look at, let alone study and ponder over, but I think you can see that the WSDL is not particularly bad. Conceptually, it's well organized. You have data types. Those data types apply to messages. Those messages are put together in the port type section to create the operations. The operations, in turn, are bundled into a service, and that service has an endpoint, a URL, at which you can reach it. That's our relatively quick tour of the WSDL, including its embedded XML schema. In the next lesson, we'll put these again to good use by looking at Amazon. In this lesson, we're going to bring together a lot of the information discussed in the two previous lessons, and we're going to do that by focusing on a client against the SOAP-based version of Amazon's e-commerce service. So to that end, I have a terminal opened, and you can see the command java -jar Amazon client soap.jar. That jar contains all of the required code and, for convenience, all of the source code, and we'll be looking at some of the source code shortly. My credentials are in a text file called creds.txt. That is, that file holds my access ID and my secret key. So let's run the demo and hope for the best. So the request was a success. What I got back was a list of items, in particular books, either by or about Jane Austen, and you can see the numbered list on the screen. I took the default number, which is 10, but we could have got many more. What I'd like to do is turn to the first of two working files in order to get a sense of how I got here. Let me open up Emacs again, and this working file is called Amazon soap.txt. What it does is reviews the steps that I went through. Amazon exposes a WSDL for its SOAP-based e-commerce service. You see the URL here. So I ran ws import -p. Again, this creates a package. I just called the package Amazon. The -keep keeps the source files, and then the URL is at the end, and this generates about 90 .java classes. And these classes include things that would be familiar to anybody who's visited the Amazon website. For example, there's a cart create class, an item search request class. I use that in this application. An item search request, also used. Items.java, also used. Similarity lookup, I don't use. To invoke the client, here then is a review. It's all packed into a jar file for convenience, java-jar, and so forth. And here's a slightly better format of the output from a sample run. The first 10 items returned from the request. Once again, as in the earlier examples, the JAX-B serialization occurs in the SOAP libraries. We don't see any of that. Now let me bring up the second of the two working files. This will give us a little better sense of the code structure. In particular, I want to talk about the code that I had to write. So from WS import, we get roughly 90 utility classes, and now I write two more. The first I call the Amazon Client Bear Style. This reflects a Java naming convention. For SOAP-based services on the client side, Java will create clients in one of two styles. The Bear style, which is simpler, which is why I'm using it, and they also have something called the wrapped style. Let me underscore that these styles refer to the client side, in other words, to how the client requests and then processes the response back. The service itself, of course, is under Amazon's control. I can't do anything about that. The Amazon Bear Style class contains main. It creates an item search request object for books by or about Jane Austen. It wraps this up in another one of those WS import classes called item search. My code then invokes item search. So this is one of the operations exposed in the e-commerce web service. What we get back from Amazon is once again a list of lists. So for example, in this case, we ask for books by and about Jane Austen, but we might ask for movies and records and many other things. So we'd get a big list, and in that list would be other lists of the items. We'll see that more clearly when we get to the actual code. There's a second class that I had to write. I call this AWS Handler Resolver. I'll get to the meaning of that very strange name a bit later. This is the counterpart of the request handler class used in the REST-style clients against Amazon. Amazon is very, very fussy about how it wants the request formatted, and rather than keeping all of that up in the main class, Amazon Client Bear Style, I put that all down here in AWS Handler Resolver so that this class could do all of the grunt work. The interesting thing for us about this particular class is it actually has access to the outgoing SOAP request, and so it can format it in a way that Amazon requires. That's an overview of how the client works, preceded, of course, by a short demo. In the next lesson, we'll look at the code, in particular, these two .java files. In this lesson, we're going to focus on the code that I had to write to get the client to work against the SOAP-based version of Amazon's e-commerce service. Most of the source files were generated with WS import, but I had to write a couple of class files myself, and we're going to look at those shortly. First, though, I'd like to do an overview to explain why these files were written. So the framework we're using is JAX-WS, that's the official name, Java API for XML, Web Services, and Web Services in this context connotes SOAP-based web services. In this framework, there are two levels at which you can work, on either the service or the client side. So far, we've been at what might be called the application level. At this level, on the service side, you would define a service with the @WebService annotation, and then define the methods that the service exposes. Each of those methods should have the @WebMethod annotation. On the client side, what you would do is invoke the operations that are exposed by the service. The really good news on both sides at this level is that the SOAP is 100% hidden. We don't deal with it at all. Now consider this scenario. Suppose I'd like to write a client against a web service that requires me to send a digital certificate for authentication in the header of the outgoing SOAP envelope. In other words, my request has to be a SOAP envelope whose header contains my digital certificate. This means that I have to have access, of course, to the SOAP message, and the handler level provides exactly that access. So there are two types of handlers. One is called the SOAP handler. It has access to the entire SOAP message, the headers, the body, and even, if needed, the attachments. A more restricted type of handler is the logical handler, which has access only to the body. Now, in the case of Amazon, as we saw in the REST-style services, Amazon is very fussy about how a request is formatted, and this carries over to the SOAP-based version. So in particular, Amazon wants a timestamp and a hash value generated using my secret key to be placed in the body of the SOAP request. This means I need access to the SOAP message. So now I have to deal explicitly with the SOAP, and I'm going to use a handler to do just that. So let's look first now at the application level code. This working file, by the way, is called handlers.txt, and it just gives us the overview. So I'll now move to the second working file, which is Amazon client bearstyle.java. I've excised some of the parts that we don't care about, the imports and so forth. All of the lines 1, 2, 3, and so forth there on the right in the documentation, those all represent application level code. So we instantiate a service object. The classes, by the way, are part of the WS import generated artifacts. This next line registers the handler. We'll look at that code momentarily. Line 2 gets an object reference that's going to let us make calls against the service. Now, starting at line 3, things become, I think, pretty intuitive. We create an item search request. It's empty. And then we set some properties. We're interested in books. We're interested in books that contain the keyword Austin. At line 4, we create an empty item search object. We set our access ID. That's our public ID. So there's no reason that this should be kept secret. This is our name for Amazon. The associate tag Amazon wants, this is the name I used to register with Amazon. By the way, I found I could use anything. I could put foobar in there, and that would work. And then finally, what we do is get the current request, and whatever that is, in this case, it's empty, and add our new request, the request from line 3. We're now good to go. So we invoke the item search operation on the Amazon side. We get a response, very nicely named item search response. We grab the items in that response. Again, we're dealing with a list of lists. In our case, we basically just want a list of books, but it might be a list of books and a list of movies and so on. There are 2 for loops. The outer for loop goes through the outer loop, and the inner for loop then iterates over the inner loop, and all of the action in this case is in the inner loop because we asked only for books by or about Austin. Now, if you come down to line 10, this style of Java is very familiar to all of us because it's the property idiom. So you see item, that's the current item, one of the 10 books. Get item attributes, get title, and there's, of course, get publisher, get price, all of that sort of thing. So if you look at this application level code, you can see there's not a hint of SOAP, and it's relatively high level, and that's completely appropriate. Now let's take a look at the handler code. So that's in a file called AWS handler resolver.java. That's also included in the working files, and we don't have to look at all of it. Some of it's pretty grimy, but I want at least to give you the sense of what's going on. So at line 1, this method called getHandlerChain. So I need to define that because that's the method in the handler resolver interface. What that does is it registers my handler with the SOAP runtime. So conceptually, what's going to happen is on the client side, the SOAP library will build a SOAP request envelope. It'll then pass that SOAP envelope to my handler, and then my handler can tinker with it before it goes out over the wire to Amazon. All of the action occurs here in a method called handleMessage, and the argument, the SOAP message context, allows me to get everything that is known about the outgoing SOAP message. The first thing I do, of course, is check which direction we're dealing with. Handlers are inherently bidirectional. So an outgoing message is caught by a handler, an incoming message is caught by a handler. I care only about the outgoing. That is the request, not the response. My handler doesn't need to do anything in the response. My application level code will handle that. So if this is outbound, at line 3, I'm grabbing the SOAP message. At line 4, I'm creating the kind of timestamp that Amazon wants. The full source code is available in the jar if you want to look. And then here I'm creating what Amazon calls a signature. Technically, it's not. A signature is encrypted. What Amazon is calling a signature is really a hash value generated from my private key. So my private ID or key does not go over the wire. Instead, I create a hash value using that key. It's got to be done in a precise way, and I send that to Amazon, and Amazon verifies that. Amazon wants the signature to be first, and then the timestamp, so I put those things in that order. It's pretty clear that this handler code is much lower level than the application level code, and this is one of the things that I find most attractive about JAX-WS. If you don't need to get at the SOAP level, you can stay at the application level where we were before, and it's very nice. If you need to get at the SOAP level, you have the ability to do that as well. This lesson takes a look back at the different clients we've seen against web services and tries to do some comparisons and contrasts. The working file you're looking at is called clientwrapup.txt, and it contains a summary of the main points. So let's start with something that's pretty obvious. You'd expect clients against REST-style services to be different from clients against SOAP-based services, and of course they are, and we'll get into some detail in just a moment. But even inside of REST-style services, there's variety, and we've seen two general approaches. The first approach is exemplified by the Perl client against the RAN service. So that client, you'll recall, makes a request, gets an XML document in response, and then does an explicit parse using XPath. XPath does a tree-based parse, so it's a variant of the so-called DOM parse, and Java as well has an excellent XPath library. One way to extract the information from the response document is to do an explicit parse. The exception to all of this are JavaScript clients that receive JSON documents, because JSON documents are just textual representations of JavaScript objects, so in effect, the parsing is done automatically. But we're interested in Java clients, of course. That's our primary concern. So a Java client can do an explicit parse. We've seen that in the case of the Java client against the Amazon RESTful service. But there's also a second approach, and that's to use JAX-B in order to unmarshal a document into a Java object. And then, of course, once we have the Java object, we can just use the normal Java programming idioms, get this, get that, get the other thing, in order to extract the desired information. There are some preconditions, however, for this JAX-B approach. For one thing, the service has to publish an XML schema or the equivalent. The major services out there, I'm thinking now of Amazon, eBay, Facebook, Twitter, Tumblr, and so on. The major services all do provide the required XML schema, and we've seen the XJC utility that ships with Java does an excellent job of creating Java counterparts to those XML data types. On the client side, some of the Java frameworks, I'm thinking in particular of JAX-RS, are on the way to automating an awful lot of this, so that the XJC step, for example, can be done automatically. When you're doing a REST-style client, there is some involvement with the XML or JSON. If you're a Java client, there is going to be either the explicit parsing or the JAX-B unmarshaling. Now let's move to the SOAP side. SOAP-based services are further from the HTTP metal than their REST-style counterparts. That's a given. So you'd expect that the SOAP-based API would be a bit higher level, and I think it's fair to say that it is. In particular, on the SOAP side, the WS import utility that Java provides is just wonderful. It will read a WSDL, will generate automatically all of the required Java artifacts. So we've seen this in the case of the client against the SOAP-based Amazon e-commerce service. It's a very, very powerful service. And once you do the WS import thing, dealing with the information sent back from Amazon is relatively straightforward because you're dealing exclusively with Java. In effect, the SOAP has gone away. The JAX-WS framework, so the framework for doing SOAP-based services and clients against them, does allow tinkering with the SOAP messages if this is required, and we saw this in the handler example. So all in all, there is in web service clients, as in almost every other part of Java, great variety. You can go the REST-style route in your service, in which case you still have some options on the client side on how to approach that service. With SOAP-based services, the same thing holds. In this lesson, we'll take a first look at security. Security is a topic that cuts across web services. That is, it cuts across the REST-SOAP distinction. It cuts across the client-service distinction. So to that end, you're looking at a working file called security-overview.txt, and we'll also be looking at some slides shortly. For an example, what I want to do is consider a conversation between Bob and Alice. These are names that are typically used in security examples. And Bob and Alice are going to exchange messages over a communications channel, for example, over an HTTPS channel. Now, security has basically two fundamental levels. The first I'm going to call the wire level. It could also be called the transport level. We'll come back to that in just a moment. And the other level is characterized in general as users, roles, security. And that's a phrase that's used everywhere in the computing disciplines. So let me go back to wire-level security using HTTPS as an example, and we'll get into exactly what the S means later. It does mean, of course, secure, but we'll get more specific. So at the wire level, there are three basic services that a security provider should furnish. The first is known as peer authentication. Sometimes this is described as mutual challenge, and the idea is pretty fundamental. Bob needs assurance that he's communicating with Alice. Alice needs assurance that she's communicating with Bob. So each needs to authenticate himself or herself to the other. Confidentiality is the next service. So the messages passed back and forth between Bob and Alice should be encrypted just in case there's an eavesdropper on the line. Finally, there needs to be assurance that the message sent from one side is the same message received on the other. Now, in general terms, the first of these, peer authentication, is the toughest challenge. We'll get into details in the next lesson. Confidentiality and integrity in modern systems are pretty sound. Now let me turn to users' roles security. As noted here in the first sub-bullet, this is a two-phase process, the first phase being required, the second being optional, and the first phase is called user authentication, not to be confused with peer authentication, and this is familiar to most of us. So for example, if I go to a shopping website such as Amazon and I want to place an order, they ask for my email, that's my identity, and then they ask for a credential that vouches for that identity. And the credential, of course, is typically my password. I'll come back to that with the Amazon example in just a second. The second optional phase is known as role authorization, and the idea again is intuitive. If I log into Amazon, I'm allowed to place an order, but unfortunately, I am not allowed to set the prices. So Amazon does that. I don't have the security role that would allow me at Amazon to change prices. Now, let me take something that we've already seen. Let me talk about this user authentication with respect to Amazon, because we've seen 3 Amazon clients so far, 2 in REST, 1 in SOAP, and under the hood, they all do basically the same thing. So when I register with Amazon, I get an access ID, so that's my identity, and I also get a secret key, and the secret key is what I use to create a credential that vouches for that identity. So let me get specific. In the 3 clients that we've seen in the code under the hood, the client creates a 160-bit hash value using my secret key. The important point is made in 2. That is, it's this hash value and not the secret key itself that travels over the wire. This hash value is known in security jargon as one-way secure. That is, even if a bad guy gets the hash value, and even if the bad guy knows the particular algorithm used to create that hash value, the bad guy is not able Well, statistically, it's improbable that the bad guy could use that information to get the secret key. Finally, Amazon on the receiving side has, of course, a copy of my secret key, and it uses that secret key on the same data to regenerate the hash value, and then it simply compares the two. If they're the same, it takes my credential as legitimate. If they're not the same, Amazon basically refuses the connection. Now let me try to summarize these points using two simple slides. The first slide has Alice and Bob again, and the idea is that Alice intends to send a message to Bob. Eve is the typical name used for the eavesdropper. So the first thing that has to happen is Alice must be assured that it's Bob rather than somebody else on the other end, and Bob needs to be assured that it's Alice rather than some imposter on the other end. So this is the peer authentication or mutual challenge phase. Once Alice and Bob are assured of the identity on the other end, they can start exchanging messages. So Alice sends a message to Bob and encrypts the message so that even should an eavesdropper such as Eve intercept the message, Eve is going to have a very, very difficult time. Basically, a computationally intractable task of deciphering that message. Finally, Alice and Bob both need to be assured that the message that Alice sends is the same message that Bob receives. And that's the integrity service that the security provider should furnish. Now let me move on to the second slide. This slide summarizes users' roles security. So let's start at the right. So suppose I'm going into a pay-for web service. The secured resource might be the entire service. It might be certain operations within that service. So for example, some aspects of the service, a list of products to buy, for example, might be publicly accessible, but ordering. So the ordering operations, for example, in an e-commerce service, those might be secured. So the idea is to get to the secured resource, I have to go through at least user authentication and perhaps role authorization as well. So to do that, on the left, I provide an identity. So for example, a username, an email, whatever, together with a credential. And the simplest credential, the most familiar one to all of us, of course, is the password. The user authentication phase then checks that credential. If I get through that, the second optional phase is role authorization. This is typically done through a database lookup or the like. In other words, the service in this case is going to check to see if I'm authorized to perform whatever operation I want to perform. For example, am I allowed to place an order? Yes. Am I allowed to change the price on the thing I'm ordering? No. This first look at web services security will now lead to a division. So what we'll do to begin is we'll focus on wire level security. And once that's in place, we'll come back and look at users' roles security. In this lesson, we're going to focus on wire-level security. So let me begin with a short demo. You can see in my bash shell, I'm about to run a Java program called Google Client. This client makes a GET request against Google, but it uses HTTPS instead of HTTP. As part of the peer authentication phase, so that mutual challenge phase, Google is going to send my way 3 digital certificates. These digital certificates are, in effect, vouchers for its identity. We'll get into some detail in a bit, but let me begin by running the demo. So you can see that the status code return is 200. That signals, as usual, a successful GET request. Then you see Cipher Suite, and there's an inscrutable looking phrase on the screen. We'll go through that in some detail momentarily. The short version is that this summarizes all of the algorithms at play in setting up this connection. What then follows is some information about each of the 3 digital certificates. You can see, for example, that the type of each certificate is X509, and that's basically the current standard for digital formats. You see a hash code, that's sometimes called the fingerprint, The algorithm in all cases is RSA. This is a well-known algorithm, public key algorithm. More about that later. And then the certificate type and the format turn out to be the same. Now, let me move to one of the working files. This is called wire-level.txt, which basically does a summary of what's happening. So let me start with the digital certificate, which plays such a central role. This, by the way, will be our first, not our last look at the digital certificate. So for our purposes, there are really three fields of principal interest in the digital certificate. The first is this. The certificate contains a public key from a key pair. For right now, I'm just going to depend on your intuitions about key pair, although we will get into details about that as well. So the public key, as the name suggests, is a key that I would feel free to distribute. Amazon has a public key. I can have a public key. It's basically an identifier. There's a digital signature from a so-called certificate authority, abbreviated as CA, and well-known certificate authorities include RSA. We've just seen that from the algorithm, and VeriSign. Basically, a digital signature is an encrypted hash value, and as the name suggests, it's meant to be the counterpart of a physical signature that you or I might use. The important thing is that digital signature is a voucher for the public key. So in effect, on the Google digital certificates, there's a signature that vouches that those certificates are in fact identifiers of Google. Finally, there's a hash value, usually called the fingerprint, that identifies each certificate. So each certificate is going to have its own fingerprint. Now, there's some other fields of interest. In particular, there is a from and to. So, for example, a typical digital certificate might have valid dates that span 3 years, let's say. But you could have ones that are longer, ones that are shorter. Now, here's the gist of the role that the digital signature plays. During the peer authentication phase, which is basically the first phase in the so-called HTTP handshake, one side, so in my case, this is my Google client program, is going to challenge the other side, in this case, let's say the Amazon web server or the Google web server or whatever, to produce one or more digital certificates. As it turns out, Google is not going to challenge my client. Amazon wouldn't either. And again, we're going to let that pass for now. So the peer authentication turns out to be one-way authentication. It's basically the server, Google, authenticating itself to us by sending us 3 certificates. Now, in order to validate that certificate, the challenger, so my Google client program, needs to check that certificate against what's called a trust store. And as the name suggests, a trust store is just a list of all of the digital certificates that the challenger trusts. As it turns out, Java, core Java, ships with a default trust store. You see it down here. It's Java Home, JRE, Lib, Security, CA Certs, Certificate Authority Certificates. So that's the default trust store. It's basically just a file, in this case, on the file system. One important point is this. The verification of a certificate might be indirect. Suppose, for example, that this is a fresh computer. I've never done an HTTPS connection against anybody, and I go the first time against Google, and let's say my default trust store does not have a Google certificate. However, the Google certificate has a digital signature from, let's say, RSA. RSA has a digital certificate. So basically, what would happen in the verification is that the signature would be verified, and if the signature turns out to be legitimate, we assume that the digital certificate on which it occurs is also legitimate. So the long and the short of it is, on my side, the client side in this case, all 3 of those Google certificates are being verified against this particular trust store. Now, as noted, and as the name emphasizes, in peer authentication, each side typically challenges the other, but when you hit traditional websites such as Google or Amazon, typically the peer authentication turns out to be one way. The client challenges the server, but not the other way around. In web services, by contrast, it is common to have genuine peer authentication. Each side needs to provide a certificate, at least one, to verify its identity to the other. In this lesson, we're going to take a close look at the source code for the Google client. First, however, I'd like to review the distinction between a key store and a trust store. So let me bring up a slide. Now, a key store contains my digital certificates. So for example, if I'm being challenged by a peer, I send one or more certificates from my key store, my repository, to the challenging peer, and the challenging peer then does verification of those certificates. By contrast, my trust store is a repository of the digital certificates that I trust. So when I challenge my peer and get certificates back, I compare those certificates against the contents of my trust store. The difference between the key store and the trust store has to do with functionality, not format. So for example, one and the same file could serve both as a key store and as a trust store. With core Java, you have a built-in trust store. It's called CA certs, as we saw last time, but you don't have a built-in key store, and we're going to have to create one eventually. Now, with this distinction in mind, let's turn to the source code. Let me bring up my Emacs editor, and the file you're looking at is called Google Client Short.java. The full running client is Google Client.java. Both files are contained among the working files. So let me make a couple of points, then we'll get to the core part of the code. You can see at line 1, we're going to be using something called the HTTPS URL connection. It's a subtype of the URL connection that we've seen earlier. And at line 2, you can see the endpoint. It's got HTTPS as the so-called scheme, and you can see the port number at the end is 443. That's the standard port number for servers to accept HTTPS connections. Down here at line 3, we open the connection using a URL once again as the object reference. And here basically in the comment, you see the output from a sample run. Now I'm going to return to the Cipher suite momentarily. The line above it, you see the status code is 200. So the client sends a GET request to Google over HTTPS, gets back 200, the standard OK for a GET request. And the first line of output is something called the Cipher suite. The short version is this is a list of all of the algorithms that are in play. Of interest right now are the 3 certificates that Google sends back. So each of these certificates needs to be verified against my trust store. And in this case, my trust store is the default one, CA certs under JRE-lib security. Now, let me come down to the Cipher suite, which I've repeated here just for convenience, and talk a little bit about these acronyms. So the first one, TLS, stands for Transport Layer Security. So that's the S in HTTPS. This is a derivative of the earlier SSL from Netscape, Secure Sockets Layer. You'll sometimes see TLS and SSL used interchangeably. The next algorithm is quite a mouthful, elliptical curve Diffie-Hellman key exchange. This is essentially the handshake algorithm, and the handshake is the process that the client, in this case the Google client code, and the server, in this case the Google server for the home page, this is the process they go through to establish an HTTPS connection. We'll come back and study that in some detail. RSA, named after 3 researchers who started this company, is the public key cryptography algorithm. Basically, it's the algorithm used to create a key pair, which consists of a public key, which is on the certificate, and a private key, and we'll return to that as well. AES 128 GCM, another mouthful. The AES stands for American Encryption Standard, and the GCM stands for Galois Counter Mode. The 128 is the size of the encryption key used to encrypt messages that go back and forth across the wire. We'll return to that as well. And SHA-256 is the hash value algorithm. This algorithm is used for integrity. In other words, an outgoing message has a hash value attached. On the receiving end, that hash value is recomputed and the two are compared. If they're the same, we assume that the message was received intact. If not, we assume there's a difference between the sent message and the received message. Sometimes this hash value is described as a fingerprint, although that can be a little bit misleading. Now, down here in the dump details utility method is where the printing occurs. So as you can see, the connection is passed in as an argument. We get the response code. Down at line 4, we get the cipher suite. That's what we just looked at. And then we iterate through the certificates that Google happened to send. So Google, and this is not uncommon for commercial sites, sends us 3 digital certificates. In the minimalist case, you might send back only 1. In this lesson, we're going to focus on the HTTPS handshake. And after we've gone over the handshake, we'll be in position to configure a production-grade web server such as Tomcat to accept HTTPS connections. So let me begin with 2 slides that contrast 2 different approaches to encryption and decryption. The first approach is sometimes called single key or symmetric, and the idea is this. If you start over on the left, you see plain bits. These are unencrypted bits. So for example, the bits that make up a message sent from a client to a server or in the other direction. These plain bits are put through the encryption engine. They're one input. The second input is a numeric value, the single key, which is used to transform those bits into cipher bits. Basically, this is an arithmetic computation. The cipher bits then are the encrypted bits, and on the receiving end, they go through the decryption engine using, and this is the critical point, the same key that was used earlier to do the encryption. And of course, if all goes well, you recover the original plain bits. Now, let me contrast this with a second approach. This is called asymmetric, or more commonly key pair encryption and decryption. And the picture is a bit more complicated because now we have 2 separate keys. For example, a public key from a key pair and a private key from a key pair. The public key, if used for the encryption, requires then that the private key be used for decryption. It's possible, by the way, to encrypt in the other direction. In other words, to use the private key for encryption, in which case the public key would have to be used for decryption. Now let me go back to the original. The single key encryption-decryption has a tremendous advantage. It's roughly 1,000 times faster than the alternative. The problem is what people call the key distribution problem. In other words, if I'm the client side and I have the single key, how do I get that key over to the other side without having it intercepted? This is basically the key idea behind the handshake. So let me now bring up my Emacs editor, and this working file is called handshake.txt. It gives us the short version of the HTTPS handshake. So recall from the last lesson that the underlying algorithm is this, quite a mouthful, ECDHE. By the way, this is normally abbreviated simply to Diffie-Hellman, the 2 researchers who came up with the algorithm. Now, I'm going to focus only on the client side. If there's true peer authentication, in other words, true mutual challenge, then basically you would have challenges going both ways. Okay, step 1 then is this. The client, so the Google client code we saw earlier, or a browser, challenges a server. So we'll assume this is the Google web server. And the web server responds with 1 or more digital certificates from its key store. The client then uses its own trust store to verify these digital certificates. If the certificates are verified, we continue. If not, we're done. In the third step, the client generates what's called a pre-master secret. So typically, browsers nowadays will generate a 48-bit value. It has certain cryptographic properties. We don't care about those so much. The pre-master secret is going to be used to generate the single key on each side. Now the trick, and this is the critical step 4, the trick is to get that pre-master secret over to the other side so that it can't be intercepted. To that end, the client uses the public key from one of the digital certificates it got from the server. So you'll recall that Google actually sent 3. So the client picks one of those public keys from a digital certificate, and it encrypts the so-called pre-master secret before sending it to the server. The server will then use its private key to decrypt that secret. Now at this point, life is good. The client and the server have the same pre-master secret. They've already discussed, in effect, the algorithms that are going to use to do all of this. So they use that pre-master to generate the secret key, the single secret key. And in the web, this is typically described as the session key. So in the example that we saw, that session key is going to be 128 bits in size. This is configurable. You might have a 256 or a 512-bit session key. At this point, the session key is going to be used on both sides to encrypt and decrypt messages, and this would be significantly faster than if the two sides were to use public key encryption. By the way, at any point, if either the client or the server suspects that a bad guy has somehow come into play, either side can ask that the handshake be repeated. So for example, either side could say, in effect, I think we need a new session key. Let's do the whole thing over again. Exchange certificates and all of the rest of it. Now, with this wrap up, we have enough information to talk about something very practical, that is how to take a web server such as Tomcat, which comes out of the box ready to do HTTP, but not ready to do HTTPS. So we'll take this background information and we'll apply it in the next movie to configuring Tomcat. In this lesson, we're going to look at how to configure Tomcat for wire-level security. In other words, how to make Tomcat accept HTTPS connections. I'm going to start with a demo. As you can see, I have a browser opened, and up in the browser URL window, there's HTTPS crossed out. That's a caution from the browser. Localhost 8443. 8443 is the default port number that Tomcat uses for HTTPS. Now the browser is very unhappy because my digital certificate is not signed by a legitimate certificate authority. This is called a self-signed certificate. We'll talk later about how I got it. So this is the certificate that Tomcat is providing to the browser when the browser does the peer authentication challenge. And the browser, rightly so, thinks this certificate is worthless. So I'm going to go into advanced, and I get some more caution from the browser, but in the end, I'm going to say, no, please go ahead anyway. And as you can see, the standard Tomcat welcome page pops up. So Tomcat is now up and running. It will accept HTTPS connections. It will also accept the old HTTP connections. So we haven't turned anything off. All we've done is turn something else on. So let me just type that in quickly for confirmation. So there's the HTTP connection, and we just looked at the HTTPS connection. Now let me step through what I did in order to make this configuration work. So I'm now in my Emacs editor. We're looking at the working file called config.tcat.txt. It's included in the working files. So let me begin with the most important step. We need a digital certificate so that Tomcat can send that down to any challenging client. There's a variety of tools that can be used to create such a certificate, and Core Java ships with one of these. It's called KeyTool. So the command I use is shown here. KeyTool, and then you see some flags. Generate key pair. The algorithm I'm using is RSA, and I want the resulting digital certificate stored in a file called tcat.keystore. Any name, by the way, would do. Now, what's going to follow is an interactive session. I'm not going to show you all of that, but the key tool utility is going to prompt me for various pieces of information, my name, my organization, the city in which I live, and so on. It's also going to ask for a password, which I give it. I'm using qubits as a password. And when the session is done, it just takes a minute or so to walk through the entire process. We're going to have a file called tcat.keystore, and that's going to contain the self-signed digital certificate. Now the next step is to configure Tomcat. So Tomcat's main configuration file is contained in a subdirectory called conf, and the name of this file is server.xml, and right near the top, so maybe a quarter of the way down, you'll see this particular item, so this element, a connector element, commented out. So for example, the close comment up here to the right is actually at the very end. So the first thing I do is I uncomment this. We'll look at some of the elements or some of the attributes in just a second, and I add the two lines you see at the end. The keystore file is the file that I just created. You could put this file any place. I created a subdirectory under conf called certs, and I just copied the file there. And then I entered my keystore password. As noted earlier, that's qubits. Now let me walk through these attributes quickly. So the default port number is 8443. On a regular web server, for example, Apache 2 or Nginx, the standard port would be 443. And then you can see the particular protocol implementation that Tomcat uses. Max threads is the maximum number of connections supported. We could change that. We're enabling SSL. We want that. Using the HTTPS scheme, we're going to get encryption automatically. This line is particularly important. You can see here that client authentication is turned off. In other words, Tomcat expects the client to challenge it, but Tomcat is not going to challenge the client. This is standard in web servers that support websites. And the protocol is TLS. We've talked about that before. Here's my keystore file with my self-signed and therefore worthless digital certificate. And here's the password for that keystore file. Now, once I edit this and save it, I need to restart Tomcat if it's running, because Tomcat reads the configuration information only on startup. And then you can perform a test, of course. So I used a browser to do this. You also could use curl. It's a bit quicker. But if you use curl, as shown here, you want to use the "insecure" flag, because again, curl is going to recognize that the digital certificate is self-signed and hence worthless. The configuration is relatively straightforward. It would be very similar, by the way, for any production-grade web server. The most important thing is to have one or more digital certificates and to let the web server know where those are located. So at this point, Tomcat is ready for wire-level support of HTTPS, and what we need to do next is configure a web service so that it takes advantage of this wire-level support. The purpose of this lesson is to take the various details we've seen so far about wire-level security and to bring them all together into a demo. You're looking at the working file https deployment.txt. For convenience, this file and the other files are combined in a zip called https demo.zip, and we'll talk about the other files in that zip in just a bit. So here's a quick overview of the demo. I've taken the predictions2 service. That's a REST-style service. It's servlet-based. It supports all of the CRUD operations. We saw it earlier. And I've redeployed it for HTTPS instead of HTTP. Now there's very good news here. This redeployment requires no change whatsoever to the service code. The only thing that changes is the web.xml file. And for contrast, here's the original file. It's fairly short, so it goes from here down to here. And the gist of the file is this. Any request that comes in for the predictions2 service is sent to the predictions2.predictions-servlet instance. So in other words, it's basically routing information, nothing more. Now, for the redeployment, essentially we have everything unchanged except there's a slight addition right in the middle, and this is the added section. There's a security constraint on a web resource collection, so we might have many different resources. In this example, we have only one. The URL pattern is given. This is the only thing that we might want to tinker with a bit. Basically, what this pattern says is, if anybody requests the predictions2 service, then everything in that service should be covered by this constraint. We could fine-tune this because in the deployed WAR file, we might have a public subdirectory and a special stuff subdirectory, and we might want to limit HTTPS services to the special stuff, not to everything. But to keep it simple, I've basically imposed HTTPS on the entire WAR file. My 2 cents, by the way, is that this is a better approach to take. Put everything under HTTPS because then it's less tricky. Now, under the user data constraint, you see the transport guarantee is for confidential. Basically, this covers all of the standard HTTPS services. In other words, peer authentication, encryption and decryption, that's really what confidential points to, and message integrity. So, in summary, I took the original web.xml and basically added this section here, redeployed, we're now ready to go. Now, let's turn to the client side. There are many ways to do the client. In this particular case, I've done the security part in the code itself, but I could also do this by using command line properties. I wanted to do it in the code to give you a sense of how much code is involved. The full source code, by the way, is available in the WAR file. What I've done here is excise the imports and some other code that we don't care about. Once again, the main point is to give a sense of how much code is required. So let me go through the essentials. The most essential part is we now need an SSL context. You can see that here. And we're going to get an SSL context appropriate for TLS because that's the version of HTTPS security that we're using. I've hardwired the password. We could, of course, send this in as a command line argument. And the reason for that is as follows. If you jump up here to this line, you can see test.keystore. Test.keystore is actually the key store that I'm using for Tomcat. So you might say the fix is in. Tomcat is going to deliver certificates to this client. This client is going to test certificate against the very same file, which I'm now calling test.keystore. So there's going to be a match. In production, of course, we wouldn't do this, but we're interested in the setup. Incidentally, at the line immediately above, you can see that we're using HTTPS to connect to Tomcat. Coming back down here, this password, qubits, is the password to get into that keystore file. The keystore file is then loaded into memory, basically in these next 3 lines. And then a trust manager is created, and the trust manager is initialized to this keystore file. So let me take a step back. Remember that the difference between a key store and a trust store is functionality, not file format. A key store is just a file that contains digital certificates to be sent to a challenger, and a trust store is just a key store that is used to verify incoming certificates. So in effect, I'm taking Tomcat's key store, where it holds its digital certificates, and I'm using that as my trust store. So as noted, the fix is quite definitely in. The SSL context is then initialized. The first argument is set to null. If it were not null, it would be my key store, but I know that Tomcat is not going to challenge me. When we configured Tomcat for HTTPS, we saw that. Client authentication was turned off. So Tomcat's not going to challenge me. Instead, my client is going to challenge Tomcat. So for simplicity, I've left the first argument to null. The second argument gets the trust managers. In other words, this is basically the code that's going to check the incoming digital certificates to make sure they're okay. And a secure random instance is used by the SSL context to generate whatever random numbers are needed in the course of doing encryption and so on. With all of this in place, we basically complete the initialization at this line. It's a relatively short, if a bit complicated, chunk of code. That's all of the code I need to enable my client now to talk HTTPS with Tomcat. Let's now put it all together by running the demo. For convenience, what I've done is put all of the client code in an executable jar. It's called predictions HTTPS client HTTPS.jar. I run this and it runs the standard series of tests, get all, post, put, and so on. And you're seeing the output for that code. Now, just for ease of reference, in fact, let me emphasize this by hitting the zip. I've taken all of these required files and I've put them in a working file called httpsdemo.zip so that everything is in one place. In this lesson, we're going to focus on users' roles security, one of the two sides of security. The other side is the one that we just covered, wire-level security. The two can go together, but they can also be used independently. For now, in this overview, we're going to focus simply on users' role security. Later on, we'll have a chance to talk about how this connects with wire-level security. So the working file you're looking at is called usersrolesoverview.txt. So let me begin with the two phases of users' role security. The first phase, the required one, is called user authentication. And this little picture reviews what we've seen before. So let's suppose there's a client against our web service, but we want to secure that web service. What that means in effect is, in order to get to the web service, the client has to identify itself. So it needs to provide an identity, but it also needs to provide a credential that vouches for that identity. Now, Java is very flexible here. We can secure the entire service, which basically means the whole WAR file. So I've depicted that with a URL that ends with my web service. But we could also, if we like, limit the security to part of the WAR file, in effect, to selected operations. So in this case, with the URL ending with my web service/special. So only those operations under special would be secured. Now, the second phase in users' role security, this is the optional phase. It typically occurs under the hood. This is role authorization. And if you're looking at REST-style services, it's easy to explain. Basically, this has to do with which CRUD operations are allowed for a particular identity. So, for example, I might hit a web service and be allowed to read information because that's the limit of my authorization. You might hit the same web service but be able to, for example, edit or even delete information because you have other authorization. Now, with respect to users' role security, we have seen the rather clever Amazon approach to this. Clever because it's so simple. Again, when you register with Amazon, you get an access ID. That's your identity. You also get a secret key. The secret key is not the credential itself. The secret key is used to generate a hash value that you send over the wire, and it's that hash value that acts as the credential. What Amazon does on the receiving end is it recomputes that hash value. If its computation matches yours, it's a go. Otherwise, you're denied access. Now, for programmers, in fact, for anybody who uses computing devices, this two-phase security process is familiar, although we don't always use these terms. So, for example, when you log into any device, a desktop machine, a handheld, whatever, you typically provide a username and then a password The username obviously is the identity. The password then acts as the credential. Down here in about the middle, I just review basically the terms again: user authentication, role authorization. It's convenient to refer to these together simply as auth. So the first auth is the user authentication, the second auth is the role authorization. Now let's turn a bit to the programming side of things. So we want to divide the labor again between the service side and the client side. So on the service side, there are, at least in principle, two approaches you might take. You might do security at the application level. This is not a particularly good idea, doesn't scale, it's ad hoc, takes too much work. You basically wind up, when you go from an unsecured to a secured service, you wind up changing the code, or at least injecting new code into old code. A better way, so the preferred way, is to do what is known as container managed security. So for example, if Tomcat's going to be our web server, or anything comparable to Tomcat, we want to turn the user's roles work over to Tomcat. That's basically the gist. Now Tomcat provides all sorts of options for doing this. They're quite sophisticated, and we'll look at those a bit later. For now, I want to turn to the client side, because the question becomes, how do we get the identity and the credential over to the server? So Tomcat out of the box does not support the Amazon approach. Instead, Tomcat is really looking for a username and a password, and so the client needs to get the username and the password in the incoming request in such a way that Tomcat can find it. So we turn again to HTTP. It has something called HTTP Basic, which is short for Basic Access Authentication, and it supports storing an identity together with a credential and an HTTP header element. The only catch is that this information has to be formatted in a particular way so that Tomcat is able to extract it. And we'll get into those details when we have a look at some code. In this lesson, we're going to focus on how Tomcat can be configured to handle users' roles security. I'm going to build on the previous example, the Predictions 2 service, which we enabled for wire-level security, and I want to draw a comparison. In order to make the Predictions 2 service available over HTTPS, we had to change something on the Tomcat side. We had to enable it to accept HTTPS connections, and we had to change the deployment file, the web.xml, in the service. But no code had to be changed in the service. The same thing is going to hold here. Now, Tomcat has some unusual jargon. With respect to users' role security, Tomcat has the concept of a realm. A realm is basically a data store for identities and credentials. So, for example, you might have a database table that contains usernames and passwords, that sort of thing. Tomcat comes with 6 realms already available as plugins. You can create your own. Some of these are quite sophisticated. There's a realm that would support, for example, an LDAP-based security provider, some sort of proprietary single sign-on provider. There's a lockout realm that guards against so-called dictionary attacks, where somebody tries repeatedly to guess a password. So these realms are hardly toys. They're production-grade realms, and they include a relatively easy-to-use one called the memory realm, and that's what I'm going to use for this demonstration. The memory realm has that name because at startup, Tomcat reads the contents of an XML file into memory. So here's the file for Tomcat 8. As you can see in the body of it, everything is commented out. So Tomcat provides this basically for tutorial purposes. We could edit this file as is, but in order to make the point that not much has to be done, I've redone it, and basically the body now contains just 2 lines. The first line declares an authorization role called Big Shot. Any name would do. Technically, we could drop that line, but it's a good idea to have it. And this is basically the authentication authorization section. So we have a username, in this case Mo, a password, the word mo 3 times, capitalized each time, no white space, and the roles, well, in this case, there's a single role, big shot. Were there multiple roles, as you can see above, at this line, they would be separated by commas. They could come in any order. So after making this change to Tomcat users.xml, I need to restart Tomcat because it reads this file only on startup. Now there's only one other change to make on the service side, and that's to change the deployment file web.xml. So let me show you that. This is an expansion of the earlier web.xml that we looked at for HTTPS. So let me focus on the changes. The first change is this one. Again, technically this is optional, but you'll get a warning if it's not included. What we're doing here is declaring a security role name. So in this case, you can see Big Shot. And if we had others, we would name them in any order. The security constraint we had before, in particular, what we had was the so-called user data constraint, which mandated encryption and decryption, and basically the other basic HTTPS services. The new item in this case is the authorization constraint, and as you can see here, we put in the role name declared earlier, Big Shot. So the gist of this says that in order to hit this web service, you have to be authorized as a big shot. If you're not, you can't get in. The other change is the login config section, and the authentication method is HTTP basic. I've put it here in all caps. That's traditional, but mixed case, lowercase would do just fine. So in summary, we've just done some slight changes to the web.xml for the service, and we've basically configured Tomcat's memory realm by providing the information, username, password, authorization, roles. That's pretty much it. In this lesson, we're going to focus on the client-side code. In particular, we're going to look at how the client has to send the username and the password to the revised Predictions2 service so that Tomcat can perform the user's roles security. For convenience, I've put all of the files needed for this application in a zip. It's called auth.zip. And what you're looking at right now in my Emacs editor is predictions HTTPS client AA.java, cut down, of course, for readability. But the full version is included in a jar file. It's an executable jar file that I'll demo in a bit. So let me go through the important parts. This is a client, again, against the Predictions2 service. We're going to use wire-level security, HTTPS, and we're also going to introduce, from the client side, users' roles security. So at line 1, you can see the URL as a string, HTTPS, and so forth. The name of the WAR file is Predictions2AA, and that's included in the zip as well. Once again, we need the trust store because automatically the client is going to challenge Tomcat to send down its digital certificates. So that part is pretty much unchanged. Down at line 2, this is also unchanged code from the earlier HTTPS version. So this is basically the HTTPS setup all the way down here. And finally, at line 3, we get at the new parts. So we now need a username and a password. As you can see, I've hardwired the username and the password into the code for convenience, but we could, of course, read these in as command line arguments. What follows then in the full client code is the usual series of CRUD tests. So there's a get one test, a get all test, a post test, a put test, a delete test, and so on. So I've not shown the code for those. The important point for us is that each of these CRUD tests invokes this private method called getConnection. So this is where the action occurs for our purposes. So getConnection at line 4 expects 4 arguments. There's the URL, so that's the string converted into a Java URL instance. There's the verb, get, post, put, delete. and the username and the password, in this case hardwired, as shown above. We now jump into a try block and open up an HTTPS URL connection. We've seen that before. We set it for both input and output. We're going to be sending data over to the service. We're going to be getting data back from the service. So we need both of those. And then the request method is set. So the get, post, put, delete, and so forth. Now we get to the point of interest for us. So let me just do a tiny bit of background here. Basically, Tomcat implements the HTTP 1.1 spec when it comes to so-called basic user authentication. What that means, in effect, is that it wants the username and the password configured in a very precise way. We've seen this sort of thing before in writing clients, for example, against Amazon. So the same thing occurs here, although we're following, in effect, a standard. The first thing is this. We create a string. I just call it user pass here. And it's the concatenation of the username and the password with the two separated by a colon, no white space. So in this case, it's mo, colon, mo, mo, mo. And the last three mo's, of course, are capitalized. Now, there are two further steps. Next, we create another string called basic, followed by a single blank, followed by basically the base 64 encoding of this username password concatenation. So this, in effect, is required by the standard. So this is the fussy part, if you like, at line 6. Finally, at line 7, the URL connection class has very convenient properties. I'm using one of those right here. Con set request property. This basically is going to create an HTTP header element. The key for that element is going to be authorization, even though technically what we're doing is user authentication. So it's authorization, and then this base 64 encoded combination of the username and the password. With those changes, we're now good to go. So let me demo this from the command line. So as you can see, I have an executable jar. It's called predictions https client aa.jar. It's included in that zip file. I'm going to run it and hope for the best. We get some XML output. This is the output from the standard series of CRUD tests that you've seen any number of times. In this lesson, we're going to focus on users' roles security against a SOAP-based web service. The examples we've seen so far have used REST-style services and, of course, clients against those services. So to begin, we need a service. This is a minimalist service, quite deliberately. We don't care so much about the operations. We just need some example. So this is the temperature conversion service. It has two operations, centigrade to floating point conversion, floating point to centigrade conversion. And you'll notice, as in the REST-style services, there's nothing in here that hints at security, and in particular, at users' roles security. All of that is done in the configuration, and the web.xml used for this service is essentially the same as the one used for the REST-style services. In fact, the security sections are exactly the same. There's no change at all. The only difference is that the SOAP-based service needs a so-called interceptor servlet that we talked about earlier. There's also no change whatsoever to the Tomcat configuration. Everything remains the same. So this service, as you can see, the source file is tempconvert.java, is deployed in the usual way. And in fact, in the working files, there is a zip file called soap.urs.zip that contains all of the files that we're going to be looking at. So that's for convenience. And there's a README in there to remind you about how to compile and run the client. The WAR file is included. Now let me turn to the client code because that's our main interest. And this file is an abbreviation of the actual client. So this working file is called tempconvertclientshort.java. It won't compile because I've deleted the imports and other extraneous information. but the actual client code is included in the zip. I have the lines numbered again, but I'm going to actually start near the bottom and then move up to the top. So let me go down to line 5 and explain what that is. A binding provider in the context of SOAP-based web services is basically the transport level. So up here, what we're creating is a temp convert instance, in other words, an object that allows us to invoke the operations in the service. But now what we need to do is get down to the transport level. In this case, it's the HTTP level because we need to inject the username and the password into the HTTP request. The data type that Java uses in Java SOAP-based web services is called the binding provider. So I get the binding provider, and then down at lines 6 and 7, I use these put operations. Basically, the request context that you can see here is a map that represents the HTTP request. So I put in the username, the key, and then the actual username. In this case, once again, it's Mo. And then the password, and once again, the password is Mo, 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 with the M's capitalized. By the way, this username underscore property and password underscore property are simply strings, and in the comments I've shown you what these strings are. So in effect, down here, this first key, that string, is followed by a colon, followed by Mo, the username, and then the second key, this one, password, followed by a colon, followed by Mo's password. Now this is slightly higher level than what we saw in the REST-style clients. In those clients, we were very close to the HTTP metal. We had to combine the username and the password, as you'll recall, into a single string. We had to base 64 encode that string. In other words, we had to basically follow the HTTP 1.1 spec. In the SOAP client, we're working at a slightly higher level, so a more intuitive level, if you like. And that's appropriate because SOAP is further from the HTTP metal. Now let me move all the way back up to the top to line 1. You'll see that this code occurs in a static block. So let me explain what I'm doing, and then we'll look at the details. Suppose you're in development mode and you don't want to create even a dummy trust store. So the dummy trust store we've been using is a file called test.keystore. And we created that using the key tool. But suppose you don't want to do even that. So you want to use HTTPS, and you can see up at this line, the URL starts with HTTPS, but you don't want to do the mutual challenge part of that. Well, Java provides a number of ways to work around that. You could do one of these at the command line, but I prefer to illustrate in the code because I think it makes things clearer. So at line 1, we create a trust manager, which is basically an array. And we're going to put one thing in that array. So you can see here, new X509 trust manager. X509 is the standard format for a digital certificate. And then in the body of this constructor call, we define 3 methods: get accepted issuers, check client trusted, and check server trusted. So at lines 2, 3, and 4. And you'll notice, of course, that these are minimalist definitions of these methods. In other words, at line 2, we return null. We have to return something to get by the compiler. And at lines 3 and 4, we have empty bodies. The critical thing is that none of these functions throws an exception. And this basically tells the Java runtime, the security engine, that everything is okay. So you'll see if you unpack the zip file, there is no trust store file included. We basically don't need one because of lines 1 through 4, and then the follow-up setup below that. Now, let me do a demo to show you how this all works. As noted, there's a README in the zip file that repeats this, but it's always good to see that the code actually runs. So let's do that now. So I'm going to my bash shell. I have Java temp convert client. That's the compiled version, obviously. It expects 2 command line arguments, the username and the password, and these are the same as in the earlier examples. So the client makes 3 calls against the service, and as you can see, the output here is illustrating what the inputs and outputs were. So the inputs to the service were 3 temperatures, the outputs were the conversions of those 3 temperatures. In summary, what we've looked at is the slightly higher level API that you get on the client side if you're going against a SOAP-based as opposed to a REST-style service. In effect, we could stay with the REST-style approach if we wanted to, even in a SOAP-based service. But if you're going to write a SOAP-based client, you might as well take advantage of the higher level API. This is the wrap-up lesson, and the working file is, of course, wrapup.txt. So let me do first things first. I'd like to thank everybody for having participated in this series of movies, and also to congratulate everyone. We've worked through lots and lots of code. As programmers, we all love code, but we all recognize the challenge of working through code, especially somebody else's. So I appreciate your patience as I've shown you my code. I hope you'll have an opportunity to play with it and to make it better. So in this wrap-up, I'd like to go back to 2 points that were brought up way at the beginning. So in the introduction, basically, because those 2 points, I think, are a nice way to wrap up what we've done. What appeals to me about web services, and I hope to you as well, is that they're so powerful and flexible. So the components of web services, these so-called pure functions, these very simple operations, can be put together to form services, and services can be orchestrated together to form ever more complicated software systems. So I like that power and flexibility very much. I like, in other words, the service-oriented approach of web services. At the same time, web services are very practical. They basically piggyback on existing infrastructure, networking infrastructure, protocols such as HTTP, document exchange technologies such as XML and JSON, and so on. So when you do web services, it's not as if you're reinventing the wheel. You're basically using, and we hope extending, technologies that are already in place. As we work through the many code examples, I hope that the big picture hasn't been lost. Now, in any case, is a good time to go back and look at the big picture. So thanks again. Good luck with web services. Please take my code and make it much better.